this section we will get familiar with the ETAP environment. So throughout my course I will be using 12.6 version of ETAP. However, if you are using ETAP 14 or ETAP 16, then you can still follow the course. We will discuss the additional features of the later versions sometime in the future. So after you open ETAP, this is what you come across. So I will go to File, then I will click on New Project, and I will enter a name for the new project and click on OK. Then it will ask for user information, full name, description. I will just click on OK. Then I will enter into the edit mode, which is the default mode. So this is the edit mode, and this is where we are supposed to draw a single line diagram. So before that, we would like to get familiar with the ETAP toolbars. On my left side, I have the systems toolbar over here. Here we have different systems, one line diagram, star system, underground raceway system, ground grid systems, and so on. And just below the systems toolbar, we have the wizard toolbar. I will explain this later. And on the top we have the mode toolbar. Right now I am in the edit mode, so I can change this to load flow analysis mode, short circuit analysis mode, and so on. So we'll go back to the edit mode, and just above the edit mode I have this presentation toolbar. So I will show you how to use this after drawing a single line diagram. And just above the presentation toolbar, we have the menu toolbar. So we have several options which we can use from here, such as open, new, save, print, just basic elementary. So here we have show grid lines and get from template, hyperlink, and find. Also we have this power calculator, which is a handy tool. We can use this to calculate the MVA, MW, etc. So I'll close it now here. And just above this we have the main toolbar over here. Let us go through some of these options over here. I will not go through file, edit and view, which are self-explanatory. So I will go to the project here and I will click on information. So this is where you enter your project information, such as your project title, your location, contract, engineers. These are just optional, you don't need to give them anyway. So I'll go to the standards, and from the standards I can change the standards to IEC, or I could change the frequency and the unit system and so on. These are also optional. And again I have your settings, so I could change the settings from here, such as loading categories. I can change this to normal or peak time. I could edit this and make something else. Again we'll go to some more options, and this is for the saving. So ETAP automatically saves for every 30 minutes, which you can change over here. I have put this at the default of 30 minutes, but it's better to reduce it, and I have also asked it to prompt me before saving the project. So I'll keep this on and I'll put that like that, and I'll click on OK. Next we have the library over here. So ETAP has a very large library consisting of several devices such as cables, fuses, relays, reclosers, and so on. So if you want to add any element which is not available in the ETAP library, you can go here and enter it from here. So let us put something new in the relay library. So I have to take this relay over here. So the relay library comes I think I will put a new manufacturer. So I'll go here and click on add. Then I will enter the manufacturer name and reference web link. These are optional. I'll click on OK. So my manufacturer name has come across from the manufacturer's list. Next, I will go to the model. If you want to filter depending upon your protection type and your function, you can just click here, and mine will be a general purpose one. So the function will be overcurrent. So I'll click on that, and to add the model, I will come here and click on add. So I will provide a model name. This is something I just made up. I'll take the relay type for electromechanical. No, sorry, the electronic one. Sorry, and the protection type to be the general purpose one. And I will take two trip elements, the overcurrent and instantaneous one. Then I can change the current rating to a 1 ampere relay, and you can pretty much change anything from here. You have to get the data from the manufacturer's datasheet. Just click on OK, and the item will be available in the Etap library. So I'm not going to save this. I'm going to click cancel, and I'm going to remove this. So I'll click on OK, and that's it. I will close the library, and again back to the edit mode. And over here I have default options such as I can change the display fonts, display options, block options. I could put in presentations and so on. You could go through all this. I'm not going to go through all this because these are pretty much self-explanatory. Tools, I could change the bus size, symbols. I could change the symbols from the IEC to the NSI or something like that. I could change the orientation and so on. Again, you have to play with these options to know more about it. And these two we don't have to bother about these two, that is self control and real time, until we are connected to a real time system. And the window option is simply to toggle between different windows. See, if I go back here, I'll click on the project editor. The project editor comes, and I go back to the edit mode. So that's it. And here we have the help. Once you are in the edit mode, you will come across your right side to see the elements toolbar over here. This consists of all the elements required for your single line diagram. And over here we have the protection elements over here, such as CTs, PTs, voltage relays, overcurrent relays and so on. And just below this we have the DC elements. We have charger, UPS, variable frequency drives. Everything here will be DC. And if you go to another mode such as the load flow mode, then the options changes. So on the next lesson, we will learn to draw a single line diagram in Etap. In this lesson, we will learn to draw a single line diagram in Etap. We have our window open here. We are in the edit mode. I will go over here and click on the show grids option. I will have a reference of my single line diagram, so I will know the alignment. And let us draw something simple. Okay, then I will go over here to the elements toolbar, click on a power grid, and I will have to drag it over here and click here. So the elements are pulled from the elements toolbar like that. And let us add a transmission line, transformer, and let me see. Okay, we will need a cable, and a load. So this is it, and we will need buses. So I'll click on the bus option over here and come here and click over here. So again, if I want to go and pick up a bus, I will have to come to the elements toolbar. Another way of doing is that I will go and double click over here. So this will remain selected, and I will click like that over here, and I will press escape to remove from the selection. Next, we will have to connect all these elements together. So I will come to this connection point over here. So as you can see, this turns to pink, and I will click on the pink over here and drag it to the bus until the bus becomes pink. And you can also drag the elements like this. I will drag the line like this and go to the bus until it turns pink and leave it there and drag this back. Okay, so let's go about connecting all our systems. When drawing a single line diagram, it is best to make sure everything aligns in a perfect way so that it can be pleasing to your eyes. So one option to do this is to select your single line diagram. Right click, then I will go to the alignment option over here. So you have different alignments. I will select this one over here. So everything comes in a single line. Then another thing you can do is over here I have only a single branch from the transformer. If you want to make another branch, then it's better to make a template of the current branch. So I don't have to make another branch from the start. So I will just select this over here. Right click on this, or I will go to this option over here, that is add to template. I'll click this over here and I will select a template name. Let me put it as 3. Then I will save it over here. Okay, template was successfully generated. I will click on OK. Then I will go over here to get my template, or I can simply right click over here and get from template. And I will take this template. I'll click on OK, and here we see this same has come as a template. So I'll put it over here and I will connect it to this bus. Also, we can drag this bus like this over here, and you can also change your connections like this. So it could be more appealing. For every element there will be a terminology such as bus 1, bus 2, bus 3 and so on. So when you are making templates, you will have this cable 1 and cable 1-1. The next feature that I would like to discuss is the system dumpster. Let me show you how it works. So let me select a select a bus. Okay, I will select a bus, and when I put the bus over here, so it numbers it as bus number 5, and I'm going to delete this bus number 5, and then I'm going to look into the dumpster, which is over here, the system dumpster, and what I see is that the bus 5 is being in the dumpster. So if I want to bring back the elements to my single line diagram, so I could go back to the dumpster, then I would come here and I would copy this, and I will go back to the single line diagram and I would paste it over here. So this over here. Okay. Now the bus has come back, this is bus number 6. Now when I go back to the dumpster, I can still see my bus number 5 over here. So if you want to bring the element from the system dumpster, before it was bus 5, now this is bus 6. If you want to make this bus 5, then you will have to go to the system dumpster and delete this bus. Over here, I will go and delete this. And when I come back to my single line diagram, and I will have to select another bus and I put over here, see, this becomes the bus number 5. And this is how it is done. So it is simply like a recycle bin. So we'll delete both of these and go to the dumpster and see. I have deleted both of these. You can see it in the system dumpster. And the next feature I would like to show you is the composite network. For very large systems, you will like to create some subsystems, so it could be more understandable. For that purpose, we have the composite network over here. So I will click on the composite network and I will put it here. So this becomes network 1. So I will connect it to this bus. Okay, then I will double click on this. Then it will open into the subsystem. So I will again go here and show grid lines. Then let me connect this to something like, okay, we'll connect a static load over here to the bus number 3. Let me go to my main window. This is the main system, and from the main system we go to the subsystem. Actually, this is all connected to a single system. That's all for this lesson. So see you in the next lesson. After drawing the single line diagram, we will have to write our components present in the single line diagram. Before that, we will add a generator over here, and we will check the circuit continuity using this option here. So now the generator is in the faded condition, which indicates that the circuit is not connected properly. So let me take this off. After connecting this and again checking for the circuit continuity, everything is fine. And let's start by writing our power grid over here. So double click on the power grid and the power grid editor appears over here. This has many tabs or pages. So every element will have an information page or the info page. In this page we will have the information such as the ID, device ID, the bus to which it is connected, and the equipment tag name and description. And here the configuration is also present. This is for normal condition or normal loading category. We can also change this in the study case. And here this is the mode. It is put at default in the swing mode. So let me go to the rating page over here. So this is rated for a 110 kV voltage, and the short circuit values will be like 1000, SPI-R ratio 7, and this fills these impedance values with the 100 MVA base value, and everything else I will put on default over here and click on OK. So this updates the bus voltages over here. Bus 1 and bus 2 are now at 110 volt. Then go to the transmission line over here, double click on the transmission line. Again the transmission line editor comes over here, and this shows the information page, and from the information page I have the length selected over here. Let me change this to kilometers, and the length will be 5 kilometers with 5% tolerance. Then I will go to the parameter over here, and Etap has a large conductor library. So I will go to the conductor library. Let me select a conductor, I will select this conductor over here and click on OK. And then for the ground wire, I will go to the ground wire library over here and select the EPRI, and this I will select this cable, this conductor over here. Click on OK. Then go to the configuration page. Then configuration type will be horizontal, and the height will be 30 feet, and the spacing will be 2 feet. So this updates the GMD value over here, and this will have one ground wire which will be at 4 feet high. After that is done, I will keep everything else in the default values and click on OK. And next, for the transformer, double click on the transformer. This brings the transformer editor over here, and let's go to the rating page over here, and it is rated for 110 to 11 kV, and the MVA will be 12.5. So this automatically updates the full load current over here. And go to the impedance page and use the typical values over here. If you have the manufacturer data with you, you can enter it manually. Then everything else I will keep on the default values. And over here we have this cable over here. Let me select this cable, and the cable editor appears over here. So the length of this cable will be 10 feet, and let me select the cable from the library. So I will select this cable, which is the frequency copper type, which is rated for 15 kilovolt, and the underground ampacities and the ampacities are also shown. So let me select this cable size and click on OK. Everything else will be in the default values and click on OK. And I will do the same here. And for the load, I will double click on the lump load over here and go to the nameplate, and this will be 2 megawatts operating at 97% of power factor. Okay, I want 2 megawatts over here. Okay, now it's fine, and click on OK. And here the load will be operating at 94% with 3 megawatts. Okay, and the load connected to the composite network will be 1 megawatt, and that will be operating at 89.4% of the power factor, and click on OK. And for the generator, we will double click on the generator over here, go to the ratings page and use a 3 megawatt generator, and go to the impedance model over here, or else you won't get the correct capability curve. So go to the impedance model over here. If you have the manufacturer data of all these impedances and the dynamic model, use that, or else use the typical data option over here. And coming back to the capability curve, I will use the capability curve to determine the reactive power limits, and I will be generating about 1 megawatt using this generator. Everything else I will put on default. Click on OK. And this is how you rate your components in ETAP. So every element will have different editor windows, and it's up to you to provide these values accordingly. Sometimes if you don't provide the model data of generators or motors, then you can't conduct certain studies such as transient stability studies or motor starting analysis, etc. So you will have to provide your values to your components before running any simulation. In this lesson we will discuss briefly about the presentation toolbar over here, and also about creating study cases and editing those study cases as well. So in order to use this presentation toolbar, you will have to know what these are used for. So at this point over here we have the cable manager. So selecting the cable manager, this shows all the cables that are used in my single line diagram, and we can also classify this depending upon the voltage ratings also. So let me close this over here, and over here we have the configuration manager, and from the configuration manager I can change any of these from here. So the generator is already put at voltage control mode by default, and the power grid is put at swing mode by default, and we can also change these to intermittent or spare type of loads if we want to, and we can also select all these elements separately, and we can configure this from here. And next option we have here is to create a new presentation. So this copies the entire single line diagram into a new edit window. So let me click on OK. So this is my new edit window. If you notice here, the edit mode window has changed. So let me go back to my old edit window. And over here we have the data manager, and from the data manager we have the elements, total elements used in this single line diagram. So that's how you use your presentation toolbar. And coming into the mode toolbar, if you select any of these two modes over here, for example if I choose the load flow mode over here, then you will have this study case already appear over here. So at default there will be always a study case available, and if you want to create a new study case, I will click on this briefcase over here, and I can duplicate the study case and again reconfigure my single line diagram and conduct the load flow. And you can also create a study case using the project editor window over here. So from the project editor window and going to the load flow analysis over here, I can create a new case study from here as well. And that's it. See you in the next lesson.
In this section we will be performing load flow analysis on ETAP. So before getting into ETAP, I would like to discuss some of the terminologies used for load flow analysis and why load flow analysis is done. Let's go through a brief theory. What is load flow? Load flow is the solution for the entire power system which is under consideration. So that's it. And why we are using load flows? In order to compute the voltages, phase angles, real and reactive power flowing into every line. And why are we doing this is to design a substation or design a power system. So after doing a load flow, we get the current flowing through every line, every node, and based on that current we can then select the suitable cables, suitable transmission line conductors, suitable insulators, and the circuit breaker ratings and so on. So load flow is an important analyzing tool that is used to design our components used for power systems. how we will do the load flow is by using these iterative techniques. So we have the Gauss-Seidel method, Newton-Raphson method, and fast decoupled method. There are also other methods. These are classified based on their speed of convergence to a solution. So since these are iterative solutions, then we have to get a faster rate of convergence to quickly come up with a solution. Fast decoupled method has a greater rate of convergence compared to the Newton-Raphson and with the Gauss-Seidel method. Next, we will look at some of the terminologies used for the load flow. In the load flow analysis, we are classifying buses as three. So let me go to the first one, is the load bus. For the load bus is any bus where the load is being connected. So the real and reactive power are drawn from the supply. This is also called as the PQ bus. The voltage and phase angles are unknown, but we know the real and reactive power of a load bus. And the next one will be the generator bus. And for the generator bus, this is also known as the PV bus. So the real power and the voltages are known, and the reactive power limit is also known from the capability curves. So the phase angle and the reactive power is to be determined using the load flow analysis. And the next one is called the slack bus. This is also known as the swing bus or the reference bus. There will be only a single slack bus, so there will be a single voltage and phase angle. So the voltage and the phase angle are known. The voltage we usually provide will be 1 or 100%, and the phase angle will be 0. And all the other values will be computed based on this reference value. Next, we will get into ETAP, and we will understand better after doing a load flow analysis.
In this lesson, we will conduct a load flow analysis in ETAP. So I have the single line diagram already open on the ETAP window. So in order to conduct a load flow analysis, I will have to hover over to this mode toolbar over here and select the load flow analysis mode. After selecting the load flow analysis mode, on the right side I have this option called run load flow. So after clicking on it, it will ask for an output file name. Enter in a file name and click on OK. So now we have some values alongside our single line diagram over here, and also we have some percentages displayed alongside our bus. So in order to understand what these are, I will go over to this unit show on my right side and click on it. And here we have the units of the displayed numbers, which are kilowatts and kVArs. So now we have the total power drawn from all the sources over here. That is, from the grid we are drawing about 5 megawatts of power, and from the generator I am drawing about 1 megawatt of power. And these percentages are used to represent the percentage voltages at each buses. So in order to understand much better, I will go over to the display options over here, and we can change the display options from here. So the bus voltages are presently at percentage voltages. So if I change this over here, these become kilovolts. So this is 110 kilovolt, and over here we have 109.9 kilovolt. And similarly, all the bus voltages are displayed alongside their buses. And let us view these in amps. So let me go to the display options over here, and I will change this to amp, and I will click on OK. So I am drawing about 26 amps from the grid, and over here I am drawing about 140 amps from the generator. And next thing I will have to look is the alert view over here. If we have anything faulty in our single line diagram, mainly referring to the oversizing or undersizing, Because of that, we will have overloading or underloading. ETAP doesn't show you if anything is underloaded, but it will show you if the system is overloaded or if the generator is underexcited or overexcited. So let me go over here and see if we have any alerts over here. So clicking on the alert view, and on the alert view I have two windows, which is the critical and marginal over here. Presently we do not have any problem with any of our devices, so it is clean. Let me close this over here, and over here we have the ampere nodes which are drawn by the two lump loads over here, which is 2 megawatts and 3 megawatts each. And next thing I will have to show you is the report generator. I can select the load flow report from here and click on the report manager, and this gives me the study case and load flow report for the study case. So maximizing this, I have the voltages and phase angles, the generation at each bus and the load connected to each bus, and this will show the load flow through all the buses. So let me close this. And next thing which I want to show you is this over here, which shows the load terminal voltages, and after clicking on this I have the load terminal voltages displayed over here. So I have 11 kV and also 11 kV terminal voltages at the loads. So let me turn this off, and here we have the line and cable voltage drop, and after selecting this I have 0.067. so let me change the display units over here. I will change it to percentage and click on OK. So I have about 0.1 percentage change, I mean 0.1 voltage drop. Over here I have 100 percentage, and over here I have 99 percentage. So we have a voltage drop of about 0.1 percentage. And here we have the load flow result analyzer. We can use this to analyze our reports. So I will click on the general info, and here we have the study case. All the study case that I have created using this will be displayed over here. So presently we are in this study case, and we have the loading categories. So everything is loaded, every load is put in design mode, so the diversity factor and so on. If I want, I can change the loading category. For that I will have to double click on this, and on the nameplate I will have to change this over here. So I have only put the values for design and normal. If I want, I can put values in here as well and change the loading categories from the load analyzer over here. So if we want to change the type of load or the diversity factor, then I will have to go to this option over here, which is called the load analyzer. And next thing I want to show you is the edit study case over here. So hovering onto the presentation toolbar and clicking on the edit study case, the load flow study case option appears over here, and from here too we can change the rated voltage units and power in MVAs to kVA and so on. So here we also have the method for load flow studies. So at present it is at adaptive Newton-Raphson method, and the precision is 0.0001. So the maximum iteration is 99, and this is the precision value, that is 0.001. If I want to change the precision, I can, but this is pretty good for me. And from here I can also use the loading, I can also choose the loading category which I mentioned before. And over here we can change the conditions over here, that is for critical values and marginal values. So about 95 to 100% is the loading the percentage voltage for the bus, and if anything is shown below 95%, it already puts it in a critical mode. So I can change these options over here and stop the alert manager from notifying me. And this is how you conduct a load flow study in ETAP. In the previous lesson, we learned to conduct a load flow analysis on ETAP. I also mentioned about different loading categories and diversity factors. So in order to understand this, we must also know that for a power system, the load is subjected to changes with respect to different seasons. So in many parts of the world, we have winter peaks owing to different heating loads, and in other parts of the world we have summer peaks due to air conditioning loads in the summer. So ETAP provides this feature of simulating load flow analysis using different loading categories. So in order to better demonstrate this feature, I will show you a case study. Here we have the case study for the system, and I have 3 loads here as in the single line diagram, and for the design category I have put all the loads at 100%. So in my country during the monsoon period we have less consumption, so the load 1 becomes 50% and load 2 becomes 60% and the load 3 becomes 40%. And during summer we have large amount of consumption and we have our peaks during the summer, and the load 1 becomes 90%, load 2 becomes 95% and load 3 becomes 90% of the design values. So let us go back to ETAP to simulate this. To conduct the load flow analysis for different load categories, I will have to double click on the load. On the nameplate, I have different loading categories over here. So I will be entering values for the monsoon load, but at present the loading category doesn't have such an option. So I will have to edit any one of these loading categories to include the monsoon load. I will have to go to the project settings and loading categories and edit the winter load to the monsoon load. I will double click on the load 1 and my monsoon load is about 50%. Summer load is about 95%, and I will click on OK. Similarly for the load 2. And load 3. Then I will have to go to the load flow analysis mode and I will have to create a new case study. Although I have several other case studies, but I better prefer to make another one. And let me conduct the load flow over here, and I will put the study case as and I will click on OK. So these are presently in the design category as shown because we have not changed our load categories as of now. So let me go to edit study case over here. I will go to loading. I will change the loading category to monsoon load and I will click on OK. Then after I run the load flow analysis, I have the modified load flow for the monsoon period, and similarly I will make another one, and For this, I will also change the generate ratings as well. So I will put the generator in standby. So I will only put out about 800 kilowatts, and I will click on OK. And let me create another study case. And I will go to edit study case and go to the loading over here, and so I will change this to summer load, and this I will change to standby, and I will click on OK. Then we will run the load flow analysis, and over here we see the load flow analysis for the summer period. So this is 800 kilowatts, and this is how you run load flow analysis for different seasons. And in order to analyze all the case studies at once, I will go to this option over here, load flow result analyzer, and we see the general info. So we have 3 case studies now. This is load flow 1, load flow 2 and load flow 3. So here the diversity factor is all at normal loading, but we have these loading categories as different. Over here we have design, over here we have monsoon, and here we have summer. And similarly the generation categories are also different over here. And we can see the different power over here. We have the total load megawatts over here to be about 6 megawatts of power during the design loading category, and this becomes about 2.5 megawatts of power in the monsoon loading category, and this becomes about 5.6 megawatts of power during the summer category. And I will click on close. So I think you have a better idea of load flow analysis. In the next lesson we will learn to conduct a short circuit analysis. So see you in the next lesson. In this section we will learn to conduct a short circuit analysis in ETAP. Before entering into ETAP, we should know why we conduct a short circuit analysis in power system. Short circuit studies is used to rate switch gears and substation equipments. It is also used for setting of relays, because relays should be able to distinguish between the load current and the fault current. It is also used for stability studies and designing of earth mat as well. Faults occur due to installation failure of equipment and flashover of lines initiated by lightning, permanent damage to conductors and towers, and accidental faulty operation. Mainly faults are classified as 3-phase fault, which is also called the symmetric fault, line-to-line fault, double line to ground fault, and single line to ground fault. The last 3 are also known as unsymmetrical faults. So let us enter into ETAP to conduct a short circuit study. In this lesson we will learn to conduct a short circuit analysis in ETAP, and I have my single line diagram already opened up for me. So in order to conduct the short circuit analysis, I will have to hover over to the mode toolbar and select the short circuit analysis mode over here. So I have already selected this over here, and on the right side we have the short circuit analysis options over here. So let me click on the 3-phase short circuit analysis, and this is the ANSI C37 standard. So after clicking on this, you will get this error over here, because in order to conduct a short circuit analysis you will have to fault any of the buses. So in order to fault any of the buses, I will have to click on the bus like this over here and select on fault, or I can go to the edit study case option over here and choose the bus I want to fault, and I will click on OK. So now the bus turns into red color, which indicates that this bus is fault. And next, when I will run the 3-phase short circuit analysis, Now we have this value over here, that is 8.9 kilo amps, and we also have some values alongside our single line diagram. So let me go to the display options over here, and I will click on show units, and I will click on OK. So these are the fault current contributed by each branch over here. So the voltage drops at this bus to 93.329 kilovolt, and over here to 96.295 kilovolt, and this is the fault current. And in order to get the fault level, we will have to use the pre-fault voltage and the post-fault current. So here the pre-fault voltage is 11 kV, so we will have to multiply the 11 kV with that of 8.9 kilo amps to get the fault level. And below this we have the single phase short circuit, and over here we have this option, which is the reliable way of running a short circuit analysis, because over here we have 3-phase fault, line to ground fault, double line fault, double line to ground fault, and is simulated for half cycle. So I'm using a 60 Hz system, so half cycle means about 8 milliseconds. So let us conduct this study over here. So I have already faulted my bus 3. So when I click this on over here, these values are populated alongside my single line diagram. So this is about 8.94 kilo amps at 84.9 degrees. So in order to better understand what we are looking at, I will go to this report generator over here. So let me select the complete over here and generate a report from this. So the short circuit analysis shows the number of buses, number of branches, number of machines. So let us look at another report. Okay, here we have the short circuit report, and here we have pre-fault voltage is already selected of 11 kV voltage. So the 3-phase fault is as shown, and the line to ground fault is also as shown. And over here let me see, the bus voltage becomes 0, and the symmetric RMS value of current is 8.9 kilo amps. And the line to ground fault, here we have the A phase, which is faulted. This is single line to ground fault, and the symmetrical values of the current, unsymmetrical values of current I say, because current here is 9.3 kilo amps, and the zero sequence current is also 9.37 kilo amps. And looking from the bus, we have the impedance calculated with a 100 MVA base value. And clicking on the summary, we will generate the summary over here. And here also we have the 3-phase fault, the line to ground fault. So the 3-phase fault is 8.94 kilo amps, and the line to ground fault is 9.379 kilo amps. Line to line fault is 7.764, and line to ground, which is the double line to ground, is 9.226 kilo amps. So every value is in kilo amps. And over here we have this short circuit analysis conducted for 4 cycles, and here also we have this conducted for about 30 cycles. And the other 2 options below here are for arc flash analysis, which we will study later in this course. So this is how you conduct a short circuit analysis in ETAP. See you in the next lesson. In this section, we will learn to conduct an arc flash study in ETAP. Roughly 80% of accidents occurring in a substation or a power station are due to arc flash. So we will see what an arc flash is. So what is an arc flash? An arc flash is an electrical explosion resulting from a low impedance connection to ground or another voltage phase in an electrical system. High temperatures cause rapid heating of surrounding air and extreme pressures result in an arc blast. So this is what an arc flash would look like. The causes of arc flash. When significantly large fault currents are flowing through several conductors that are in close proximity of each other, the differences in potential among other factors will ionize the air, allowing a low resistance path between the conductors. And now we will see what sort of injuries can occur from an arc flash. The degree of injury is directly related to the power of the arc flash, the distance the person is at the time of the arc flash, and the protective equipment PPE worn by an individual during an arc flash. After conducting an arc flash study in ETAP, we will get the incident energy, that is the power of the arc flash, the PPE requirements according to the NFPA standards, which is the National Fire Protection Association standard, and the safe distance from the equipment. And these are the distances we have to keep from the exposed or energized conductor at all times. So there will be a restricted approach boundary, a limited approach boundary, or an arc flash boundary. So if anyone is working near a live equipment, then one have to consider the appropriate PPE requirements and also the distance from the equipment. So in ETAP we can also generate labels such as these in order to warn any personnel from getting too close with an equipment. So this displays the arc flash boundary limit, the incident energy, and the safe working distance. It also categorizes the arc flash according to the NFPA standards. So we have the limited approach boundary, restricted approach boundary, and the prohibited approach boundary. Next we will conduct an arc flash study in ETAP. In this lesson we will learn to conduct a arc flash study in ETAP. In order to conduct an arc flash study, we require protective elements such as relays and circuit breakers. So in my single line diagram we do not have any protective elements now. So in order to conduct the arc flash study, I will have to modify my single line diagram and include any of the protective elements. So let's start by modifying my single line diagram. What I am intending to do is to include a new branch over here and to conduct the arc flash study on that branch. So let me go to the edit mode and select my elements over here. This is the low voltage circuit breaker. I will be using this. And I will use this load over here. So let's start rating these elements over here. I will rate the transformer for secondary at 415 volts, and this will be 100 kVA transformer. And I will put all these typical values. Click on OK. And the load will be 50 kVA. And I will click on OK. So let me conduct a quick load flow study over here. So let me go to the load flow mode and conduct the load flow study. Okay, everything is fine. And next I will have to rate my circuit breaker. So my full load current is about 70 amps. So I will select the suitable circuit breaker from the library. So the rating page, go to the library. I will select Cutler hammer and I will select a model. So we have to select the suitable voltage rating also. So okay, this is fine. EGB, which is rated for 480 volts with a 3-pole, and I will select the 80 amps because the full load amp is 70, so I will rate it just above the full load amps. So I'll click on OK. Now we will go to the short circuit analysis mode, and at present I have my bus 3 faulted over here. I will unfault it. So then I will fault my bus 8 over here. So let me do this way. I will go here and put this to fault. Then I will click on OK. So my bus 8 is at fault now. So let me conduct my arc flash study now. So I will go to the run arc flash option over here. So this will ask you for a PPE approval because we need latest version of NFPA. So the following data comes across our single line diagram. So this is the arc flash boundary. Arc flash boundary is about 0.89 feet, and this is the incident energy. Incident energy is 0.43 calorie per centimeter square at 18 inches. So let me go to the display options and select further options over here. So the energy level and the fault clearing time in seconds, or I can change this to cycles. So I prefer to use seconds. And here we have, this is at level A, and the arc flash boundary, the incident energy and the fault clearing time is also shown over here. So next I will go to this edit study case over here, and I will go to the arc flash data. Arc flash data over here, and here I could approve the PPE levels. So at present it is put at 2012 NFPA standards. We might have even later standards, so I could edit this over here. So the PPE requirements, I could enter in user defined values for different incident energies over here. So according to NFPA 70E 2012, these are the categories or standards for different incident energies. So I don't want to change any of these. If you have the latest standards of NFPA 2014 or 2016, then we can edit these values over here to keep up with the standards. So I will approve these PPE values over here, then I will click on OK. So the next time you will not be notified. Even if you are notified, you will have to go to this option over here and approve this PPE. So I will click this over here, then I will click on OK. So next time it will not ask me for updating the PPE values. So another option of running arc flash analysis is using the insertion option over here. So after going to this insertion option and coming to this bus over here, or any of the buses over here, this turns to yellow color. That means this is active and can be used now. So after clicking on this bus 8, this shows that the protective element that is to be operated is this circuit breaker over here, and again all the data are populated alongside my single line diagram. So in order to generate labels, which I mentioned in my previous lesson, then I will have to go to this bus and double click on it. Then I will have this ratings page over here. So from the ratings page I will go to this data options in the shock protection. So click on this. Then at present it is put at NFPA 70E 2004 standards. So I will change this to 2012 standards, and if I have any user defined, I will put this at user defined values. So let me put this at 2012 and I will click on OK. Then I will load the typical data over here. So if we want to print any of these, so I will print this limited approach boundary over here. Then I will go to arc flash options. So the bus fault current is calculated using the short circuit analysis tool, and the bus arcing current and the protective device element, protective device arcing current, a fault clearing time, etc. are shown over here. If I want to change any of these or want to put values manually, I could do that using the user defined option over here. But I would like to use this calculated values, which is much easy. So the working distance, I could select any of these working distance depending upon my choice or the standard. Then I will use this option over here. I could print this in any size I want to. So I will print this in 3.5 into 7 standard. So after clicking on print, we have the label generated for me. So the arc flash boundary is 0.9 feet, the incident energy calculated is 0.4 calorie per centimeter square, and the working distance is 18 inches, and it has classified this to category 0. And all the other data is also populated alongside these values over here: the shock hazard voltage, limited approach, restricted approach, and the prohibited approach. And this also shows me the equipment, which is the bus 8. So let me close this and cancel that. Then let me show you the arc flash report analyzer. So the report analyzer shows me the total entire data over here. So the voltage level, total energy, arc flash boundary in feeds, the energy levels, and so on. So after running a number of arc flash studies, the total study report will be available over here. Or I could just go over here to this arc flash summary and generate the report like this. So this is how you conduct an arc flash study in ETAP, and see you in the next lesson. In this lesson we will learn to conduct a transient stability analysis in ETAP. So transient stability analysis is used to measure the tolerance of a power system to the disturbance, or how much disturbance a power system can withstand before becoming unstable. So ETAP provides the ability to conduct these studies. And to understand more about transient stability, I suggest studying the single machine infinite bus system and the swing equations and equilibrium area criteria. So you will get a better understanding about what results are we going to expect after conducting a transient stability analysis. So in ETAP we can simulate various disturbances and thus observe the system stability, and that is whether the system will be stable or unstable after the disturbance. So let me make a new project over here. So let us make a two machine system which is connected by a transmission line. I have already drawn my single line diagram, and we have two generators over here. This will be the generator at which I will be conducting the transient stability study, and this will be in the voltage control mode, and this will be in the swing mode. So let us begin by rating all of these components over here, starting with this generator. So let this be a 10 megawatt generator which is rated at 11 kV, and this is already in the voltage control mode. So then I will go to the impedance and the model, putting typical data over here and put a damping coefficient of 10. And then I will go to the inertia page over here. So this will be provided by your manufacturer, but all I know is that the total inertia is about 0.8. So in order to obtain the other values, I will start by putting values until this becomes 0.8 for my case. So this automatically updates the omega r square value, so which is a good thing. And all the other options, exciters, governors and PSS, harmonic, everything else I will put in default. So coming back to the capability curve, and I will now use the capability curve for my Q max limits, and I will be providing a power of 8 megawatts from these generators, and that's it. I will click on OK. And the other generator over here, I will start to rate this also. So let me begin with this. This is put in voltage control mode. They are always put in voltage control mode in default. So let me change this to swing. Then I will again rate this for 10 megawatts with 11 kV voltage, and again we will have to enter in these values over here. And click on OK. And for the transformer, this will be 110 to 11 kV with a 12.5 MVA, and the impedance will be the typical values, and click on OK. Similarly for here. And the transmission line, I will select the type of conductor from here. Let me go to the T&D book and select some conductor. Okay, this is good for me, and I will select the same. And next, the configuration. So this will be at a height of 50 feet, which is put at random for with 3 feet each other. This updates the geometrical mean distance. Everything else I will put on default and click on OK. And this load will be 6 MVA with 0.85 power factor, and this will be again 7 MVA with 90% power factor, and click on OK. To verify everything is in proper order, we will go to the load flow analysis and conduct a load flow study. So everything is good. Now let me go over to the Transient Stability Analysis mode over here from my mode toolbar, selecting the Transient Stability Analysis. In order to conduct a Transient Stability Analysis study, we need to generate a disturbance on the system. So we need to create a disturbance on the system, and for creating that disturbance, I will go to the edit study case over here, go to the events over here, then I will go to add event, and this event will take place at time 1 second, and the action that takes place is that the device type is bus and the device ID is bus. So we can change this to generator, and we can make different types of actions over here, such as we can create loss of excitation, droop and so on. So I will put this on bus to make it simple, and we will simulate a 3-phase fault on t equal to 1 second, and creating another event at time t equal to 1.1 seconds. I will just clear this fault over here. So we have a disturbance now, and then I will go to the plot option over here, and I will plot the generator 1 and all the bus voltages. So I will have to check all of these, and I will click on OK. Then I will go to run the transient stability option over here. And now we have these values populated alongside my generator. So this 21.3 degree is the rotor angle of the generator, 1.843 per unit is the excitation of the generator, and the speed of the generator is shown in RPM. And these are the percentage voltages and the frequency over here. And this also brings the transient stability time slider. So I will select the action list from here. So I have this action list which shows me the time in seconds and the event which will take place. So after sliding this to 1 second, I have the event Q1 happening, that is the 3-phase fault. Then after 1.1 seconds, I have the fault being cleared by my event 2. So let's see. Previously the rotor angle was at 21.2 degrees and post fault conditions is about 40.8 degrees. So this is oscillating about the previous value, that is 21.3. So in order to use this data graphically, we will go to the plot options over here. So select the generator 1 and the power angle relative. So I'll click on one of the options over here and click on OK. So this brings the generator relative power angle. So as shown before, the rotor angle was previously at some 23, and at 1 second the fault occurs. So the rotor angle now swings and this settles to the same value after a period of 5 seconds. So let us observe the bus voltage also. As you can see, for the bus voltage we have about 100% till 1 second, and the voltage reduces to 0 and again rises from here after 1.1 second. If we want to simulate the study for a longer period, we can go over here to the total simulation time and change this to 10 seconds or 15 seconds if I want to, and we can also change the simulation steps also and the plot time step also. So let me increase the simulation time and observe the graph now. So as you can see, the disturbance has caused the power oscillations for about 4 seconds after it has occurred. So at 1 till 5. And then we have the report generator over here. We can generate the complete reports from over here, such as the exciter, dynamic stability, complete report, action summary, and so on. So now we have seen a system which is stable. So going to this option over here and selecting the relative power angle, you see this system is stable system. So what happens for an unstable system, we will just see now. So I will turn off the damping over here, damping coefficient is 0, and we will again run this transient stability analysis. So let us see the relative power angle now. So now the system is not stable even after 10 seconds. So this is not a stable system. And we will go back and correct this, and I want to show you some more plots. So in order to activate more plots, I will have to go to this option over here, and the generator option, generator 2 is to be checked, and I will click on OK. and again run this calculations over here and to the plot options. Then I will check the absolute power angle over here. You see the absolute power angle is sync with each other. And let us see some more plots over here. Speed, current for the generator 1. So this is the generator speed. Generator speed increases and gradually reduces. And the generator terminal current. After the point of fault, the current increases sharply and oscillates and comes to the constant value over here. So this is how you run transient stability analysis in ETAP, and see you in the next lesson. In this section we will learn to conduct harmonic analysis in ETAP. So before conducting the harmonic analysis, I would like to discuss about the harmonic and its effect on the power system. So let's see what harmonics are. Harmonics are electric voltages and currents on the electric power system that can cause power quality problems. So harmonics is as old as the generator. So in a generator, since the field windings are not uniformly distributed, then they will create distortions in the voltage and current waveform. So the distortions at the point of the generation is very small, like about 1 to 2%. So let's see what causes harmonics. So mainly harmonics are created by electronic equipment besides the generator. Now with the nonlinear loads drawing in current in abrupt short pulses. So the short pulses causes distorted current waveforms, which in turn causes harmonic currents to flow back into other parts of the power system. So in case of loads, there are two classifications, that is the linear load and the nonlinear load. For linear load, the current drawn is proportional to the voltage. Loads like heaters, motors, etc. And in case of nonlinear loads, the current drawn is not proportional, that is disproportionate with the voltage, such as the static loads, power electronic loads, etc. These creates distortions, and this distortion superimpose on the fundamental frequency. So let's see the harmonics over here. So here we have the distorted current waveform over here, and this can be resolved into several sine waves over here. And this is the fundamental frequency at 50 Hz for a 50 Hz system, and the third harmonic will be 3 times the fundamental frequency, then it will become 150 Hz, and 5th harmonic, 7th harmonic, and the 9th harmonic. So in power system we are mostly concerned about these 3 harmonics over here, that is 3, 5 and 7, and we will neglect the 9, 10 and so on, 9, 11 and so on. This is because the magnitude of the 9th harmonic is very small compared to that of the 3rd, 5th and the 7th. So let us see what are the problems caused by harmonics. Overloading neutral conductors. So for a balanced 3-phase supply, there will be 0 neutral current flowing. So the neutral current is not very large, and in case of buildings having large amount of computers or large number of computers, SMPSs and other power electronic loads, then the third harmonic current will get added in the neutral, and as a result the neutral conductor will have to be very large to accommodate these harmonic currents. So mostly this would cause the overloading in the neutral conductors and also cause fires if the neutral conductors are not rated for this. And overheating of transformers. So in the case of transformers, we know that the no load losses are mainly due to the hysteresis loss and the eddy current loss. So the hysteresis loss is proportional to the frequency, whereas the eddy current loss is proportional to the square of the frequency, and this results in additional no load losses, and this also causes problems for motors as well, and nuisance stripping of breakers. All circuits contain capacitance and inductance. These will have one or more resonant frequency. So when any of the resonant frequency correspond to the harmonic frequency which is provided by the nonlinear load, then harmonic resonance can occur. And depending upon the circuit, if it is series circuit or a parallel circuit, this will result in voltage amplification or current multiplication. So this will cause nuisance stripping and also damages in the power system. Overloading in capacitor banks. So capacitor banks are usually rated to operate at the power frequency, and large amount of harmonics can cause overloading because the capacitive reactance is inversely proportional to the frequency. And so if the frequency increases, the capacitive reactance decreases, thereby acting as a sink. And then the skin effect. The skin effect is applicable to the cables as well as conductors, because the skin effect is directly proportional to the frequency. The skin depth is inversely proportional to the square root of the frequency. So greater the frequency means the skin depth will be small. So this will cause more losses. And then the total harmonic distortion, or the THD. This is a quantity which is used to measure the distortion in power system. So this is the ratio of the sum of powers of all the harmonic component to the power of the fundamental frequency. So I believe we have gone through most fundamental theory of harmonics. So let us enter into ETAP to conduct a harmonic analysis. In this lesson we will learn to conduct a harmonic analysis study. So the data from the harmonic analysis study is useful for filter designing. So in order to start with, I will add a nonlinear load to my existing single line diagram. And let me see, the static load over here, and I will connect it to my bus over here. Then I will rate this for 2 MVA, and the power factor will be at 85%. And I will come. Okay, before going anywhere else, I will go to the harmonic page over here. Then I will go to the library and select one current source. So I will select the fluorescent current source over here. We have the waveform and the spectrum over here. So I will select these. Then I will conduct a load flow study over here. So going to the load flow analysis. Okay, everything is fine. Then we will switch over to the harmonic analysis mode over here. And this appears over here. Just close this over here. Then let me run the harmonic analysis over here. It will ask for a file name. Then I will click on OK. Then go to the edit study case again and go to the plot options and plot my bus 3. Then the harmonic slider appears again, so I will close this and again run this and go to my display options. Okay, this is the fundamental harmonic, or the first harmonic, which is occurring at 60 Hz. So this is about 10.92 kilovolt, and the total harmonic distortion is given in percentage is about 0.78%. And when I slide the harmonic order, so this is the first harmonic, that is about 10.92, and there is no third harmonic, and the fifth harmonic is 0.07 kV, and this is the seventh harmonic. So since the harmonic value is below the specified limits, I will go and change the loading to make it more significant. I will go to the 10 MVA load and again running this Okay, this straightforward puts me in the critical window over here. So as you can see, all the buses are exceeding the harmonic levels over here. So the rating limits are 1.5, but these are operating about 2.91. And let me close this. And now the total harmonic distortion is 3.45%, and the third harmonic is absent, fifth harmonic is 0.31. Okay, now let's go to plot over here. Then I will select the waveform and the spectrum for the bus 3. So as you can see, the fifth order harmonic magnitude is about 2.8. So the magnitude is about 2.8, and here this is about 1.8. Seventh harmonic is about 1.8. So this is the distorted waveform over here. And next I want to show you is the frequency scan. So running the frequency scan, again we go to the alert window over here. Let me close this over here. So this system is operating at 60 Hz fundamental frequency. So 60 Hz fundamental frequency, we have about 0.79 ohm. That is the impedance towards this frequency. Now if I change the frequency over here, you can see the impedance value changes accordingly. And this is one of the reasons where the higher order harmonics have lower amplitudes. So we can have this over here. We can go to the plot options and go to the frequency scan. Then I will plot for the bus 3 over here. So this is the impedance angle. As you can see, the impedance angle, and over here this is the magnitude of the impedance towards the harmonic orders. So let me change this from the harmonic order to the frequency. So let me change this to the frequency. With respect to the frequency, I will go this over here and select this, select the bus device, OK. Then and this gives the angle with respect to the frequency. So as you can see in the magnitude plot, there is a reduction in the impedance at this frequency over here, which is about 4000 Hz. And as you can see right about here, we have low impedance, which is the impedance for the fundamental harmonic, and this is how you conduct a harmonic analysis in ETAP. And in the next lesson we will learn to size a harmonic filter to mitigate the problems caused by harmonics. In this lesson we will learn to size a harmonic filter in order to eliminate harmonics. So in order to select the harmonic filter, I will have to go over here, and here we have the harmonic filter. Selecting this, and I will connect this through a single throw switch over here. So we will be able to analyze the performance with and without the harmonic filter. So I will open the switch by double clicking on this and put this in open position. So in order to size a harmonic filter, we will need the data from the load flow. So going to the load flow analysis over here, then I will use the display options to display the kVA plus amp and the percentage power factor. Then conducting the load flow. So here we have the data Now double clicking on the harmonic filter over here, and this brings the filter editor window. Then going to the parameters. So the filter type that I'm using will be the single tuned filter type, and I will go to the size filter option over here. So the harmonic order which I want to eliminate is the 5th order harmonic. So I will put in the 5th order, and the fundamental harmonic current is about 503.1, and this filter has a capacitor with it, so I can use this for power factor correction. So I know the power factor is about 85% from the load flow, so my desired will be like 95%, and my total load in MVA is 9.186. So then I will go to the size filter option over here. Then I will substitute these values to here. So let's substitute this, and I will put the Q factor with some 0.9 value. Then the resistor will be 1. Let's put a small resistor value. Then I will click on OK. Then going to the harmonic analysis over here. Then let me conduct a harmonic load flow. So now the total harmonic distortion is about 3.45%. So let me close the harmonic filter and conduct the harmonic study over here. So now the THD value has reduced to 2.04 value, and you can see the 5th order harmonics has been reduced. So let's change our load values back to 2 MVA, and I will resize the filter again. So I need to run a load flow analysis over here, and I will keep this switch open during the load flow analysis. So the load now is reduced, and the current is also reduced over here. And again we will run the harmonic analysis without the filter over here. So the total harmonic distortion is about 0.78%, and we'll go to the plots to observe the spectrum. As you can see, this is in the frequency domain. Let me change this to the harmonic order. Okay, now we can see the harmonic order 5, and the magnitude is about 0.64. It's about 0.64. And let me close the switch over here, and I will again conduct the harmonic load flow over here. Now as you can see, the 5th order harmonic has been reduced significantly. So let me see. Now this value is about 0.58 or 0.56. So it has reduced from 0.64 to 0.56. So that's the improvement in the waveform. And this is how you conduct a harmonic analysis and tune a harmonic filter in order to mitigate harmonics in the power system. That's all for today's lesson. See you in the next lesson. In this lesson we will learn to conduct a motor acceleration analysis in ETAP. And this is an important tool because in many power systems and industries we have motors which are started with or without a starter, and this can have impact on our power system. So this studies enables us to view the impact and analyze the performance of the motor with and without the starter. So to begin with, I will open a new project and draw a single line diagram. So let me draw my single line diagram over here. So I have drawn my single line diagram. In ETAP you can perform AC motor acceleration analysis, and talking about AC motors, there are mainly two types of motors, that is the induction motor and the synchronous motor. And in the induction motor, depending upon the construction, there is the squirrel cage motor and the wound rotor motor. And in case of AC induction motors, we see that it works as a rotating transformer. So at rest, what we have is the short-circuited secondary. So what happens is that due to the short-circuited secondary, there will be a large inrush current in AC induction motors. However, this current reduces depending upon the slip value. So when the slip start to reduce, the short-circuit condition slowly start to diminish and become settled over time. So I will show you the relation in the lecture video if I am able to do the video. And the other motor is called a synchronous motor, and similar is the case in synchronous motor. There will be a starting current or inrush current during the starting period due to the slip over here. So keeping this in mind, we will perform our AC motor acceleration. So let's write the components for our single line diagram. So what I'm trying to draw over here is to simulate somewhat an industry. So in an industry, what we have here is a motor connected to the bus bar by means of a cable and a breaker. But for the sake of simplicity, I have simply connected this directly to the bus over here. So I have two induction motors and a synchronous motor. Now going to the ratings for every element. I will write the power grid for 11 kV. And the short circuit values will be infinite as possible. So that's done. Now for the transformer, I will use 11 kV to 415 volts 5 MVA transformer. And then for this induction motor, I will use, so when you go to the induction machine editor, go to the nameplate page over here. When you enter the horsepower, this asks for a typical nameplate data. So we have the NEC codes, the FR codes, and we can also select this from the library, but I will prefer to use the NEC codes. So according to the NEC codes, my current, power factor, efficiency will be calculated using these codes over here. So let me select the NEC code over here, and okay, everything else I will put in the default mode and click on OK. So this will be a 100 HP motor, and over here this will be a 200 HP motor. And this will be a 200 HP motor as well. So if you notice, in the induction machine editor on the nameplate, we can also choose the percentage slip for operation, the RPM, the number of poles, and so on. I am not going to edit any of these values. I will keep everything in the default values. Click on OK. And next I will write the cable over here. Double click on the cable. I will put a length of 10 feet and go to the physical parameters. Okay, go back to the info page, click on the library. Then I will pick one cable over here. I will put a 350 cable, and everything else I will keep on default values. Now to write my circuit breaker over here, so double clicking, go to the rating page. I had to pick a 200 amp circuit breaker. Okay, over here we have the 250 amp circuit breaker, so I will choose this, and the trip device will be the cutler hammer, and everything else I will keep the same, and I will click on OK. Now let me conduct a quick load flow analysis over here, so let's do that. Okay, so everything is fine as now. Now going to the motor acceleration analysis tab over here from the mode toolbar. Now as you can see on my right side, I have two analysis options over here. So we have the dynamic motor starting over here and the static motor starting over here. So the difference between the two is, in static motor starting you don't have to provide the dynamic model of the motors or the synchronous motors that you have used in the simulation. So what you will get is a steady state response. And going back to the dynamic motor start analysis, you will have to provide the load models, the motor models, motor equivalent circuits and so on, and the results you will get will be a dynamically varying one. You will better know it after I conduct my analysis. So for first we will conduct the static motor starting over here. So before conducting any of these, we will have to provide events so that these motors could be switched on and off at particular periods. So to do that, I will go to the edit study case option over here and go to the event over here, and I will add the event. So the event Q1 at time t1, I will turn on my motor 1, and at the event Q2 which will be at 2 seconds, and I will add my motor 2 over here. Then I will start this over here. The motor 2 will be started at 2 seconds, and again I will add my event 3, which will happen at time 3 second, and I will start the synchronous motor over here, and simulation time I will increase this to 6 seconds. Then I will click on OK, and let's run the static motor analysis. So static motor starting analysis, I will go over here and click on this. So let me put a file output, and now we have the motor starting time slider over here. So let me move this time slider to 1 second over here. So at the first second you can see the motor 1 has been started, and we have the load current for the motor 1. And as you go over here at 2 seconds, you can see this motor has been started, so we can see the load current over here. And at 3 seconds the synchronous motor is also started over here, so we can see the load current as here as well. So in static motor acceleration analysis, what you see is the steady state currents over here. So you can't get the inrush moments, and you can see the current reducing as the motor starts to pick up speed. So let us observe some of the bus voltages over here. So we will look at the bus 1 voltage over here. Now as you can see, in the first second we have a drop in voltage over here owing to starting the motor 1, and the voltage drop here is more because this time we are starting a 200 HP motor over here, and at the time 3 seconds we have started this synchronous motor over here. So this is the voltage profile during the starting of these 3 motors over here. And in the next lesson we will learn to conduct a dynamic motor acceleration analysis. In the previous lesson we learned to conduct a motor acceleration analysis in ETAP, and what we have done is to run a static motor acceleration analysis. So in this lesson we will learn to conduct a dynamic motor acceleration analysis, and as before I have said that in order to conduct the dynamic motor acceleration analysis we will have to provide the motor model, equivalent circuit, the load model and the inertia. So let us enter these values to these motors over here. So going to my motor 1, which is a 100 HP motor, then I will go to the model option over here, and we can either perform a parameter estimation like this. So in this case we cannot estimate the machine parameters. Okay, that's fine, but I am going to select a model from the library. So for a 100 HP motor I will select this, and I will update these values over here. And if you have the manufacturer data you can use that, but here I am going to use the library values over here. I will click on update, and now we have the equivalent circuit of the motor over here, all the values of the resistances and the reactances, and over here we have the torque slip Cara over here. And next I will go to the inertia page over here and enter the inertia values as well. Then I will go to the load page over here, then I will add a load model. I will go to the library to pick a load model. I will select this pump over here. So this fills the polynomial curve with the coefficients A1, A2, A3 and A0 over here. So this is the speed torque relation over here. I will click this on OK, and now we can see the torque speed Cara of the motor over here, and the torque speed Cara of the load will be always below that of motor. And going to the starting devices, at present I will not put any starting devices. So everything is done for this machine, and similarly I will do this for the other 2 machines. This is a 200 HP motor, so I will have to choose the library accordingly. So now I have modeled my motors depending upon the circuit parameters. The load model and the motor models are all updated. So now we can conduct the dynamic motor acceleration or the motor starting test over here. So previously we have given our events to turn on the motor 1 at 1 second, the motor 2 at 2 seconds and the synchronous motor at 3 seconds. So let us conduct this study over here. Okay, I will close this over here and let us observe. the motor starting timer slide over here. So at 1 second we have the inrush current for the motor 1 over here, and as you can see, this gets reduced with time when the motor starts to pick up speed, and you can see this has reduced significantly compared to what it was at 1 second. Now at 2 seconds we have the inrush current for the motor 2. Going back to this 3 second, you can see this has reduced, as well as this has also reduced. The inrush current for motor 1 and motor 2 have been reduced. Then you can see the inrush current for the synchronous motor as well, so this also gets reduced with time. Now let us go to some of the plot options over here. So let us observe the bus voltage. So now we get a dynamic curve of the voltage over here. We can see at which point what the voltage has become compared to the static, because in static we only had the load current values. We do not get the inrush current values and the variation of the inrush current with time. Now let us observe the motor parameters as well. I will go to the plots option over here, select the motor and compare the slip of motor 2 and the synchronous motor. And now we can see the slip performances of both these motors over here. And what I am interested is to look at the starting current of both the motors over here. So of these two motors, terminal current, I will also look at the line current and the speed as well. So the motor terminal current, this reaches to a peak of more than 600 amps of the, so this is about 600% of the full load current over here, and this reduces over here. And similar is the case of the synchronous motor as well. And this is the motor speeds. Since I am starting this from the 2 second, you can observe the motor speed reaching to its rated speed after 3 to 4 seconds. And this is the motor line current. This is similar to the motor terminal current that I explained before. And this is how you conduct a dynamic motor acceleration analysis in ETAP. And in the next lesson we will learn to introduce starters and variable frequency drives in order to limit the inrush current. So see you in the next lesson. In this lesson we will learn to use a starter for a motor and compare the performance of the motor with and without a starter. So we will look at the same motors and we will start one with the starter and one without the starter. So let us perform that with this 200 HP motor. So I will delete both these motors over here. These will be available in the system dumpster. I will copy this motor. Now I will use a starting device for the motor 4 over here, and to do that I will have to go to the starting device page over here and select a starting device. I will select the auto transformer, and after selecting the auto transformer we will have the control scheme window over here. So here we will have to provide our control scheme. Then I will change this to second, that is to vary the voltage with respect to time, because at present we are varying the voltage with respect to speed. So I will change this to seconds, and I will add more control schemes over here. So at the 0 second we have 65 percentage of voltage over here. Then at first second over here, I will change this to 80% of the voltage, and at the second 2 I will change this to 95% of the voltage. So now you see these are in steps, the voltage is varied in steps. I will change this to the ramp, so I will get a smooth transition from one voltage to the other. Okay, now we have a smooth transition from the 65% to the 95% over here, and at the third second we have the 100%. So I will click on OK, and now let us go to the motor acceleration analysis over here, and I will run the dynamic motor starting over here. So okay, I have forgot to add an event over here because we have not started the motor 2. So I will delete these events Q2 and Q3 over here, and I will add these events. I will start both the motors at once. And click on OK. The simulation time is set for 10 seconds. Then I will run the dynamic motor starting again. So the warning pops up that the motor voltage is currently at the under voltage condition. So let me close this and let us observe what the inrush currents are like for both these motors over here. Okay, as you can see, the inrush current has been reduced by a large margin over here. So we have about 50%, roughly 50% of decrease in the inrush current. As you can see, after time these both currents become the same. So let us observe the motor starting plots over here. We'll go to this motor over here, and I will check for the speed, current, line current, terminal current, and we will also look at the electrical power as well. So let us see that. So this is the motor terminal current for the motor 2 and the motor 4. So as you can see, the inrush current for the motor 4, which we used a starter for, has only an inrush current about 420% of the full load current, whereas for the motor 2 we have more than 600% of the full load current. But you can also observe that the time required for this motor 4 to reach the rated speed is more compared to the motor 2. So we'll close this option over here. Then I will look at the motor speed, and in the case of motor speed, this is what I explained to you before, that the motor 4 takes time in order to reach its rated speed, whereas the motor 2 reaches the rated speed quickly. So we'll close this, and the power demand. So the power demand, real power demand for the motor 1, the motor 2, will be greater during the starting period owing to the inrush current. And this is the motor line current. This is what I have explained before in the motor terminal current as well. So this is how you use a starter for induction motors in order to limit the inrush current. So this is a starter using the auto transformer over here. Similarly, you can use any of these starters for both the synchronous motor. For the synchronous motor, the starters will be different, but in the case of induction motor, we can use any of the starter elements over here. Then we can provide a control scheme, and we can thereby limit the inrush current accordingly. So in the next lesson, we will learn to provide a variable frequency drive in order to properly regulate the starting of an induction motor. So see you in the next lesson. In this lesson, we will learn to provide a variable frequency drive to an induction motor and to start the motor smoothly using the frequency drive. So in order to do the simulation, I will again copy this 200 HP motor and we will compare this with the motor 2 which does not have a starter and the motor 4 which has an auto transformer starter. So let me copy this motor over here. And we will go to the variable frequency drive option over here. So I will drop this from the variable frequency drive. I will add a bus over here. Now in order to provide the ratings for the variable frequency drive, I will have to obtain the data from the load flow. So let us conduct a load flow over here. Okay, now let us edit the variable frequency drive. Now this variable frequency drive editor pops up like this and we will go to the ratings page. Now we know the HP rating of the motor, that is 200 HP motor. Then the full load current is 237.5, which we have from the load flow analysis. And going to the loading, I will keep this at default. Then going to the variable frequency drive editor, and here we have the control scheme. And for the control scheme, I will use the V by F to be a fixed value of 8. So for every hertz change in the frequency, we will change a corresponding 8 volt. So the V by F will be 800. Now I will add in more over here. Okay, then at the first second I will have about 50% of my frequency, and the second second I will have 75% of my frequency, and at the third second I will have 90% of my frequency. And I will change this to ramp because I want a smooth transition from 50 to 75 and so on. And so we have the smooth slope over here, which varies the frequency with time. So I will click this on OK. Then I will connect my V by F drive to this bus over here. Then let us conduct the motor acceleration analysis. Let me go to the edit study case option over here. Then I will add this motor 6 and the action will be to start. And let us conduct the dynamic motor acceleration study over here. Okay, now it is started to show some error. We will have to reduce the simulation time step. Okay, we'll go over here, then increase the simulation time step. Click on OK, then again run this. Okay, now we will neglect these warnings over here because these are only for demonstration purposes. The system that I have drawn is only for demonstration purposes, because in the actual system we do not start all the motors at once. So what the problem it is shown here is that the motor voltage is always becoming in the under voltage for a period, As you can see, the motor 4 is becoming under voltage for the period 1.11 second, and the motor 6 is becoming under voltage for 0.3 seconds, and so on. So let us close this, and the motor time slider appears over here. So let me go to the 1 second, and now you can see the inrush current for various starters, and this motor 2 does not have any starter, so this is the inrush current, whereas for the motor 4 having the auto transformer starter, we have 663 amps of starting current, and for the V/F drive, this is the starting current. And now varying gradually, you can see the change in the currents drawn after the starting period. Now let us observe the motor starting plots over here. First I will observe the bus voltage over here. So let me choose the bus 1 over here, and I will click on OK. Because all the motors are being started at the same instant, we will have a significant drop in voltage. As you can see, we have come to 98% of the nominal voltage over here. So let me close this, and we will observe the motor plots over here. So I will choose these 3 options over here. We will also observe the slip while swell, and we will click on OK. And now we have the motor terminal currents for the 3 motors, and this is for the first motor, or the motor 2, which does not have a starter, which will have about more than 600% of the full load current during the inrush period. And over here we have the motor 4 having the auto transformer starter, and this has about 400% of the full load current during the inrush period. And for the motor 6 having the V/F drive, we have only the full load current across here during the starting period. So let me close this, and you can see the motor speed over here. Because I have not configured my V/F drive to operate at 100% of speed, which I will do afterwards, we can see these motors are reaching the rated speed at different time. Now, as before, our auto transformer starting motor takes more time in order to reach the rated speed, but our V/F drive starter takes less time than the motor without any starting elements. So this is the advantage of using a V/F drive. We can smoothly regulate the speed of the motor and also control the inrush current as well. So let me close this option, and similarly for the motor line current over here. And you see the motor slip quickly becomes the rated value for the motor 6 having the V/F drive, whereas for the motor 2 and the motor 4 this takes time. So let me edit my control scheme over here, and for the next second I will put in 100%. Now we will run this analysis again. Now let us compare the plots over here. And now you can see the motor terminal currents as before. So the V/F drive also reaches the rated motor terminal current after the starting period, but it starts very quickly. It does not take the inrush current of the motor 2 or the motor 4. And here you can see this is the biggest advantage of the V/F drive. You can see the motor has reached the rated speed faster than the motor having the auto transformer starter and the motor without the starter. And this is the motor line current, and this is the motor slip. As you can see, this takes 0 time, as you can say, because the slip becomes from 100% to less than 5% over here. It takes like 0 time over here, whereas for the motor 2 and the motor 4 it takes about 3 to 4 seconds, or maybe 5 seconds. So let me close this. And this is how you conduct a motor dynamic acceleration studies with a motor without a starter, with a starter, and by using a V/F drive or the variable frequency drive. So see you in the next lesson. In this section we will study more about ground grid systems or earth mat systems. So let us see what is the definition of an earth mat or a ground grid. So according to IEEE, a solid metallic plate or a system of closely spaced bare conductors that are connected to and often placed in shallow depths above a ground or elsewhere at the earth's surface in order to obtain an extra protective measure minimizing the danger of the exposure to high step or touch voltages in a critical operating area or places that are frequently used by people. So this is the IEEE definition for what an earth mat or a ground grid is. So basically a ground grid is a system of bare conductors that are buried below the earth's surface or above the earth's surface, which is used for protective purposes. So why we need earth grids or the earth mat? So the purpose is to prevent electric shock and to mitigate over voltages that can damage equipment. So in substations, high voltages line carry alternating currents which can induce voltages on conductors. So this means that the steel structures in and around live equipment will pose a shock hazard. Even when the fence is enclosing the substation will have induced voltages when high voltage transmission line passes overhead. So it is essential to ground all the above conductive structures to mitigate the shock hazard. And next we will discuss about what is the step potential. So step potential is the step voltage between the feet of a person standing near an energized ground object. So it is equal to the difference in voltage given by the voltage distribution curve between the 2 points at different distances from the electrode. So during a fault, a large voltage will be induced in all the other conductors in the substation. So if we are about to touch these conductors, we will have a shock because the fault current causes induced voltage on these equipments. Then there will be a ground potential rise, and because our 2 feet are at 2 points, then there will be a resistance between them or a potential difference between them. So this causes the step potential. And next is the touch potential. So touch potential is much simpler than the step potential. Touch potential is the touch voltage between the energized object and the feet of a person in contact with the object. So this is equal to the difference in voltage between the object and a point some distance away. So let me show this graphically. So the transmission tower will have induced currents flowing through it. So over my right side we have a person touching the transmission line. So this is the touch potential, or from here to here. That is the point from he is touching with his hand and to his feet at the ground. The voltage between these 2 points is called the touch potential. Whereas in the case of step potential, the step potential will have the induced current flowing from the tower to the person's feet, because these two feet are at different positions or different points, then the potential difference will cause a current to flow through the legs of the person. So as you can see, the touch potential is much severe than the step potential, because the path of the current is through the heart in the touch potential, whereas in the step potential the current path is only through the legs. So next we will look at the tolerable voltages. So the touch potential for a person having 50 kg weight is given by this equation over here, where Cs is the surface layer derating factor. This is the correction factor we use because in substations, in order to minimize this step potential, we usually place granite rocks or crushed rocks, and in order to correct the actual soil resistivity, we use this term over here, the correction factor, considering the effect of the crushed rock. And this is the step potential for a 50 kg person, and this Ts or the ρs is called the soil resistivity and is given in ohm meters, and the Ts is the maximum fault clearing time in seconds. Then the next term is the split factor. So not all the fault current will flow back to the earth. A portion of the earth fault current may have another return paths. As a result, the current gets divided at the point of fault, and some of the fault current would go through the overhead earth return cables, buried pipes, and earth conductors, and therefore the current division must be applied to account for the proportion of the fault current flowing back to the remote earth. So in many cases we consider split factor to be 100%. We consider that all the fault current is flowing to the earth, but in actual case there will be a split of the current, and some of the current will flow through the earth conductors and other part of the current will flow to the earth. So we are actually over engineering this so that we do not have any problems regarding our safety. And another factor is that the split factor is very difficult to calculate, and there are other regulations put forward by IEEE in order to calculate the split factor. So in our case and in many cases we use 100% of the split factor. And next is the ground potential rise. So the potential between the local earth and the site is considered to be zero at normal condition. However, when a fault occurs, the flow of current to the earth causes a potential gradient in and around the site. So the maximum potential difference between the site and the earth is known as the ground potential rise, or the GPR. So it is important to note that this is a maximum potential difference, that earth potential around the site will vary relative to this point. So during the period of fault, the potential in the site will increase compared to that of the local earth. So that potential is called the ground potential rise. And in order to verify our earth mat design, actually there are less methods concerned to how a earth mat should be designed. However, there are methods put forward by IEEE standards, but actually the thing to consider is whether the designed earth mat will have mesh voltages or the ground potential rise which is less than the step and touch voltage limits. We also take into consideration of the economic factors such as the price of the conductor and so on. And in ETAP you can perform earth mat design either by using the IEEE 80 standards or by the finite element method. In the finite element method, we will design the earth mat according to our specifications, and we can also plot the 3D graphs as well. So in the next lesson we will design the earth mat in ETAP. So see you in the next lesson. In this lesson we will learn to design the earth mat in ETAP. So I have already opened my single line diagram over here, and I will be designing the earth mat for the bus 3, which I will consider this as the substation in my case. So in order to design the earth mat, I will have to go to the elements toolbar and pick the ground grid from here. So let me pick this over here and place this over here. I'm going to drag this through my bus 3, and to make the view more and appealing, I will go to the symbols option and change the symbol to this. And next we will go to design the earth mat, and for that I will double click on the grid option over here. Then I will have the study model over here, which will be the IEEE method or the finite element method. So we will be doing our design in both these methods, that is the IEEE method and the finite element method. So for now I will use the IEEE method. So I will click this on OK, and we will enter into the ground grid system. So in the ground grid system, on this portion over here, what we have is the soil editor. So double clicking on this portion, I will get the soil editor, and from the soil editor we can edit the surface material, the top layer and the lower layer. So my surface material will be crushed rock, and my top layer will be moist soil, and my lower layer will be wet organic soil. And I will change the depth over here to 3 feet and clicking on OK. And next I will go to the edit mode over here, and in the edit mode on my right side I will have these toolbars over here. So this is the IEEE rectangular shape, IEEE T shape, IEEE L shape, and the IEEE triangular shape. I will use the rectangular shape over here. And on this portion we have the 3D graph of the drawing over here. So double clicking on this, I can choose the grid size. So let me put in 100 feet. This is for default condition, and the number of conductors I will keep this in the default, and the conductor type will be put in the default, the conductor size as well, and the cost also. And these factors will be changed according to the type of the conductor. And here we have the rods. This is also the same case as of that of conductors. One thing you will have to keep in mind is that the earth rods or the rods are used to dissipate the fault current, whereas the conductors are used to suppress the dangerous step and touch voltages. So I will click this on OK. Then going to the ground grid study option over here, I will click this on the study case, edit study case over here. So before that, let me fit this into page, and I will go to the edit study case over here. And as in the previous lecture, we have the options for calculation in 50 kilogram and 70 kilograms, and the ambient temperature is put at 70 degrees Celsius, and the method is IEEE 80. So I will update the number of conductors and rods depending upon the optimization. And over here the ground short circuit current is put at user specified. Okay, I will have to change this to short circuit study, which I will do after one cycle of analysis. And this is the fault durations over here, and as before, the split factor is 100%, and the projection factor is considered if my substation is subjected to future expansion. So if not, I will put in 100% over here. Then let me click this on OK. Then I will go to the optimized conductors option over here. Then create a output file name. Okay, Now this has already optimized my earth mat. As you can see, we have number of conductors in the X direction and 5 number of conductors in the Y direction. And we have a warning over here which we will look later. So the tolerable voltages are 980 and the step voltage is 3429. So the calculated is 882 and 1313, and the ground potential rise is 1546. So here I am having this warning which says that the grid depth is greater than 2.5 meters or less than 0.425 meters. So let me close this and I will go to I will double click on this and I will increase the depth of the conductors to a feet. Then let me conduct the study again. Okay, now everything is fine. Now we have conducted our study based on these values of the short circuit current, but actually we are having a different value, so we will go and change this back over here. So I have come back to my single line diagram, then I will go to the short circuit tab over here, and I will fault my bus 3. So bus 3 is faulted, then I will run my short circuit analysis. Then right click on my earth mat, then I will click on update fault kiloamps. Okay, now I will replace these values. Then again I will go to the ground grid system and go to the edge study case option over here, then use the short circuit study. So in the short circuit study, now I have the values from the short circuit. Then I will click this on OK. Then I will again conduct the optimized conductors option. Okay. Now we are getting a warning. This is because my earth mat is not having sufficient size. So I will have to increase the size of my earth mat. So the warning is over here. So let me close this. Then double click on this. I will change the size over here. And again, okay, now everything is fine. And over here we have the calculated volts which are well within the tolerable volts over here, and we have the optimal number of conductors and the optimal number of conductors in both directions. And I will go to the optimized conductors and rods option over here, and so the optimal number of rods is 4. So I will click this on close. And next what we can do is to go to the report manager over here. Then I can check out the results from here. We will look at the result. So the ground resistance in ohm is shown here, and the ground potential rise, the touch potential, step potential. So I will close this over here. Then I will go to the report generator, report manager. Then I will select the input data. Then I will view this. Okay, maximizing, and we have the system data. So the short circuit current and the fault durations are shown over here, and the weight, ambient temperature, and the soil data. The soil resistivities are also calculated by ETAP over here. The material constants, the type of the material, the conductivity, and so on. And we also have the cost per rod. So number of rods is 4 and the cost per rod is 100. And we also have the grid configurations, grid length, the number of conductors, and the cost in feet, and the total cost is also over here. So the total cost of the conductor as well as the total cost of the rod is also calculated in ETAP. So in economic and engineering point of view, this earth mat is sufficient for our system. And in the next lesson we will design the earth mat based on the finite element method. So see you in the next lecture. In the previous lesson we learned to design the earth mat based on IEEE method, and in this lesson we will learn to design the earth mat based on finite element method. So to do so, I will double click on the earth mat over here, then I will select the finite element method over here and click on OK. So now we will go into the ground grid system, and let me change this over here. This automatically updates the surface material resistivity and so on. Then I will click on OK. Then I will go to the edit mode over here, and in the edit mode on my right side, this time I will find several conductors, rods and some shapes. So I will select a shape over here, then let me resize the shape. I will change the grid size from here, and as before we can change the conductor depth, the size of the conductor, the type of the conductor, the cost of the conductor and so on. And I will put in some rods. Okay, then I will put in some conductors. So using the finite element method we can design any shapes we want to, because there is no restriction on the shape as in the IEEE standard. And we can place the conductors with unequal distances as well. I can also place this in several angles. Okay, let's try to simulate this. So I will go to the ground grid study option over here, then I will go to the edit study case, and now as you can see the method has been switched over to the finite element method, and now we do not have the optimization function over here and everything else. I have not updated my short circuit study, so I will put this in the user specified fault current. Then I will click on OK, and let me conduct the calculations over here. Okay, so after the calculations, this has found that the system is actually feasible because the tolerable volts are greater than the calculated volts. So in the finite element method, the advantage is that you can design any shapes you want. And let me go to the plot section over here. So I will plot the touch voltages, step voltages with the over voltage limits. And here we have, so the step potential profile is as shown over here. So the step potential is very less at these points over here and is very large at these red colors over here. I will close this. Then the touch potential profile. The touch potential profile is also shown over here. The touch potential is also somewhere around 100, 350 to 400 or 100 to 150, I suppose. And this is the absolute potential profile over here. So after conducting my analysis, we have found that everything is well within limits. So everything is well within the limits. So let me close this option over here. Then we will go to the report generator and we will generate the input data. Okay, this time we have only used the user defined data, so the total fault current is 2 kiloamps, and we have the conductor data over here from what coordinates we are drawing and the length of the conductor and the cost per feet. We also will have the total cost over here. So let me go and update my fault current over here. Going to the single line diagram, then I will conduct the short circuit study and update this fault current. I'm sure this time this will not stay within the acceptable limits. So I will go to the edit study case, short circuit study. Okay. And now you can see which I suspected, that the maximum touch voltage exceeds the tolerable limits. And let us go to the plots option over here for the touch voltage alone. And now you see we have voltages in the range of 1600. So this is not a very good design, and we can change the shapes if I want to, but it's better to use the IEEE ET standard. We can only use this finite element method if we have any specific requirements. Either way, you can design the ground grid using the IEEE ET method or the finite element method. It actually depends upon the project you are working on. So this is how you conduct a earth mat design using the finite element method in ETAP, and see you in the next lesson. In this section, we will learn to perform a cable pulling calculation in ETAP. So before approaching ETAP, we should know the basics of cable pulling and the expected results. People in the industry are much familiar with the process of cable pulling. So cable pulling literally means to pull the cable through a conduit. So if you are wondering why we should perform such calculations, because cable pulling is a delicate process as threading a needle. So in order to perform the correct cable pulling, we need to have the exact pulling tensions, otherwise we could damage the cable or get the cable jammed inside the conduit. So what is cable pulling? Cable pulling is the moving of lengths of cable from one place to another in order to install a connection of some type between the separate areas. And during the process of cable pulling, the engineer will have to consider different factors to compute the pulling tension so that the cable does not get stuck in the raceway or trench, or no damage occurred to the cable during the process. And we will go through some cable pulling terminologies. The cable clearance is the spacing between the cable and the conduit inner diameter. And the cable configurations. So for a 3 cable, there will be 2 configurations, which is the triangular and the cradle. So the type of the configuration selected will depend upon the percentage fill. So the percentage fill as shown here is given by this, which is the inside diameter of the conduit, and the dx is the 1.05 times the largest cable in the conduit. So if this value is less than 2.4, then we can use the triangular configuration. Whereas if this value is greater than 2.4, then we use the cradle configuration. So basically what this means is, if the conduit diameter is larger, we could go for a cradled configuration, whereas if the conduit diameter is small, we could go for the triangular configuration. And another configuration is the diamond configuration. So this is for a 4 cable pulling 4 cables through a conduit, and here the d by dx ratio should be less than 3. And next is the weight correction factor. So the weight correction factor is a variable that adjusts the sidewall bearing pressure caused by uneven weight distribution of single cables in a multiple cable pull. So during the cable pulling, we will consider the case of the weight of every cable. So if we are doing multiple cable pulls, then we should adjust the weight, and that is given by the weight correction factor. So the relative position of the multiple cable in the conduit produces a greater than normal force between the cables and the conduit that would exist for a single cable. So this can be viewed as an effective increase in the weight of the cable, and this depends upon the configuration in the conduit. So having multiple cables in the conduit can create a greater force between the cables. So as a result, you could have to use the weight correction factor in order to adjust the calculations. And these are the equations for the weight correction factor for various configurations, for the triangular and for the cradled, where small d is the diameter of the cable, and the capital D is the diameter of the conduit. And the coefficient of friction. The coefficient of friction actually depends upon the conduit through which the cable pulling is done. So in practical applications, we would like to apply lubricants in bends so that the coefficient of friction through the bend can be reduced. And the jamming potential. So actually, in a cable pulling scenario, if the cable pulling tension is higher, then this would cause a greater sidewall bearing pressure, or if the pulling tension is too low, then it could result in a jamming potential, or it could cause the cable to jam. So there is a greater chance of getting the cable jammed if the pulling tension is lower. So we use the following formula to determine the likelihood of jamming. So inner diameter of the conductor of the raceway and the outer diameter of the individual conductors are given by the capital D and small d respectively. The constant 1.05 factor is a reflection of the fact that bends are usually oval in the sectional view. So if the value of the jamming potential is less than 2.5, then we do not have a jamming problem. And if it is less than 3 but greater than 2.8, then jamming is possible. And if it is greater than 3, then you don't have a jamming problem. Then we will look at the sidewall pressure. So the sidewall pressure, the final step in cable pulling process, is determining whether the pulling tensions will compromise the conductor's sidewall bearing pressure limit. When you pull a cable or an individual conductor through a raceway bend or through a sheave, the sidewall bearing pressure develops between the cable or the conductor wall and the bend of the sheave. As I have mentioned several times throughout this lecture, that the cable tension, the cable pulling tension, is dependent on the sidewall pressure as well as the jamming ratio, or the case of jamming. So if you have too much tension on the cable, then this could affect the sidewall bearing pressure of the cable and the conduit and thereby damage the cable. And if we have very low tension on the cable, then this would potentially result in the jamming of the cable. So the cable pulling calculations are used to effectively optimize between these two tensions and get the cable pulled through the conduit without any damage to the conductor. So let me show you the sidewall bearing pressure over here, and over here we have a bend in the cable, and during the bend the cable will have a bending pressure over here. At this point the cable will be touching the inside of the conduit, and there will be a pressure applied onto the conduit. If this pressure is greater than that of the rated value for this cable, then we would have the insulation damaged. And now we have all the basics of cable pulling calculations, and let us go to ETAP to conduct a cable pulling calculation. In this lesson we will learn to conduct a cable pulling calculation in ETAP. So I am in the new project window over here in my new presentation. So let's draw a single line diagram. I will have a utility, a transformer, a cable, and then a load. And I will put in buses over here. And let me connect this. Okay, let me write the components in my single line diagram. This will be 11 kV utility or power grid with a maximum value of short circuit current, and that is modeled over here. Now for my transformer I will go to the rating page, then this will be 415 and this will be rated for 100 kVA transformer, and I will go to the impedance page and put in typical values over here. So my transformer is modeled, and I will model my load over here. So my load will be 50 kVA with 90% of power factor, and then I will write the cable. So I will double click on the cable. So the length of the cable will be 20 meters, and I will put in some 10% of tolerance. Then going to the library, I will have to pick a cable from the library. So I will select the cable having the frequency 60 Hz, aluminum, voltage will be 600 volt, and a 3-core cable. So I will have to select the size from over here. I will take this size for now, and I'll click on OK. Then let's conduct a quick load flow over here. So let me conduct the load flow study. Okay, everything is within the margins. Then we will go to the cable pulling system. On my left side I have this option over here, the cable pulling system. Then I will click on this, and we will go to the cable pulling systems over here. So I will maximize this window. So on this portion, when I double click on this portion, I have the type of the conduit over here. So the ID of the conduit is the conduit itself, and I can change the type of the conduit over here, and depending upon it the coefficient of friction will also change over there, and I can also change the size of the conduit over here and the outer diameter of the conduit. So the thickness is also shown over here. So the friction factor depends upon the number of segments and the number of bends. So at present I have put some 35 bends and 35 segments over here. If we are using more than 35 segments, then I will have to come here and edit this over here. So at present the percentage fill is 0 because we have not put any cables in the conduit for now. So let's do that first. So on my side over here, we have these options over here. This first option is the existing cable and the new cable. So I have already an existing cable in my single line diagram. So if I want to pick that cable, then I will have to go to the existing cable option over here and drop my cable in the conduit. So now this will ask which cable I want to pick in my single line diagram. Because I have only a cable in my single line diagram, I can only select this from the drop down menu. So I will click this on OK. And now you can see the percentage fill over here. So the percentage fill is 15.9. And now I could change the conduit size, and by changing the conduit size to 3, you can see the change in the percentage fill over here. So I will change this to the conduit size of 3 or 3.5. Okay, I will use the 3.5, and here we are. And if I want to put in a new cable, then I can use this option over here. And when I double click on the cable over here, I have the info page and the physical page. And in the physical page, I have the dimensions over here, the cable outer diameter and the kV size, etc. So the number of conductors, then the maximum tension. So the maximum pulling tension is 6 lbs per kcmil, and the sidewall pressure is 450 lbs per feet. And this is the weight of the cable over here. So this is a 3-core cable, and we have 3 cores over here. So I will click this on OK. And next what we need is a routing plan. I have already created a routing plan, so I will show you my routing plan. And this is my routing plan. So I have drawn this in AutoCAD Electrical, and this is my substation, the transformer bay and the cable bay over here. So I will be drawing the cable through a conduit to this control room over here. So this is the path of the conduit, and the distances of the conduit is shown over here. This is 2, 11.5, 3 and 2.5. So we will be pulling the cable through these bends over here. So this has 3 bends over here. So this is the routing plan, and we will be performing our calculations according to this routing plan. So let's go back to ETAP. So now we are back in ETAP, and we will continue with our cable pulling system. So first I will have to provide in more segments over here. So let's do that. And in order to add a new segment, I will go to the new segment option over here on my right side. Then I will click this several times, so I get a number of segments over here. So the first segment, the length will be 2 and the slope will be 0. And the second segment, the length will be 11.5, and the horizontal angle will be 90 degrees, and the bending radius will be 5. And for the third segment, this will be 3, and the horizontal angle will be minus 90 degrees, and again the bending radius will be 5. And for the fourth segment, this will be 2.25 in length, and will have a 90 degree horizontal angle with a bend radius of 5. And I will remove these segments over here. So I will click this and press on delete, again press on delete. So now we have our routing plan over here. So I can change the angle of view like this. So this is my x-axis, this is my y-axis. So as you can see, this is the cable bay, and from the cable bay I will pull my cable through in this conduit to my control room. If I double click on this portion over here, this keeps on rotating. So I double click again, it stops over here. And next we will go to the edit study case option over here, and we will look over here. So the 3 cable configuration is put at cradled or triangle. Since this is a 3-core cable, there is only a configuration. So there is no cradle configuration or triangle configuration, as this is only applicable to 3 cables. And the cable tolerance is also shown over here, the weight, the outside diameter, and the maximum allowable tension. And the maximum allowable tension has these reduction factors over here. These are actually the reflection of the weight correction factor, and the reduction factor tells us how much percentage we will have to reduce our maximum allowable tension. And this is for up to 3 cables, so I do not have any reduction factor over here. And this is the reduction factor for a single core cable, and this is the reduction factor for a 3-core cable. So since we are in the 3-core cable, there will be a reduction factor of 40% of the maximum allowable tension. And the reel to conduit. So the cable length that I will be drawing from the reel will be 20 meters. So I will have to convert this into feet. So that will be roughly 65 feet. So I will click this on OK. And now we have all the input data provided to my cable pulling system. And next we will have to perform the calculation. And in order to perform the calculation, I will go to this option over here, that is the calculate cable pull. So clicking on this, I will provide an output file name. And this is the result. So the maximum allowable pulling tension for this cable is 4501 lbs, and the equivalent length of the cable pulling of the reel, which is the one I have provided into it, and the total length of the pull is 42 feet. So let me close this option over here. Then I will go to the report manager over here, then going to the input data. So you will see, so the input parameters, the maximum allowable tension, the equivalent length of the cable, total length of the pull, and the total and the tolerance for the cable diameter, and everything is over here. And I can also go to the result. So now we have the length of all the segments over here. I have not provided any slopes, so the slope degree is 0. The length is provided in feet over here. So we have done all our calculations in feet, and we have the radius over here, which is also in feet, and the angle over here, and the sidewall pressure, the maximum tension in lbs, and the forward pull over here. So let me close this option over here, and we also have the forward pull and the reverse pull over here, and also the sidewall pressures at these points over here. Now we have conducted the cable pull calculation for a 3-core cable. So next I will do this for a single core cable, which will have 3 cables in the same conduit. In the previous lesson, we learned to calculate cable pulling tensions for a 3-core cable, and in this lesson we will do this for a single core cable, and this will have 3 conductors in a single conduit. And in order to do so, I will go to the cable over here and select a single core cable from the library. So over here I have this cable which has single core conductor and it's rated for 600 volts. So I will select this and pick a size of 250. And in the cable pull calculations, all the calculations are based on feet. So let me change this to feet over here, and I will put in a length of 25 feet. So if you are doing your actual calculations in meters, and if you are going to use ETAP, then if you have like 10 meters, then you have to change this to feet. Otherwise the calculations won't be perfect. And after your calculations, you can reconvert your results back to your metric units or any other units. So let me put this in feet, and I will click this on OK. Then I will go to the cable pull system over here, and I will pull my existing cable over here. So now we have a percentage fill of 25.8, and this is my previous routing plan in the previous lesson, and all these lengths are in feet as well. So let me calculate the cable pull over here, and before that let me show you some of the parameters over here. So the physical page, now you see the maximum tension of this cable is different from that we used in the previous lesson, and the sidewall pressure is also different, the weight as well. And okay, now let me calculate the cable pull. Okay, so this is the maximum allowable pulling tension over here, and this is the equivalent length of the cable pulled up from the reel and the total length of the pull. So over here we have the sidewall pressures at LBS, which is 3883, and previously this was like 2147. And let me close this. Depending upon your cable and your conduit, this can vary over here. The sidewall pressures can vary, and similarly the tensions of the forward pull and the reverse pull can also vary accordingly. And this is how you calculate cable pull in ETAP. Then see you in the next lesson. In this lesson we will learn to perform cable ampacity calculations in both above ground and underground systems in ETAP. So cable ampacity is defined as the maximum current in amperes that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. This is also explained as current carrying capacity. So what we understand from is that all the cables have some temperatures, a lower limit temperature and a higher limit temperature. So exceeding the temperature will result in insulation failure, or going below the temperature, that is going below the minimum rated temperature, can also cause insulation failure due to brittle insulation. In ETAP we can perform cable ampacity calculations for both above ground and underground systems, and this can be done in 2 ways. That is, one by using tables which are provided by the standards such as NEC, IEC and so on, and the other way is by using calculations. All the cables have particular value of ampacity which is provided by the manufacturer for a particular temperature. the cable ampacity will be derated because the cables are not installed having the ideal temperature. So there will be always a derating capacity or the derated ampacity of a cable, and it is required to calculate this derated ampacity so that we could properly select the cables for our use. Now let us move to ETAP to perform cable ampacity calculation using tables. Now I have drawn a single line diagram in ETAP, so let us start by rating these components in my single line diagram. And the transformer will be rated for a 110 bar 11 kV transformer, which is having a power rating of 12.5 MVA. And then we will go about rating the loads over here, lumbar loads. And my loads are rated for 1 MVA, 2 MVA, 3 MVA and 100 HP motor. Then let us go about rating the cables. The length of the cable will be 10 meters for every load. Let me pick a cable from the library. So I will pick this cable over here, which is rated for 60 Hz, copper 15 kV and has an insulation of rubber tube. This is a single core cable and at the size P2. All the cables shown here are sized according to the American wire gauge or AWG. So in many parts I have seen that cables are sized according to their cross-sectional area. So if you are using the cable sizing using the cross-sectional area, you might want to check out the conversion tables that are available on the internet. And over here we have the underground ampacity and the above ground ampacity. These are provided by the manufacturer and are the base ampacity values. So according to the manufacturer, the ambient temperature is 20 degree and the soil or the thermal resistivity of the soil is 90 degree and the core temperature is also 90 degree. The thermal resistivity is 90. So these are the parameters used for the underground ampacity calculation by the manufacturer, and similarly for the above ground ampacity and so on. So let me click this on OK and go about picking the cable for all the other loads as well. And now I have selected all my cables over here, and let me conduct a simple load flow over here. So everything is fine except for these under voltages. We will ignore the under voltage for now and go to the ampacity calculation. And double clicking on the cable here, we have the loading page over here. Let me go to the loading page, and in the loading page you can see over here the loading current for sizing. So over here we have three options, which is the operating current, the full load amp of the element, or we can put in user defined data. So now if I select this over here, we have several options to select from. So the full load amps of the element, I have the motor over here. So the full load amps of the motor is loaded over here. Because this option is not available for lump loads, so I can't use this option. We will have to either put in the user defined value for the current or put in the operating current from the load flow. So let us do that, and in order to do that, let us go to the load flow option over here, go to the edit study case, and we will update cable load amperes. So after that I will click on OK, then I will conduct the load flow again. And now when I go to the loading page and select on the operating current, now we have the operating current available for this cable, and similarly I will do the same for all the other cables as well. Now double clicking on the cable and going to the ampacity page, you can see over here the installation for ampacity. So at present I have a case that my cable must be a larger cable. So let me change the cable to a large one. And going back to the ampacity page again, and you can see the warning has gone now and the about try option is selected, and we have two standards for ampacity calculation using the table. So I can use the ICEA P54440 standard or the NEC standard. So let me choose the ICEA standard, and over here we can select the type of tie, that is the bottom cover or the top cover and so on. And over here we can see the derated ampacity already calculated for, and the temperature. So this is the base ampacity calculation temperature. We cannot change the base values, but we can change the operating values. So let me change the operating temperature of the ambient. So I will put in 40 over here, and now you can see the derated ampacity available according to the table using this standard. And if I change the standard, this will be different. So the base ampacity is from NEC tables and so on. And we also have the option of providing fire protection. We can put in the fire protection coating from the library. We have the manufacturer, flame master, and the material and so on. We can put in the fire stop, the fire wrap, and so on. Now let me change this from the above ground trace to the above ground conduit, and again we have different standard. Now we only have the NEC standard, so this is showing that the base ampacity is from NEC tables. And by putting in the temperature over here, we can get the derated ampacities from the tables. So if you notice over here we have three options. We have the derated ampacity calculated directly from the tables, or we can put in user-defined data. And we can also put in values from the underground system calculations, which we will do in the next lesson. And that's all for this lesson. See you in the next lesson. In the previous lesson, we performed cable ampacity calculation using tables in ETAP. So the tables were like NEC tables, ICEA tables, and so on. So in practical projects, you can only use these values for benchmarking, because in practical projects we will not use the duct bank or the duct sizes as specified in the tables. So in order to obtain the derated cable ampacity, we will have to perform cable ampacity calculations. So ETAP provides underground raceway systems which can be used to perform cable ampacity calculation in order to obtain the derated ampacities. So we have my single line diagram over here, which is the same as in the previous lecture. And I double click this one over here. So this is the derated ampacity as from the NEC tables. So in this case, let us see what will be the underground raceway system derated ampacity calculation. How I am planning to do is to put these three cables in a single duct bank and the cable 4 in the buried raceway system. So in order to perform cable ampacity calculation, let me go to the underground raceway system over here, and I will create a new presentation. And we have two modes over here, which is the underground raceway over here, and here we have the different options such as direct buried raceway, which is existing cable, new conduit, and so on. And when I double click over here, we have the underground raceway system UGS mode, which specifies the soil, the thermal resistivity of the soil, and the temperatures over here, the warning temperature, alarm temperature, and so on. Just click on OK. I will put everything in the default. Now let me put in a new duct bank over here. So I will click on the duct bank, and I can size it by simply dragging that over here, or I can double click on this over here and put in the width and the height, and change the type of aggregate, the thermal resistivity, and so on. So the default ID is over here, and we can also specify the distances from these two axes over here. So this is the X and Y axis. Okay, this X and Y. So let me click this on OK. Then I will put in new conduits. So this is the conduit. Double clicking on the conduit, I can put in 3 conduits like that, and I will arrange this. And when double clicking on the conduit, you can select the conduit ID, the horizontal vertical distance, the type of the conduit, size, outer diameter, thickness, and so on. Then I will put in my 3 existing cables from my single line diagram. So this will be cable 1, cable 2, and the cable 3. So we have these 3 cables over here. So let us continue with performing cable ampacity calculation. So when I go to the UGS mode, I have these options over here. So this is the steady state temperature, uniform ampacity calculation, uniform temperature calculations, cable sizing, and the transient temperature calculation. So let us perform the steady state temperature calculation. I will click this over here and put in a output file name, and let me observe the summary. So these are the sizes of the cables which I have provided in, and these are the ampacities of the current. This is the operating temperature. I will close this, and I forgot to show you, this is the edit study case, and in the edit study case we can observe we can use these 2 methods, that is the Neher-McGrath method or the IEC 60287, and over here we have the update option. I will show you this later. Everything I will put in default and click this on OK. So next what we have is the uniform ampacity calculation. So when I run the uniform ampacity calculation, we have the 2 cables in pink color. So To observe this, I will go to the summary report again. So you can see the cable 2 has reached the alarm temperature. The cable 1 is in the warning temperature. So in this case, what we have is here the temperature rise due to the current in cable 1 and cable 3 has produced a increase in the ambient temperature around the cable 2. So the cable 2 is having more temperature, or the ambient temperature across the cable 2 is higher as compared to the other two cables over here. So what we see is here, so the cable 3 has to be operated at this amount of ampacity so that the cable 2 will operate satisfactorily. So if we want to change the temperature limits, I can do that by double clicking over here. I will put in 98 degrees Celsius and again run the uniform ampacity calculation, and here you can see the ampacity has changed accordingly, so that now the cable 2 have to be limited at this amount of current ampacity, and in effect we will have to limit the cable 3 to this amount of ampacity, and so on. And in this case I want to put in the values I obtained from the uniform ampacity calculation into my single line diagram, and to do that I will go to the steady case. I will put in the currents from the ampacity calculation. I will check this box over here, click this on OK, and I will run the calculation again. And let me go to the ampacity page, the UGS. So this is already updated over here. I will change this back to 90 degree. Okay, I will run this again. Okay, then we have the uniform temperature ampacity calculation. When running the uniform temperature calculation, what we have is the maximum ampacity for these three cables over here. So every cable will be limited by the operating temperature of 90 degrees Celsius. So this is the limited ampacity. And next we have the cable sizing. The cable sizing is a very handy feature that ETAP provides you. You can size the cable accordingly. So when I press this on cable sizing, ETAP provides me with the optimal sizes of the cables over here. And if I want to update this to my single line diagram, I can do that by simply checking this over here and click this on OK. So you can see the cables have been sized accordingly, and so on. So, and the next thing what we will do is to perform transient temperature calculation. And in order to perform transient temperature calculation, you will have to provide in the transient load profile. So to do that, double click on the cable brings the cable editor. Go to the loading page over here. I have already put in the transient load profile. This is by simply putting in this add over here and putting in the values for the currents, and the time I have provided is in hours. So in any case, you don't want to provide the values from the cable sizing calculations or the ampacity calculation. You can simply tick these boxes over here so that this cable will be fixed at the size you mentioned regardless of the calculations for this particular cable. So I will click this on OK. Then I will run the transient temperature calculation. I have already put in values for the other cables as well. You can see this over here. And when I run this, I can select 3 of these conductors and I can observe the temperature with the hour with respect to the transient load profile. So I will click this on close. So my fourth cable, the cable number 4, is supposed to be put in a buried raceway, and in order to put that in the buried raceway, I will create a new presentation. I will put in my new direct buried raceway. I will put in a new location, and I will put an existing cable, which is cable number 4. And in order to make things more interesting, I will run a steam pipe close to it. So this is a heat source which is operating at 100 degrees Celsius, and I can perform the ampacity calculations. I can also perform the cable sizing calculation, and I can also put in my existing duct bank raceway. So my existing duct bank raceway is raceway number 4, so I will put this over here. And now you can perform the overall calculation at once. So this is how you perform cable ampacity calculation, cable sizing in underground raceway system using ETAP. So I hope you understood the lesson, and that's it for this lesson, and see you in the next lesson. In this section we will perform protective device coordination in ETAP, and before entering into the topic, I assume that you are well aware of various protective schemes, basics of power system protection and switchgears. So in this lecture we will be talking about relays and their terminologies associated with relays. So relays are the protective elements that are used in power system in order to detect the fault in the power system, and upon the detection of fault we provide the trip signals which are provided by the relay to the circuit breakers. So the circuit breaker then isolates the faulty part of the power system from the healthy part. Relays are classified depending upon their type, make, characteristics and more. So in this lesson we will be talking about 3 classifications, that will be type, make and characteristics. And depending upon the type, there are several relays such as the overcurrent relay, earth fault relay, directional relay, differential relay, distance relay, frequency relay, voltage relay, reverse power relay and so on. There are more classifications, and these are only the example of some types of relays. And depending upon their construction, we can also say that is depending upon their make. There are electromechanical relays, electronic relays, digital relays and the numeric relay. The numeric relay is the advanced relay that we have now. And before going into the next classification, I will be talking about the time current curves, TCC curves. So TCC curves gives the relationship between the current and the trip time, or the plug setting multiplier of the relay, and the time taken by the relay to trip. So I will explain later in this video. So depending upon the type, we can classify relays as definite time relay, the inverse definite minimum time, and in this the inverse definite minimum time we have various other classifications such as normally inverse, extremely inverse and so on. So this is the TCC graph. Over here we have the current or the multiples of plug setting, and over here we have the time. So the IDMT curve is as shown here. This is the very inverse IDMT and the extremely inverse IDMT. What this means is that as the fault current increases, when you see in the definite time, regardless of the current, the relay will trip at almost the same time for any fault. So even if the severity of the fault is very high, the time taken for the relay to trip is definite. So that is definite time relays. Then we have the inverse definite minimum time. The inverse definite minimum time has a curve like this. So in this case, when the severity of the fault increases, the time taken by the relay will be this. So when we compare the very inverse cara with the extremely inverse cara, we can see for the same amount of fault current or the same amount of current over here, we get smaller operating time, and for the very inverse curve we have a bit more operating time. So that is the difference between very inverse and extremely inverse and normally inverse. There are many curves such as normally inverse, short inverse, very inverse, extreme inverse, and so on inside the IDMT itself. Relay terms. So next we will be discussing some of the relay terminologies, and the first one is the pickup current. The pickup current is simply the current at which the relay begins to operate. So taking the analogy of electromechanical relays, we have two torques which are in opposite to each other, that is the deflecting torque and the controlling torque. The pickup current is that amount of current which causes the deflecting torque to just rise above the controlling torque. And the current setting, it is the current at which the relay should operate, which is given in percentages. So adjusting the number of turns in case of electromechanical relay, we can set the pickup current or adjust the current setting of the relay. And the next term we have is the plug setting multiplier. So the plug setting multiplier is the ratio of the fault current in the relay to its pickup current. And then we have the time setting multiplier. The time setting multiplier is the time delay setting of the relay. So this will be explained using the graph. So here we have again a TCC curve. So in the TCC curve you can see the various time multiplier setting. Here it is shown as TDS. So this is the time multiplier setting, and when we increase the time multiplier setting, you can see the time taken for operation will differ even if the same pickup is provided. So here you can see the time taken for the relay using this graph is only 0.3 seconds, whereas for a TMS of 1.1 we have the time taken for the operation to be greater than 3 seconds. So that is the difference when setting the time multiplier setting. And now we will discuss more about overcurrent relays. So overcurrent relay is one of the oldest form of power system protection that is still in use. So nowadays we have several sophisticated protective schemes, but still we have backup protection of overcurrent relay and earth fault relay. We either use the 3 overcurrent plus 1 earth fault or 2 overcurrent plus earth fault. And the overcurrent relay is also classified depending upon the characteristics. There is the definite time relay, the inverse definite minimum time, or the instantaneous. And comparing with the definite time and the IDMT, instantaneous have negligible time of operation, and I will show you this in the next lesson. So next we will be talking about protection coordination and why we require protection coordination, and this will be demonstrated in the next lesson. So here we have a radial system over here, and we have a fault at this point which is farthest from the source. So the fault is a 3-phase fault, and the coordination time interval or the CTI is 0.3 seconds. This value actually depends upon the industry standard or the code. It differs upon the IEC code and the NC code. And the pickup current is usually 1.25, and again this depends upon the code or the industry standard, or usually from the protection engineer's experience, and this is a general rule of thumb. So usually the pickup current will be 25% more than the load current and 0.6 times the fault current. So the relay should be able to differentiate between the load current and the fault current. And this is a table showing the inverse characteristic equations. This is according to the IEC standard, and according to the IEC standard the equations for the curves are shown here, and this is the standard inverse and the very inverse curve and the extremely inverse curve. So here you can see the time of operation is directly proportional to the time multiplier setting. So using the time multiplier setting we can adjust this, and it also depends upon the magnitude of the fault current as well. So here we will be following the IEC standard equations, and in order to perform the coordination, the first thing we have to see is that we always begin the coordination from our load end and not from the source end. So we must always keep this in mind, and we should classify our power system into different zones, and we have to assign protection to that zones beginning from the load end. So first we will choose the relay, and we put in a time multiplier setting of 0.025. No intentional delay is provided because R1 is not acting as a backup for any other relay. If we look over here, you can see what we are trying to coordinate is that when a fault occurs at this point over here, the relay R1 should operate. If the relay R1 fails to operate, the relay R2 should operate, and if the relay R2 fails to operate, R3 should operate, and so on. So we should provide enough time between these relays. So in this case, if R1 does not operate, R2 should operate. So R2 should be provided with enough time so that the fault, if cleared by R1, does not cause R2 to operate. So the time of operation for R2 will be greater than that of R1. So here we are coordinating the relay operation by setting the time grading. So the pickup current, let us assume a value of the pickup current, and for the fault on this section, again this is 500 amps. So the fault current is 500 amps, the pickup current is 160 amps. So what we are assuring is that the pickup current is in between the load current and the fault current. So we will calculate the plug setting multiplier, and from the fault current, the actual pickup current, this is the ratio of the fault current to the actual pickup current, that is 3.125. And using the TCC curve, we will calculate the operating time. We know the time setting multiplier that we have set over here, so the time of operation of the relay can be obtained from the IEC normal inverse equation. So the time of operation is 0.15 seconds. And for the case of R2, here the pickup will be a little more than that of R1, or we can actually put it at the same pickup values, and we calculate the plug setting multiplier, which is 2.99, and the expected operating time for the relay 2 is actually the operating time for the relay 1 and the coordination time interval. So this will be 0.45 seconds. So we will set the TMS from this equation. So we will substitute the time of operation and obtain the TMS for this relay. So we have the TMS for this relay, and we calculate the maximum fault current over here and the time of operation for the fault current as well. So the time of operation is 0.24 seconds. In a similar way, we have to coordinate the operation of the relay from the load end to the source end. And if you see over here, you can see we have provided a coordination time interval over here, so that if relay R1 does not act, and after a particular period of time, after that only relay 2 will operate. So this is the essence of protective device coordination, and in the next lesson we will go to ETAP to perform protective device coordination. And see you in the next lesson. In this lesson, we will perform protection coordination study in ETAP. So I have a single line diagram in ETAP over here. So we will be performing the protection coordination for the single line diagram using our current release. So to begin with, I will start the writing of these elements over here. And I will write the transformer. So the transformer will be 110 bar 11 kV, 12.5 MVA with the typical impedance values over here. And then we will start with the load over here. The load will be 70 amps. So that is it. And the cable, I will select a cable from here. And the cable length will be 10 meters, and go to the library and I will pick one cable. Okay, I will select this cable over here and I will select this size. So then go to the loading page. I will update the operating current as well, and the ampacity will be the derated ampacity. And then for the transmission line over here, this will be 1 mile length, and I will go to the conductor library and I will pick, okay, I will pick this one, which is a 250 size. So I will select this one, and as usual the earth wire will be the same, and this will be at a height of 30 feet, which is placed at 2 feet. So this updates the GMD, and I will go to the ampacity and use the derated ampacity. And then we will perform a simple load flow study over here. So load flow study. Okay, everything is good. Here we have 6.8 amps, 7 amps, 78.2 and 70.2. And let me go to the study case and I will update the cable load ampacities. Okay, then we will go to the short circuit study, and I am going to look at what the short circuit current over here is. So here we have 7.82 kilo amps. So this is the maximum fault current occurring at this bus. And in order to perform the protection coordination, you actually need protective devices such as circuit breakers. So ETAP provides you with fuses, contactors, high voltage circuit breakers and low voltage circuit breakers. Here we will be using the high voltage circuit breaker. So I will double click on the circuit breaker and I am going to place it here, here, here and over here. You actually need relays for this operation, and in order to sense the current you will require CTs. So go to the instrument toolbar over here and I will select the current transformer and I will place this here, here and over here. Then for the relay, ETAP has numerous relays: voltage relays, reverse power relay, frequency relay. We actually require for this simulation, you will require the overcurrent relay. There is also the solid state relay, which I will show you in the next lesson also. So go to the overcurrent relay and place it adjacent to the current transformer. And now we should write for our circuit breakers over here. Double click on the circuit breaker, and for this simulation or for this demonstration I will be using the ANSI standard. So go to the library. Okay, I will use the ABB manufacturer and 121 maximum kV. I will choose this one, and the same will be used over here as well. And for this circuit breaker I will select a different breaker, which is over here. Okay, this 15 kV max with the ABB manufacturer itself, and the same will be over here as well. and then we need to rate our CTs. So I will start with the CT over here. So the CT rating will be, I'm going to provide in 100:1 the CT ratio, and the burden will be say 50. Here too will be the same rating, 100:1, 50 VA. Over here we have 10:1 CTs. Again, burden will be 50. Here too I will use the same one. So one thing I want to specify is that all the ratings that I am using in this simulation or for this demonstration are not actually available by the manufacturer. I am not sure you will be able to use 10:1 CTs or 200:1 CTs. So you actually have CTs that are provided by the manufacturer for fixed CT ratios, such as 200:5 or 1000:1 or so on. So you will have to look at those in case of actual projects or practical projects. I plan on for doing a design project in ETAP. We will do that sometime later in this course. So next I will have to go to the relays. I will select the input tab over here. So the input tab, I have the CT already connected over here, so I don't require anything else for the input tab. And for the output tab, I will have to add a circuit breaker. So when this relay operates, I want this circuit breaker to be open. So I can select any of the elements of the relay. I can in particular select the phase element, the neutral element, the ground element, or anything else, but let me keep it simple. So any element of the relay provides trip signal to the circuit breaker, so this circuit breaker will be open. And similarly for these as well. So we have all our outputs configured, and then what we have to do is look at the overcurrent relay settings. So let me pick a relay from the library. So I will pick the Alstom P139, which is a Micom brand name. So Micom brand name, and this overcurrent or load protection for cables, lines, transformers and motors. You can select the relay depending upon the function like this, or you can just take it depending upon the protection type for the generator, transformer, bus or so on. So I will use the P139, and for now I will put everything in the default, and let us see. I'm going to select everything to be the P139. So I have selected all the P319s. So everything is set for this protection coordination, and then we will go to the protection coordination mode or the star mode. ETAP calls the protection coordination as the star mode. So here we are in the star protection device coordination, and here we have some of the options over here. This creates a star view. This is the star view manager. This runs or update the short circuit kiloamps, and the fault insertion. PD coordination is the protective device sequence of operation. So let us begin with the downstream or the load side. So actually when performing the protection coordination, you actually need to start from the downstream and gradually move up to the upstream. So first we have to operate this breaker, then this breaker, and so on. And I will select the entire single line diagram, and on the right side I have this option over here, protection zone viewer, and when I click on this option, this categorizes my protection elements into various zones. So for this single line diagram I have 3 zones, one involving the source and one involving the transformer and the other involving the zone. So I can create different star views. Star views are simply the time current curves. So I can create individual star view per zone, or create a single star view, or actually add it to another star view, and so on. So let me begin with creating individual star view per zone, and when I click on create, Etap provides me with the star view or the time current curves, and this is for the source. Over here we have 2 relays for the source and 2 breakers for the source, and this is for the relay 1 and this is for the relay 2. So these are the curves which I mentioned in the previous lecture. These are the time current curves of these relays, and in Etap you can perform protected device coordination by simply moving these up and down. So that's as easy as it can be. So, and when I double click on this relay, I actually get the overcurrent relay editor. So you can see this curve, this is over here the ANSI extremely inverse curve, and you can see here this is the instantaneous part of this curve. So for this demonstration I will turn off the instantaneous mode, so this will be more easier to explain and graphically more easy to understand. And for the ground also I am going to disable that. And let me close this. Here we have the relay 2 and the relay 3. So these are in protection zone for the transformer, and here you can see the damage curve of the transformer. So one thing you have to make sure is your relay characteristic always stay to the left side of this damage curve. So the relay operates before the damage curve is reached. So I'll close this, and this is for the lump load over here. So here we have the cable ampacity limits, you can see that over here, and I will close this as well. So for simplicity in understanding, I am going to turn this off, and every curve will be ANSI normally inverse. Except for the ground mode, which I will do that later. So now we have everything we need for our protection coordination study. So to begin with, I will put in a fault insertion. I will insert a fault at this bus over here, and I can observe the sequence of operation of the breakers. So you can see I have not coordinated any of my relays, so the sequence of operation is coming from the upstream. So this is a very bad coordination, because you actually need this circuit breaker to open first, then the circuit breaker, and you have to go from the downstream to the upstream breaker and not the other side. So let me simply go to the edit steady case option over here and go to the sequence of operation. So the fault type is 3-phase fault, and I'm going to flash 4 devices, and here we know that the ampacity or the amperes for required by the load is 70 amps. So while setting the overcurrent relay, I will select some additional percentage. So say here I am going to put in like 0.8, and if you look over here we have the pickup range. So in this relay we have two coils, so this is 4 times CT secondary, so I will use this curve. Here we have limited to 0.8, so from 0.01 to 0.8 amps. So my relay is 100:1, so I actually need 1 amps for the protection, so I will use the second coil over here, and I'm going to provide a pickup for 80 amps. So ETAP shows you the primary amps over here, and the time coordination I will perform this in the graph. So I will first arrange the pickup values, and this will be 0.9. okay, we'll put, okay, I'll change the, okay, 0.9. And over here we have the current. Let me see, the current is like 7 amps, so we have to look at that. And the current, okay, 1.26. okay, I have put in a value like 1.26, so maybe I should put in 1. okay, 10 amps will be the overcurrent protection, and over here we will put in 1.2 or so. So I'm going to check that everything is in the normal inverse. I have to make sure everything is in the normal inverse. Okay, and now let me select my entire single line diagram, and I am going to create a star view from this. So you can see the entire TCC curve for the entire single line diagram. I have the relays and everything over here. I want to show you the features of the star mode. So we have the zoom options, span options, and you can actually put in the single line diagram outside over here. And when clicking on this option, you can enlarge this. And so this is the damage curve of the transformer, this is the ampacity limit of the cable, this is the ampacity limit of the line, and this is the transformer 1 inrush current, the limit of the lump load. These are the relay curves, and on the right side we have the mode. We can put it in the ground mode or the phase mode. So now we are in the phase mode. We can zoom, and we can also use the crosshair in order to find the amps and the seconds of operation. And there are several other options as well. You can also plot a curve. It provides you the option to provide a new curve. So I don't want to provide a new curve, so let's close that, and let me close this. Okay, we have the also option for providing the grid. So this is the grid, and there is also several plot options: axis, general, legend, devices, and so on. So let me close this, and I am going to put in a fault at this bus. And as before, everything is in the same, so I am going to select my entire single line diagram and go to the star view. So now we have, let me keep my single line diagram out of the curve. So we have all the relay curves in the single line diagram, and this point is the point of fault. So let us actually coordinate between the operations of this relay. So my curve 4 or my relay 4 should be the first to trip. So I will bring up the relay 4 and I will bring up the relay 3. So how you perform protective device coordination from the TCC graph is to make sure your upstream breaker is always towards your right side. So the upstream breaker should be above every downstream breaker. So here the upstream breaker is relay 1 and this is relay 2. Okay, so now we have the relay 1, relay 2, relay 3, everything is in perfect order. Over here you can see when a fault occurs, the relay 4 will be the first to act, then relay 3 will act, relay 2 will act, and so on. You can actually turn in the settings from over here and you can observe the time difference between the two operations over here. So let me see, from this curve to this curve the coordination time interval is 0.195 seconds. So let us see if we actually perform the coordination. I will go back and then we will go to the fault insertion and provide a fault at this bus. And now you can see we have actually performed the protective device coordination. So you can see the first device to be operated is the CB4, then CB3, CB2, and then CB1. So let me go back again. I don't want to put in a large value of DMS, so I will bring these curves below over here. Okay, then let us check this out again. Okay, everything is good for this case when the bus 4 is faulted, and then we will perform the fault sequence insertion on this bus over here. This is the bus number 3, and when running the sequence, okay, here we have a miscoordination over here, so we will go to the TCC curve and observe. Okay, now let us observe again. So now I have adjusted all the TMS values for all the relays from the graph. As you can see, when I plot the graph, we have to remove this. Okay, when I plot the graph, we have these relays over here, and the protection coordination is working well for the phase element, and similarly we will have to do this for the ground element as well. So normally inverse pickup will be for 1 amp. Here this will be for 1 amp as well. Here this will be for 5 amps. Okay, let me put this for 10 amps. This will be for 12 amps, I suppose. We will put this for 12 amps. Okay, and go to the edit steady case option over here, go to the sequence of operation, and we will put it line to ground insertion. And when I run this, okay, here is again a miscoordination over here, so let us correct that. And to correct that, I will go to the star mode again, and from the star view I will change this to the ground mode. So now we are in the ground mode, and you can actually see any of the graphs over here. So I will go to the plot options, and I'm going to resize the current multiplier. So now we have 2 of the graphs over here. So let me bring this over here. So when we have a fault at this bus, you actually need the relay 4 to operate first. So we make the relay 4 operate first and the relay 3 operate later. So let me close this. The relay 2 and the relay 3 are not in the picture because the fault is from this end. So I will close this, and when I run the fault insertion again, you actually see these 2 circuit breakers are opening, and similarly in this case again we have a miscoordination, so we'll have to coordinate that also. So let me go over here, go to the plot options, to the axis, and rescale that. 2 graphs over here. I am going to select the 2 graphs, and I'm going to first drag this out of the way, and I'm going to pull this, the relay 2 has to be operated first, so the relay 2 will come down. So the upstream devices goes on the top and the downstream devices go on the below. So that is the basic idea when you are providing protection coordination by means of the TCC graph. And when I run the fault insertion again, you can see it's now perfect. So just to make sure everything goes well, we will do some more fault insertions. Okay, our fault insertion coordination was pretty good. Okay, you can also observe the sequence view over here. This shows the time and the operation of all these over here. You can also generate reports from over here, and this is how you perform protective device coordination in ETAP. So the protection device coordination is actually pretty difficult. This is a simple system, but with experience you can be quite good with it. So in the next lesson we will discuss more about the protection device coordination, and see you in the next lesson. In this lesson we will discuss more about protective device coordination in ETAP, and here we have my single line diagram over here. I have drawn a single line diagram of a distribution network. So here we have the high voltage part, or the voltage till this transformer over here is 11 kV, and over here we have 415 volts, and the protection devices used for this part over here, the high voltage system, is a high voltage breaker which is CB6, and a CT which is of the ratio 50:1, and we have a relay, overcurrent relay. The device number for the overcurrent relay is 50/51N, where 50 is the instantaneous element and 51 is the IDMT element, N is for the ground element. And towards my low voltage side over here, I have circuit breakers. These two are power circuit breakers over here. If you go over here, you can see these are power circuit breakers, power CBs. And here as well I am using power CBs because of the amount of current this has to handle. And here you can see I have provided cables over here. I have also sized my cable according to the load requirements over here. And here I have used circuit breakers again, and here I am using a fuse. So that is my single line diagram over here. So I will perform a load flow analysis to show you. And I have already provided the ampacity limits over here. I haven't changed the standard over here. So this is the default standard and the derated values over here. And now let us go to star mode, and first thing what I will do is I will fault this bus over here, and I will run and short circuit study. So what this does is that all the cables connected to this bus, when I double click on the bus and go to the protection over here, this updates the short circuit current over here. So that is done. I will remove that fault over here. Then I will select my entire single line diagram. Then I'm going to the protection zone viewer. So when I click on this over here, I have the various zones of protection: the bus 3, cable 1, which is this cable, the lump load, 2 of the lump loads, the motor load, 2 of the induction motors, the synchronous motor, the transformer, and the source. And I can also combine different zones to make a single zone by using this option, which is the extended to source option, or by simply dragging over here. But I don't want to do that. Then I will create individual star view per zone. So let me create individual star views. So this is the star view of the source end. So in protective device coordination, you always have to begin from the downstream or the load end. So let us. So these are all load ends over here. You can see this is the breaker rating, breaker curve. So let me minimize that, and again we have another load end. This is the fuse curve over here, and this is the protection of the cable, and this is the protection of the bus. Okay, so let me close all of these star views and then begin insertion of faults. I have already done this in advance, and I will make this file available for you in the resource. So let us begin with the fault insertion, and I will insert the fault at this bus over here. You can see the protective device coordination has worked well, and the first breaker to operate is CB1, then CB7, CB8 and CB6. It went from the downstream to the upstream breakers and there was no maloperation. So let me go to the sequence viewer. I will see the operation time over here. So the period of operation, for this circuit breaker 1 is somewhere around 1 millisecond to 14.8 millisecond. So this is less than 1 millisecond to 14 millisecond. So this occurred in the instantaneous period, and over here the period of operation is somewhere around 40 milliseconds to 60 milliseconds for this circuit breaker, and here 80 to 120, and this relay is operating which is less than 1043 millisecond, and this is overload phase, and this sends the trip signal to the circuit breaker. So tripped by relay to overload phase thermal, and again you can see this is the 51 element. The 51 element is the IDMT element, and the CB6 again you can see, and the other breakers are opening at very large periods over here. So let me close this and we can go to the star view over here. I will select these and I will go to the star view. So in the star view, CB1 circuit breaker, so this operates for somewhere around 1 millisecond to 40 milliseconds. So when you see over here, so this is the range of operation, so 1 millisecond to some 14 millisecond, and when you go to the upstream point over here, you can see the period of operation is 40 milliseconds, and again when you go upside, you have the period of operation is somewhat around 82 milliseconds, and this goes on like that. So let me show you the settings for these breakers. So this is the circuit breaker 1 is this, circuit breaker 7 is this, and this is the circuit breaker 8. And some more features which I wanted to show you. Print preview over here. So you have your print preview and you can print it from here. Let me close that, and you can also put in grids like this, and I'm going to change the plot options. I will change the major grid will be the same. The minor grid, I'm going to change the minor grid. Okay, you can make the graphs as you want them to. And you can also show the settings of these over here. So this is a Cutler hammer FI 160, the size is 150 amps, the thermal trip is fixed. So what this means is that the trip element is fixed over here, so I can't move the fixed trip element. So the only thing I can do is to change the circuit breaker here, but here I can change the trip element. So there are 3 portions for this graph. Here we have the instantaneous portion over here. Here we have the short time period portion, and this is the long time portion. And taking for this graph in instance, I have turned off the instantaneous, so there is no instantaneous. Let me show you that. So I have turned off the instantaneous. When I put the instantaneous part over here, we have the instantaneous, and this is the short period. I can change the short period curve over here, and this is the long period. I can also change the long period if I want to, but I am not going to change anything because as of now everything is perfect. So let me close this and show you the entire coordination. So in this case I have used a fuse instead of a circuit breaker. And let us fault this bus over here. So when I fault the bus number 3, the first breaker to open will be the circuit breaker 7, and it will go upstream like that. And for the bus 2, the circuit breaker 8 will be the first one to operate, then the circuit breaker 6, and then we will look at the line 2 ground faults as well. So the coordination is working perfectly. So the one thing I haven't considered in this single line diagram is that the protection for the motor. The motor requires special protection involving a circuit breaker and an overload relay as well. So that I will explain in the next lesson. So see you in the next lesson. In this lesson we will perform protective device coordination, and this will be the last lecture based on protective device coordination, and I want to stress on few points that would help you perform protective device coordination in ETAP. So I have already performed a protective device coordination on this system on the one line diagram in my presentation window over here. So the one line diagram consists of a power grid which is rated for 110 kV volts and uses a 2-winding transformer, and over here on bus 2 I have 11 kV volts, and at bus 3 I am having low voltage for 15 volts. And at this part at bus 2 I have used high voltage circuit breakers for protection, and at the low voltage side I have used low voltage circuit breakers. So to begin with, I want to explain to you the curve of a circuit breaker, a low voltage circuit breaker. So let us go to the TCC view of a circuit breaker over here. So this is the curve of a circuit breaker. This is a square D DG400 circuit breaker. So let me turn on the short time as well. So here I'm going to click on OK, and this is the curve of a circuit breaker. For this particular circuit breaker I am having the trip element such that I can actually vary the instantaneous short time and the long time part of the curve. So the instantaneous part is over here. So the instantaneous part usually refers to that the breaker should trip the circuit with no time. So you can see at these points of fault currents over here, the minimum tripping time is 0.01 seconds and the maximum is 0.04 seconds. This is like constant for all the currents which are beyond 1650 amps. And over here we have the short time curve, and in the short time curve you can see for this particular values, okay, the maximum limit is somewhere around 1350 amps. You can see the breaker actually takes some time to trip, which is usually from 0.02 seconds to somewhere around 0.06 seconds. And over here we have the long time part of the curve, and in the long time part of the curve you can see the breaker actually takes more time to trip, and you can see for this particular amount of current, that is 238.1 amps, it takes about 17 seconds to trip. So this is the circuit breaker curve. So let me turn off the short time. I have turned off it for my protected device coordination, so I will close this. And in case of other breakers, you will have breaker curves like these, and you can see the thermal element and the magnetic element, and it is actually fixed over here, so you can actually vary the curve So you can actually vary any part of this curve. So that's with these low voltage circuit breakers. And to begin with productive device coordination, you have to begin from the downstream end or the load side end. So first thing which you will want to do is to put in the pickup values for these relays, which is like 25% above the rated currents, and then you would want to run a short circuit on all the buses, and after that you will have to verify the zone of operation and go to the protection zone viewer, and then start with all the load side elements first. So in this case I am inserting a 3-phase fault on this bus, and you can see the protection device coordination is not working well. So what I have to do is I will select these 4 overcurrent relays and I will go to the star view over here. Okay, what we have here is the normalized star view. So in our case, this is the fault current over here. This is the 3-phase symmetric fault. You can see that we injected on the bus over there, which is 5.41 kilo amps at 11 kV volts. So this is my relay 1. All the curves are in IEC curves, and we also have turned on the instantaneous part as well. So let me show you the settings over here. So the CT ratio is 100:1, IEC normal inverse, pickup is 4 times the CT secondary, the time dial is 0.01, and all the other for the instantaneous part. Okay, then we are actually varying the pickup value and the TMS in order to perform the device coordination well. So let me go to the curve over here. So this is IEC normal inverse, and over here as well. Now this is NC normal inverse. So you actually need everything to be on the same curve, so that makes it more easy. I'm sorry, now we have the NC curves over here. So what I have to do is that my relay 1 is actually operating correctly, whereas my relay 3 and 4 are operating in the reverse order. So I will have to move the relay 4 upwards. So the relay 3 will be the one to operate, and the relay 4 will be the one to operate next. So I'm going to adjust the TMS values and the pickup values. Okay, and now you can see over here the relay 2 is also okay. Now that being done, you can see the relay 2 does not operate because the current, the pickup value is way beyond the relay 2. So what this means is that the entire current is being driven to the bus 4, and so the current to the bus 5 will be negligible. So the relay 2 will not operate in this sense. So let me run the coordination again. Okay, now we have the coordination which is working correctly, and then I will fault on this bus over here. Here too we are having the correct coordination now. So let us select these 3. I will also select this to show you the same. So you can see the relay is outside the fault portion over here. So relay 3, relay 4 over here, and the relay 2. So I'm going to reduce the pickup value. you actually need the downstream devices, which should be below the upstream device curves. So I have reduced the trip values over here, and let us run the coordination again. So let me look at the sequence of operations. So the relay 2 operates, and this is the instantaneous element. 50 is the instantaneous element, and for the relay 3, the 51 element, that is the overcurrent element, is tripped, and here the tripping signal is given to the circuit breaker number 4, and the relay 4 has acted based on the overcurrent element over here. 51 is the overcurrent element, and you can see we have the trip signal received from the relay 3, which is opening the circuit breaker number 5, and the circuit breaker number 7 is being tripped by the relay number 4 over here. Then afterwards we are having relay 1 circuit breakers operating, which is operating after a very large time interval, so we don't have to take this into consideration. So let me close this over here. Now let us observe the productive device coordination for the ground fault or the earth fault. So I will check this out. Okay, this is working correctly, and over here also this is working correctly. So let me go to the TCC curve. I will show you these three. Going to the ground mode, you can see the relay number 2 is the first one to operate. The relay number 3 is the next relay that would operate in this sequence, and the relay number 1 will be actually out of picture because it is not reaching its rated pickup. So in the case of earth fault or the ground fault, you actually set your overcurrent elements to be very small, so only one coil is available in this case, and the primary amps is 10 amps, and here too this will be like some 12 amps, and in this case, because the voltage level is different, you actually need to set for a lower amp, say 3 amps or 5 amps and so on. Now to go to the low voltage circuit breaker side, I have actually provided the protective device coordination by providing the overcurrent sizes of the circuit breakers. So let me show you that. So these are the currents which are flowing through here, and this breaker is rated for 150 and this is rated for say 200, and over here we have this breaker rated for 400. So let me show you. For the 3-phase fault, the operation over here. So first this CB1 breaker operates, then the CB6 breaker operates, and this all the way goes to the source end. So let me show you this in TCC. We'll select these 4 elements, and I'm going to the TCC curve. So over here you can see the relay 4 operates after this period. So the relay 4 operates at 0.275 seconds, and before that we have the circuit breaker 1 which operates over here, and then we have the circuit breaker number, let me see, the circuit breaker is circuit breaker number 6, and the circuit breaker number 2 is beyond the fault current, so this has not reached the pickup value over here. So when you select and put a fault at any of the buses, and Now when you create a TCC curve, it actually shows you the normalized TCC curve over here, and you can actually see the fault current and the period of operation. So let me show you the sequence of operations. So at this time, so these are the band limits over here, 0 to 10 milliseconds. So at 10 milliseconds the CB1 operates, and this is the fault current over here. And at 40 milliseconds the circuit breaker 6 operates, and at 276 milliseconds the relay number 4 operates, and the operating element is 51, which is the overcurrent element. And you can see the circuit breaker 7 is tripped at 326 milliseconds by the relay number 4. And here too we are having the similar one. So the circuit breaker 2, circuit breaker 6, and the circuit breaker number 7. And you can actually perform earth fault for this low voltage circuit breakers, because they do not have earth element or the ground element with them. They are only having overcurrent elements, so you can actually perform earth fault in this part over here. And now when you select the entire TCC, this gives the entire TCC. This is not a normalized curve over here. This is not the normalized curve. This gives the entire TCC over here. And in any case, if you want to print any of these TCC curves, you can do that by going to the print preview option over here. And over here we have the legend options. You can actually put in your name, the title name, the engineer name, the project title, location, contract. You can also put in logos of your company if you want to, and click on apply and OK. Then the legend will be filled over here, and when you print you can actually observe the legends as well. So this will be the last lecture based on protective device coordination, and in the next lecture onwards we discuss about various protective schemes. So that's all for this lecture. See you in the next lecture. In this section we will discuss about various protection schemes and how to implement these protection schemes in ETAP. And for this lesson we will be discussing about the differential protection. So this is the differential protection. The main philosophy of the differential protection is based on the Kirchhoff's current law, that is, the current entering is equivalent to the current outgoing. So using this as example over here, you can see the current being delivered by the generator will be equal to the sum of the currents being drawn by these two feeders over here. So if there is any unbalance between the currents that is incoming to this bus and outgoing from this bus, we can say there is a fault at the bus. So this is the main philosophy of the bus differential protection. So this is the relay over here. So any unbalance in incoming and outgoing currents can cause the relay to trip, and the device number for the differential relay is number 87. So let us go to ETAP in order to implement this differential protection in bus bar. Now we have entered into ETAP, and in this example, this is one of the previous example for protection coordination, and in this example we will be implementing the bus bar differential protection at bus number 3. So bus number 3 has 5 outgoing feeders over here and 1 incoming feeder over here. So let me conduct a load flow study over here. You can see there is about 900 amps coming into the bus number 3 over here, and all these 900 amps are being distributed to 5 different feeders. So all the currents over here will add up to about 899.3 amps. So why we implement bus bar protection is that if we have our feeder protection failure, in this case let this feeder fail under any circumstances, so what will happen is that this fault will act at this bus over here, so the bus will be damaged. So having a fault at the bus is considered to be more severe, because in the case of the feeder, this will only affect this feeder itself, but a fault at the bus will affect the entire power system over here. So the fault at bus number 3 will cause the failure to deliver power to all these feeders over here. So it is decided to have a faster protection for the bus, and therefore differential bus bar protection is preferred at substations. So let us create our schematic for the bus bar protection, and for that you will need CTs to be connected to all the outgoing feeders and the incoming feeder to the bus number 3. So let me do that first. And then to select our differential relay, which is over here in the instrument toolbar, the differential relay. I have selected the differential relay. And one thing you will have to keep in mind is that the total current from this part over here, that is the outgoing part of the bus number 3, should add up to this value of current. So in this case, if you have noticed this, you can see that all the directions of the CTs are in the same direction. So when I connect this in series, we will have the current adding up to the total value. But here too, when you observe here, the direction is similar to that of the outgoing feeder. So you will have to reverse the direction or reverse the polarity so that these 5 feeders add up and is being subtracted by this value of current, so that the differential current will be 0 in ideal case. So let me go to this CT over here, and I am going to reverse the polarity. Okay, now that is being done, the next thing we will have to keep in mind is about the CT ratios. Now when selecting the CT ratios, again you must keep in mind that all these currents should add up to the value, and that value of current should be available at the secondary of this CT in order for the differential protection to act ideally. So let me connect our CTs to our differential relay over here. So I have connected all of the differential relays terminals over here. So everything is being connected over here. Now let me go to the differential relay itself. So I will go to the DIF tab over here, and I am going to select the relay. I will select the Alstom CAG14. So this is a balanced restricted bus zone. So bus protection is also available here. This is a high impedance relay. We can also adjust the operation time over here, and the output, I am going to operate this circuit breaker over here. So that will be over here. So we can say that the protection coordination, before the protection coordination kicks in, the circuit breaker over here will act. And for the input, we have like 5 outgoing terminals and 1 incoming terminal, so that is about 6 terminals over here, and I'm going to select the IDs over here. So all the CTs are selected, but their current ratios are not being provided. Now let me provide in the CT ratios over here. So the CT ratios will be 100:1. For all the outgoing CTs over here. So So that being provided, now we will have to look at that. If you do the math, you can see that all these currents should add up to about 8.9 amps. So over here we have about 899 amps, so we will have to rate that accordingly. So this will be 1000:1. And now we have done all the CT ratios as well. So let me go to the differential relay. Okay, here you can see 1000:1, 100:1 CTs over here, and the output is also defined. We can also change in the time of operation over here. I'm not going to change that. And let me go to the star mode over here, and I'm going to put a fault on this bus over here. So you can see that the bus differential relay has operated, and the circuit breaker number 6 is the first to operate, regardless of the protection coordination that we have provided. So this differential relay will only work for this bus over here. So when there is a fault at any of the feeders, say over here, you can see that the bus differential protection will not work in this case. This is only limited to the bus over here. So this is how you can make a bus differential protection in ETAP, and in the next lesson we will look at providing differential protection for transformers. In this lesson we will learn to implement differential protection for a transformer, and here we will be implementing the differential protection on this transformer over here, which is a 12.5 MVA transformer, and the example is same as before, but I have changed the voltage levels over here. So here the transformer is a 110 bar 11 kV transformer with the full load amps at the primary being about 65.6, and at the secondary is 656.1 amps. And the philosophy of the differential protection is same for the transformer over here. Now when we look at the differential protection is considered as one of the most important protection for a transformer, because when a fault occurs at the transformer, you do not require any time lag or any time delay before the protection is to be operated. So let us go about implementing the differential protection over here. I already have an overcurrent relay set over here. So there is a CT as well. So for the secondary side I will require a CT, and we need circuit breakers for both on the primary as well as the secondary side. So I will go to the high voltage circuit breaker, and I will put in these two circuit breakers over here. So this will be okay for the 110 kV side, and for the 11 kV side I will pick this over here. So this is a 15 kV max, so that will be okay for that. And next we will go and fetch our differential relay, which is over here, and I will connect these CTs. And for the other primary CT, I can connect this from the overcurrent relay itself. So you don't need any other CT as well. So now all the connections are done. Then let me go to the differential relay or the differential tab, and again we will pick the Alstom differential relay, which is CAG14. I am going to select this relay over here. I am not going to change the operating time. The output, I will be operating two of the circuit breakers, so which is the primary side as well as the secondary side of the transformer. And for the input I am going to select these two CTs, and now we will assign the CT ratios for this CT. So the primary current is like 65 amps, so I'm going to select 100:1, and for the secondary side this is about 656 amps, so this I'm going to select 1000:1. So when you do the math, what you see is that we have both these currents same. So this is the secondary side, will have about 0.656 amps, and the secondary side of the CT over here will have 0.656 amps. Now one thing which I have overlooked is that we have not reversed the polarity. So now we have done all our connections, and it is time to verify our differential protection. So let me go to the star protection mode over here, and I'm going to fault at the transformer. So when there is a fault at the transformer, the differential relay will operate. So let me go to the sequence viewer over here, and at the sequence viewer you can see that our relay 4 is our differential relay. The CB10 and the CB11 is operating at 70 and 103 milliseconds, and beyond that period we can see that the relay 2 is operating, which is an overload relay. So this is a thermal element of our overcurrent relay. So C151 is the overcurrent relay. So the overcurrent relay is only operating afterwards. So this is how you implement differential protection for a transformer in ETAP. In this lesson we will talk about motor protection, as we know that motors are being used in industries nowadays. In fact, motors are the backbone of all the machinery that are in the industry as of today. So it is important that we provide some form of protection for the motors. So over here I have the motor curve, which is the DCC curve over here. As you can see from the curve, at the initial condition, that is at 100% of slip, the current drawn by the motor is likely 600%, then it's full load current. So at a particular instant this current reduces, and when the slip becomes like say to about 5% of slip, you can see that the full load current appears across the motor. So motors are somewhat different from that of your existing loads, lump loads, due to these characteristics. So when providing protection for induction motors, you have to consider this curve and assign your instantaneous overcurrent protections beyond this point over here. So let us go a little more further. In case of motors, we also need the thermal overload protection. So let us see what the thermal overload protection is. The thermal overload protection or overheating of the motor could lead to insulation failure and thereby damage of the winding. So it is recommended to have a proper motor thermal overload protection. The motor should be protected against the following conditions. So here we have the following conditions of the motor, that is the mechanical overloading and stalling of the motor shaft, low supply voltage, single phasing of supply mains, unbalancing of supply mains, sudden loss and rebuilding of supply voltage. So the main aim in case of motor protection is to provide the overload protection, and the thermal overload protection is provided by using a relay or any other mechanism such that the curve of the device will be in this region shown over here. So that is the main essence of the thermal overload protection. When the motor becomes overloaded, the motor could actually sustain certain amount of overloading, and if that amount of overloading exceeds the threshold value, you actually need to stop the motor from overloading or protect the motor from further overloading and prevent the thermal breakdown of the motor. So let us go to ETAP and see how we can implement motor protection. Here we are in ETAP, and as you can see, I have already made some of the protection schemes for the motors over here. I have made 4 different protection schemes, as you can see over here, whereas this protection scheme and this is the same. And so these are the 4 different protection schemes that I have implemented for motor protection. So all these motors are identical motors, which are 50 kilowatt motors, and over here you can see the different protection schemes. For the first protection scheme, I have used a motor relay. For the second, I have used an overload protection relay with a circuit breaker, and over here I have used a fuse, whereas in this case I have used a solid state trip relay. So let us go about explaining each of these protections over here. So first thing we have to look at is to get the starting curves for the motor. And in order to get the starting curves of the motor, you will have to double click on the motor, go to the protection tab over here, and you can see we have the starting curve with a constant terminal voltage, and you can also obtain the starting curve from the acceleration study, which is the dynamic acceleration study. You can conduct a dynamic acceleration study and use the value of the starting curve from the acceleration study, or you can use by simply providing these values over here. So when I check these boxes over here, I get the starting curve for different voltages over here, for 100% of voltage, 80% of voltage, and 110% of voltage. So you can plot different starting curves in the same graph itself. So the acceleration time will be provided by the manufacturer in the data sheet. For in this case, I am going to provide it the acceleration time of 1 second. So I have checked in the smooth corners over here, and I have also included starting devices on overload heating devices and equipment cable along with the starting curve over here. And you can see the asymmetric rotor current. I have given a asymmetric factor of 1.6. If the manufacturer provides in this data, you could select any values from about 1 to 2. The asymmetrical factor determines how much the locked rotor amperes will be from the symmetrical point over here. And next thing what we have here is the thermal limit curve. The thermal limit curve is actually the damage curve or the thermal damage curve of the motor. So we have 3 options over here. Hot start. So the hot start is usually used to refer to a motor that has been running for some time, so that the motor temperature is already at the rated temperature. And whereas in the cold start, we have the motor at the ambient temperature, and during its operation it reaches its rated temperature. So a motor which is already at the rated temperature will have lower thermal limits, whereas a motor that is just been started will have higher thermal limits. So that is the difference between the hot start and the cold start. These two are the thermal limits of the motor over here. So I can provide in the stall time. The stall time or the hot to cold ratio will be provided by your manufacturer. So this will be like 7 and 10. For my case, I'm going to tick in the hot start and the cold start. Actually, it is just enough to use the hot start itself, because you do not want your protection devices to be covering beyond the hot start point. For in this case, I will use all these values and the stator curve points. When I click on the points, you get the stator curve, and as a multiples of the full load amps or as in amps itself, I can add in additional values or insert or edit any of these values. This is also provided by the manufacturer itself. So those are the values that you will have to use in this case of motor protection. So let me close this And next thing which we will also have to consider is the cable protection. So when I go to the motor, I can use the cable. So this option gives a cable to be provided right before the motor, but I have directly connected to this bus. In your case, if you are connecting the motor to the bus by some means of a cable, then you will have to provide in the cable ampacities and the cable voltage drop in the machine itself. But for this example, I have used a cable that is connected between bus 1 and bus 2. So in this case, we will have to provide in the ampacity values and the protection in the cable editor itself. So I will have to change the cable in this case because I will have to use the above ground trace according to the ICA standards. So using this cable size will not calculate the ampacity. So let me go ahead and change the cable. I'm using XLPE cables, so let me choose this cable itself. So the rated voltage will be 1 kV itself is enough because our voltage is 0.415 kV. I am using this size because our ampacity calculation requires us to have at least a size of 1 bar O AWG. So I have the rated ampacity over here, so that's fine. And in the protection tab, this page is for the cable damage curve. So in order to obtain the short circuit currents, you will have to go to the star mode over here and fault this bus over here, and I'm going to run or update the short circuit KA, and let me do that. So now when we go to the cable over here, you get to go to the protection page and you can see that the short circuit values are updated over here. So that's it, and once that is being done, then next thing which we will have to do is go to the star view. So I am selecting the motor and the cable, and let us create a star view for the same. So here we are. So our cable damage curve is way beyond our motor starting curve, which is good, and you can see the motor starting curve over here. This is the asymmetric locked rotor current. So let us measure how much our asymmetrical rotor current is. So this is about 890 amps and the full load current is 91.7 amps. So as explained before, this is somewhere around roughly 600% of the full load amps. And here you can see we have the thermal limit curves over here. So these are the damage curves for the motor. The hot portion is over here and the cold portion is over here. Now let us enter into the protection scheme. So let me select the relay over here. So the relay which I have used is ABB REF 542 plus, and you can see the CT ratios. The output, I have configured it to open this contactor over here, and you can have both these elements over here. So here we have the 50 element, it's an instantaneous element. So we have both 50 element and the 51 element. 51 element is the overcurrent IDMT element, and we have the ground fault, etc. Beyond that we have the overload protection as well. So we have the thermal overload protection and the acceleration, the jam. The values for this will be set using the star mode. So we will set these values in the TCC. So we will see how we go about doing that. Now we will select the entire branch over here, including the relay with the cable and the motor. And when I go to create the star view, you can see this over here. So removing the contactor, and the cable damage curve is way beyond the motor starting curve, so I will remove the cable as well. So here we have the motor protection elements over here. This is the 51P element, so this is the overcurrent element, and I'm going to adjust this somewhere around here. So that's been done. Now you can see that this portion over here, which is the overload element, is way beyond the cold thermal curve, so I will have to bring that just about here. That will be before the hot damage curve. So that being done, then over here you can see the acceleration portion. I will have to adjust the acceleration portion over here, so that when we have a locked rotor condition, then the relay will pick up and operate the contactor over here. So start protection curve is also available, and over here we have the jam protection. So when we have a condition when the rotor is being in the jammed position, we need the relay to operate. So I am going to provide it as close to the starting curve over here, because beyond this portion you will have the stalling condition over here. So this is how I have configured my protection. So let us go back to the star mode, and I am going to insert a fault at this bus. So let us see. Okay, now this protection has worked well. So the next protection scheme we will be discussing is this over here, which involves a circuit breaker and an overload relay. So the overload relay is available over here in the toolbar as inline overload relay, and the device number is 49, whereas the motor protection relay is available in the instrument toolbar as the motor relay. So let us go to the star mode in order to analyze the curves for this protection scheme over here. So I am going to create a TCC, and in this case, as the motor damage curve is way beyond, I am going to delete this over here, and I have already set this protection scheme over here. As you can see, the combination of these two curves provides both the overcurrent protection as well as the overload protection. So let me show you which overload relay I have used. This is the Siemens 3UF7, and you can see the thermal element is there, and this type is a class 5 3-pole, and I have set the trip range which is based on the TCC graph. So I have turned off both the jam element as well as the ground element. If we want, you can use these two elements as well. So that being said, and the circuit breaker which I have used over here is an ABB 3-pole, and you can see the long time, short time and instantaneous pickup curves over here. So let me insert a fault, and you can see the circuit breaker operation over here. And the next protection scheme which I have used is the fuse over here, and this type of motor protection is used for very small motors and is not recommended for very large motors. For large motors, you actually need a motor relay or a overload protection in order to provide motor with sufficient protection, whereas in the case of fuse, you do not have the flexibility of varying the TCC curve of the fuse. So let us go about seeing the curves in the TCC view for the fuse, and as you can see, let me show you that the fuse rating is way beyond the thermal damage curve of the motor. So I will have to adjust this before the cold thermal curve. So this is the protection over here. So this type of protection is used for very small motors. Let me select the size. So this type of protection is used for very small motors and is not recommended for high power motors. So this is one type of protection over here. So the next protection scheme that I have used is by using a solid state trip relay. So the solid state trip relay is available in the instrument toolbar as MV solid state trip relay. So let me go to the library of the solid state relay, and at present we have only a single manufacturer, which is the Westinghouse, and we have two models, that is the Digitrip 3000 and the Digitrip MV. So let us go to the TCC curve to see the curves of this portion over here. So here you can see we can adjust these portions accordingly. So this is the flexibility of using a solid state relay over here. You can actually adjust the short time, the long time, and the instantaneous periods over here. So this is other method of providing motor protection by using solid state trip relays. And over here I already have this other branch for this type of protection over here. I want to show you that you can use the curve from a study as well in order to plot the curves. So I am going to turn off this starting curve, and I have the hot and cold, all the other thermal limit curves available. So let me go to the TCC portion of this graph. So here we are. So in this case we will have to adjust the overload element, or we actually do not need this overload relay. The protection provided by the circuit breaker is enough in order to provide the protection in this case. So this is how you provide motor protection in ETAP, and I will make this file available for download, and see you in the next lesson. In this lesson we will discuss about directional overcurrent relays and how to implement these directional overcurrent relays in ETAP. So directional overcurrent relays are necessary if we are providing protection coordination by means of the direction of the fault current. So the direction of the fault current has to be taken into consideration for the protection coordination. So I have the single line diagram on the screen right now, and over here I have made a simple substation. I have left out all the detailing, and for this example we will just use this portion as a substation, and we have two sources. We have the generator 1 and the generator 2, which is connected as feeders to this bus number 4 over here. So when I'll run the load flow, according to the load flow, both the sources are feeding to the bus over here, and when a fault occurs on any of these lines, say a fault occurs at this point, which is the midpoint between these two lines over here. So what happens is that this generator will feed to the fault through this portion over here, whereas the other generator will feed to the fault, where the fault current will go through this line, through the bus, and to the fault over here. So when a fault occurs at this point, I will show you the simulation. So what happens is that this operates and this operates as well. So we only need to isolate this portion over here, but what happens is that both our feeders are being isolated. So this is an unwanted condition. So what we can do here is to provide a directional overcurrent relay. So the direction of the relay will be such that when the current flows from the bus to the line, then only we need to operate this circuit breaker. As you can see in this case, that the current is flowing into the bus, and here we can see that the fault current is going out of the bus. So let us see how we can implement the directional relay over here. So double clicking on the relay, I am going to the overcurrent page over here. I have used Alstom P139, so I have this directional element already available in this relay. So I am going to tick on this portion over here, and when I click on the number 67, so the number 67 is the device number for the directional relay, and the direction is forward. I will explain this in a minute. And the maximum torque angle, or the MTA, is 45-degree lead. So the MTA that we can provide, or the maximum torque angle we can provide to a relay, is in the range of 30 to 60 degrees. So in most relays you have the option of selecting 30, 45 or 60. This actually depends upon the line impedance, and you can see the polarizing. We can choose the polarizing voltage. I'm going to click this on OK, and when I mentioned the direction, I am referring to this over here, this dot portion over here. When the current flows into the dot, we say that the direction is forward, and when the current is flowing into the non-dotted portion over here, we say that the current, or we say that it is in the reverse direction. So protection engineers have a convention such that the device to be protected should be put such that the CT's dotted portion should be away from this, or the non-dotted portion should be towards the device to be protected. So the dotted portion is what we refer to as the P1 portion, or the P1 terminal of. So this is done in order to avoid confusion between the forward and the reverse directions. So I can either put in the reverse direction. You can see that the current when flowing into the non-dotted portion over here. Then if we want to provide protection to this region, or when we want to look into this direction, we need to put the relay into reverse, or I can simply reverse the polarity of this relay. So let us stick to the conventions, and I am going to reverse the polarity of these two, and I'm going to turn on the directions for these two as well. So now let us see how we can discriminate between these two faults. I'm going to fault at this point over here, and you can see that this circuit breaker has operated, and only this circuit breaker has operated because now the current is flowing away from the bus. And you can see when this portion is isolated, we can use the other source in order to feed this load. And let me show on the other line as well. You can see that this circuit breaker has only operated and the other has not operated. So this is how you can implement directional overcurrent relays in ETAP, and I will see you in the next lesson. In this lesson we will discuss about voltage relays and how we can implement voltage relays in ETAP. So voltage relay is a particular relay which is designed such that when the voltage exceeds the set value, then we can operate any of the circuit breakers, or when the voltage is below a set value, then again it operates a certain circuit breaker. So the use of voltage relays is actually according to different regulations that is followed within different companies and in different standards. So let us see how we can implement a voltage relay in ETAP for this simple example. So the voltage relay device number is 27. So the under voltage element is 27, whereas the over voltage element is 59. So we actually need a PT, or a potential transformer, in order to connect a voltage relay over here. So now our voltage relay is connected over here, and when I double click on this, we get the voltage relay editor. And let me go to the settings page, and I am going to change. So different industry regulations or utilities prefer various levels of voltage tolerances. So some prefer 5% tolerance, whereas others prefer 7% tolerance. So it actually depends upon the industry and the standards followed. So in this case, I'm going to provide 105, so 105% of voltage, and the delay time is 1 second. No, I'm going to put it minimum, so we do not have to simulate it for a long time. And the circuit breaker CB1 will be open. And similarly for the under voltage setting, I'm going to provide these values. And in order to simulate this condition, we can't go to the star mode. Instead, we have to go to the transient stability analysis. And in the transient stability analysis, in the events page, you can see that I have created an event at time 1 second, and both these SPST switches are opening. So let us see the simulation over here. At 1 second, we have our SPST switches being open, and let us see. Okay, over here you can see that when the voltage exceeds 105%, you have the circuit breaker number 1, which is now opened. And similarly, I'm going to reverse the operation over here. So I'm going to close these two switches over here. So now after 1 second, both of these switches will be closed. So now let us see how the voltage element behaves. You can see that the voltage has reduced to 92.11%, and now the under voltage element has picked up and has operated the circuit breaker over here. So this is how you implement voltage relays in ETAP, and I will see you in the next lesson. In this lesson, we will discuss about frequency relays and how we can implement a frequency relay in ETAP. So this is the same example that I have used for the voltage relay, and the implementing of frequency relay is as simple as implementing the voltage relay. So what you need is the potential transformer, and I'm going to connect my potential transformer to the bus over here. The potential transformer ratio, usually we can provide the secondary voltage and gets updated automatically. So when you connect these to any of the buses, it provides the secondary voltage as 120 volts, and the ratio is appropriately selected over here. So the frequency relay is right over here. So the frequency relay device number 81. So I'm going to connect this device over here, and double clicking, I get the frequency relay editor. And in the setting page, similar to that of the voltage relay, I have this over here, and I'm going to reduce the time delay, and I can also set the under frequency. So I'm going to provide only a 2% tolerance in this case, but I have known of utilities providing 5% of tolerance, 6% of tolerance, and so on. So this actually depends upon the utility standards or the IEC or IEEE standards that you are following. So that is done. Now, similar to that of the voltage relay, you will have to go to the transient stability analysis, and here you can see this is the same event that I have used in the previous example, and let us see how this works. And at 1 second over here, you see that our SPST switches have opened over here, and you can see when the frequency was increased beyond 62 over here, can see that the circuit breaker has operated. So only 2% variance that I have provided using this relay. And this is how you can implement a frequency relay in ETAP. And one thing that I would like to mention about one of the previous example, you can see here I have a directional relay. So in practical applications, you require a voltage input into this relay in order to enable the directional element. And similarly for the reverse power relay also, you need a PT connection or a PT supply in order to work properly. But in this case you can see that ETAP everything is implemented by means of a software, and you can provide in the voltage source to this relay over here, but that's not going to make any difference in this case. So I would like to mention that point. So in practical applications, you actually need a potential transformer for the directional relay. And that's all for this lesson, and I will see you in the next lesson. In this lesson, we will discuss about the reverse power relay and how we can implement the reverse power relay in ETAP. So reverse power relay is a relay that is mostly used in generation stations when we have any problem with that of the generator. So when the turbine input is low or when the excitation failure occurs, then this generator would work as a motor. So this is highly undesirable, and so we'll have damage to the turbine and so on. So in this case we implement what is known as, or we use what is known as the reverse power relay. So the reverse power relay works by taking the PT supply and the CT supply. So we have both the CTs and the PTs in order to operate the reverse power relay. So this calculates the power flow, and when the power flow is in the positive direction, when the power flow is from the generator, then it does not operate. When it sees that the power is flowing towards the machine, so that now the machine will start to act as a motor, then this will operate and protect the machine. So we will see how you can implement the reverse power relay in ETAP. And here we have the reverse power relay. The device number is 32, and similar to that of the directional relay, the implementation in ETAP does not require to provide a PT supply to the reverse power relay. So in actual application you need a voltage supply as well for the reverse power relay to operate. So let us see what amount of power is flowing from the generator over here. So this is about 9 megawatts, and 518. So the CT ratio I am going to provide in 600:1. So we have the CT ratio over here, and device that will have to be operated. So we will have to provide the HVCB circuit breaker number 1, and the action will be to operate, and the setting. So we have two settings over here, which will be based on the real power that is being delivered, or the direction of the real power we can consider, or the reactive power we can consider the direction of the reactive power. So I will consider the direction of the real power, and I'm going to use the under power. So when there is a reduce in power of 9 megawatt, we can assume that the generator will be drawing from the grid and begin to act as a motor, or we can use the reactive power in order to determine this. So the setting will be 9 megawatts, okay, 9 megawatts, and the pickup will be at 90%, and the time delay is reduced so that we can actually simulate this for a short period of time. We do not want to simulate this for a long period of time. And we will go to this transient stability analysis. And for the other two examples of voltage relay and the frequency relay, I am going to operate these SPST switches at the instant 1. So let me at 1 second we have both of these switches opening over here, and you can see when the power from the generator was reduced, this relay assumed that now the power is flowing into the generator. So now this circuit breaker is open. And similarly you can use the reactive power setting as well. So when there is a change in the direction of the reactive power, you can say that generator is drawing power. And this is how you can implement a reverse power relay in ETAP. And we have now gone through all of these relays that are available in the instrument toolbar. That's all for this lesson, and I will see you in the next lesson. In this lesson we will discuss about the revision control, or what is called the rev control. Here you can see this over here. So we will discuss about how to make multiple revisions in existing projects, and how you can save these revisions, how you can merge these revisions into another revisions, and so on. So if we have a practical project, so I want to make certain revisions or any changes in the design, such as I want to change the percentage impedance of the transformer, the length of the cable, etc. So in this case I want to provide a revision. So ETAP provides the option to create multiple revisions. So that is provided by means of this tab over here. This is the revision control tab. So when I click on the revision control, I can create a new revision over here. So let me do that. So now the project revision control is created over here, and for my first revision I will create R1, which is the revision number 1, and I can create revision records based on short circuit updates and arc flash current updates. So at present I am only concerned about the load flow, so I am not going to tick any of these. And I can specify the change number, the group number, and I can also provide the authorization and the remarks. So in this case I am going to change the transformer 1 percentage impedance to 10%. So then I am going to click this on OK. Okay, now when I go over here to the revision data, so I have my base data over here. The base data is the one which I have already created over here in the presentation window over here. When I click this drop down, I get my revision 1 over here. So let me go over to my revision 1, and I am then going to change the percentage impedance of the transformer. So now I have changed the percentage impedance of the transformer, and I can run a load flow here, and let me go to my base revision over here, and again also run a load flow over here. So I can also merge into different revisions that I will show you over here. I am also going to create another revision over here, which I will use to change the cable length. So I am going to change the cable length over here. So let me go to my revision number 2 over here, and I am going to change the cable length. So the cable length has been changed over here. So I have created 2 revisions based on my base model over here. One is R1 and R2, and next thing I can do is I can merge 2 revisions together, so the changes in revision 1 and the changes in revision 2 will be reflected in the revision number 3 over here. So I can put this to revision 1. For revision 3, if I am creating another revision, so the data from the revision 2 will be copied over to the data in the revision 1. Also the data in the revision 1 will exist over there. So let me do that. So are you sure you want to mix the data? Yes. Okay, now when I go to revision 1, I can see that the transformer impedance is 10% and the cable length is 50 meters. So the both revisions are now present in the revision 1 itself. Also the revision control allows you to create multiple revisions, and if you are creating a revision, then it will copy the base revision and you will have to make changes to the base revision. And you can copy revisions, edit revisions, merge or delete revisions. So this is how you can use the revision control or the route control option in ETAP in order to create multiple revisions. You can compare different designs and so on. So that's all for this lesson, and I will see you in the next lesson. In this lesson we will look into the wizard toolbar and how we can utilize the wizard toolbar in order to batch run our projects. So the wizard toolbar is right over here on the left side. Over here you can see 3 of these. This is the scenario wizard, the study wizard and the project wizard. And the first we will go to the scenario wizard. So the scenario wizard is over here, and you can see we can create a new scenario over here. So the first scenario ID is scenario number 1. I can rename this if I want to, but I am going to leave it as it is, and I can add in remarks, and here you can see the parameters. So the system is from the network analysis over here, and the presentation is from our presentation OLV1. If we create multiple presentations, we can create different scenarios over here, and we can also select the different study modes over here. I'm going to select the load flow, and the study type is load flow, and we can create multiple revisions, and we can also create various scenarios using those revisions and the various switching configurations. And I can produce the output report to any of the files. I can provide the name of the file over here. So let us run this scenario over here. So you can see that the load flow has run in this screen over here, and then I can create another scenario. So in this scenario I am going to couple this circuit breaker over here, and I'm going to run the load flow. So I have the load flow over here on my screen. And for the next scenario, so let me click this on OK, and I'm going to perform a short circuit analysis, and I have already faulted this bus over here. So let me go to the scenario wizard, and I'm going to click on new. So now we are in the scenario number 3, and the study mode is short circuit, and see all fault 30 cycle the base revision, and first the switching configuration will be normal, and the output report is SC. So let me click this on run, and again let me put this in coupled and change the output report, and click this on run. Okay, so now we have 4 different scenarios over here, and we have the output file over here. You can see the SC was with the normal configuration, and the SC1 was with the coupled configuration over here. Similarly for the load flow, we will get the different file outputs. So this is the scenario wizard, and we can create multiple scenarios with it. So the next one is the study wizard. So when I click on the study wizard, we get a study macro. A study macro is something which executes a number of scenarios. So let me create a new study macro over here, and the scenario will be scenario 1. I'm going to add in the scenario number 2. So this will be a study macro, and when I run this, I get the scenario 1 and the scenario 2 have been executed simultaneously, and the last study results are shown on the screen. And let me create another macro over here, and the macro number will be macro 2, and I will create with the other two scenarios over here. And when I run this over here, I get the two short circuit scenarios over here. So this is how you can batch run different scenarios without having to do that tedious work of going to every tab and running and creating another output report. And the next one is the project wizard. So when I go to the project wizard, you can create a project over here. So this is the wizard number 1. A project wizard is usually used to run multiple macros. So I have already created 2 macros over here, and you can see the order over here and the study macro. So the first study macro is over here. This consists of both the load flow analysis, and the other study macro will be macro number 2. And you can also run in the macros of the scenarios from different projects along with this project. To do that, you will have to go to the add multiple over here, then go to the file of the path of the file, and you will have to browse in there and select the suitable macro. But I am not going to run this, so let me remove this over here. So we have the 2 macros, and now I am going to run these 2 macros over here. So both the macros have now been executed, and a total of 4 scenarios have been run, and you can get all the reports over here. So this is how you utilize the wizard toolbars in order to batch run your projects. So that's all for this lesson, and I will see you in the next lesson. In this section, we will be looking into DC power systems and the type of analysis that you can perform on DC power systems using ETAP. So the following analysis will be done in this section, which is the DC load flow analysis, DC short circuit analysis, DC arc flash analysis, and battery sizing calculations. So in this lesson, we will perform DC load flow analysis. So let us go to ETAP in order to conduct a DC load flow. So here we are in ETAP, and you can see that I have already made a single line diagram in here, and I also want to give you a brief introduction to panel systems over here. You can see that I have used a utility grid over here, and it is connected directly to a 3-phase 4-wire panel over here. So panels are used in distribution systems. So let me go and show you the panel over here. So the idea of the panel and the phase arrangement, you can use the phase arrangement as the phase sequence to be ABC or CBA, and you can also change the status over here. And in the ratings page, you can rate your panel and your voltage with the amps, the standards used, and the number of circuits that will be there. And you can also change the type of mounting, flush mounting or the surface mounting, and the feeding portion over here from right or left, and so on. And you can also change the standard of the enclosure, and we can also provide in the main disconnect. You can provide none and add a separate breaker, or you can just provide in a breaker over here and select a breaker from the library. And for the panel schedule, you can see here we have 12 circuits over here, and for this one I have put it as external. So let me show you what this is. And you can see here we have a single pole. We can change this to 3 pole, and we can provide to a 3-phase device. So you can also change the link from internal, spare, unusable, extension 3 and space. So when you put into the extension over here, you can connect different devices which are outside the panel over here. And if you are using the internal portion, you can select the type of load from over here. You can also choose the status, continuous or no continuous, and also you can provide in the rating values, the loading values, and also the protective devices that are used for this. So this is a 3-phase 4-wire panel, and from the 3-phase 4-wire panel you can connect it to a single phase 2-wire panel over here. And from the 2-wire panel I have connected to a 1 kilowatt load over here. So these are panel systems. Now let us go to the DC side over here. I have connected a charger over here, and let me rate the charger over here. So going to the charger, going to the ratings page, I can provide in the AC ratings or the DC ratings, and ETAP will automatically calculate all of the other values. So this will be 3.3 kilowatts for 110 volts over here. So the efficiency is 90%, so the AC rating will be 4.3 kVA. And everything else, okay. To the harmonic page, I'm going to provide in a certain harmonic, because chargers will have harmonics, as these are power electronic devices. And this is connected to a DC cable. The charger is available over here in the DC toolbar over here. You can see that the charger is over here, and the DC cable, everything DC is available from the DC toolbar. So the DC cable is over here, and we have the DC bus, and the DC bus has a DC circuit breaker, a DC cable, and the DC motor. Here we have a DC static load, and here we have a DC lump load, and here I have used a DC converter, so DC to DC converter, and is connected to a motor over here. The difference between AC load flow and the DC load flow is that in DC load flow there will be absence of the reactive element. So when we put the Q portion of the AC load flow equal to 0, then we get the DC load flow. So let me provide the ratings for all these over here. I have provided the ratings for the cables over here. Now let us go to the motor rating. This will be 1 HP motor, and let me go to the corresponding circuit breaker over here. I'm going to choose the Allen Bradley, so 15 amps is okay. I'm going to click this on OK, and again on OK. And over here the DC load will be again 1 kilowatt, 9 amps over here. For load amps is 9 amps. So the breaker will be having 15 amps again, and the DC lump load will be 2 kilowatts. So for load amps is 18 amps. Let me go to the fuse. Here I have used a fuse over here, so we'll have to select the suitable rating. So let me see. Okay, this fuse is good. I'm going to use this fuse over here, 30 amps. And over here I have the DC motor. This will be 2 HP. This will be operating at 50 volts. So the full load amps is 33.14. And going to the DC to DC converter, and This will be like 10 kilowatts with the output voltage of 50 volts, and the efficiency will be 98% because these converters tend to be highly efficient. So we have the full load amps over here, and the breaker, I am going to use a 100 amp breaker. So that breaker is also selected. And for the battery, let me go to the battery editor over here, and I'm going to go to the ratings page, and from the library I'm going to select the Excite over here. So Excite capacity of 50 ampere hours, so that is okay for me. And the number of cells, each cell has a voltage of 2.06, so my DC bus is having a voltage of 110 volts, so we will have about 55 cells. Okay, about 54 cells over here, and the number of strings will be 1 itself. And now we will go to the DC load flow option over here. So we have the DC load flow tab, and let me go to the DC load flow tab, and let me go to the steady case. So we have the DC steady case over here, the maximum number of iterations, the precision, also the voltage limits for the reports, and the loading. As in the case of AC load flow, we have different loading categories, and we also have PV array generation category. So the renewables will be discussed in another lesson. I will leave this for another lesson. So let me click this on OK, and now let me conduct the DC load flow over here. So you can see that the power flowing into this bus over here and is distributed among the various different DC loads. So let me go ahead and show the units over here. So the power flowing from the utility through the charger is about 3.19 kilowatts, and the power delivered by the battery is 2.294 kilowatts. And let me switch this over to amps. So you can see the amps flowing in from the utility and the amps flowing in from the battery, and the distribution of these over here you can see 7.8, 8.7, 18.7 and 33.1 amp. So this is how you can conduct a DC load flow analysis in ETAP, and in the next lesson we will look at how to conduct a DC short circuit analysis. So I will see you in the next lesson. In this lesson we will be performing DC short circuit studies as well as the DC arc flash studies. So I have my single line diagram over here, which is a slight modification of the single line diagram that is used in the previous lesson. So here I have added a UPS over here, and I also have an inverter over here. DC bus has a inverter and the AC system has a UPS with it. So let me go to the UPS over here, then let me show you the ratings over here. You have to provide in the AC rating, the DC rating, and also the loading for all the different loading categories, because when the UPS becomes a DC load, that is the UPS is supplying the power by means of this battery over here, you will have to provide the type of loading category. And over here we have the inverter, and similarly in the case of inverter we have the DC rating, the efficiency, AC rating. Also you have to provide in all the loading category values over here, and the DC generation values, these get updated from the AC generation values. So you can see over here sometimes it may ask you for this MPPT control of PV array system. So this inverter can also be used for grid integrated PV systems. So we will get into that in some later lessons. So let me click this on OK. Now I also want to show you how you could run AC load flow analysis in panel systems. So when I run the AC load flow over here, you can see that the power that is flowing over here is 16 amps. So let me turn this into power. So 12 kilowatts of power is flowing into the panel systems, but we do not know what amount of power is being distributed from this panel to another panels. In this case, we can say that beyond this charger unit we are having DC systems, so we could obtain the load flow, DC load flow, by conducting the DC load flow tool over here. But in this case, you can get the values of the load flow for the panel systems by going to the edit study case, and you have to tick this box over here which says calculate flows for single phase and panel systems. So afterwards, when I conduct the load flow over here, you can see that when I turn this on, here you have the results, panel and UPS systems. So you can have these values over here. Here you can see that this charger is a 3-phase charger, so I am having about 1.7 kilowatt in all the phases, and on this particular phase you can see that 6.56 kilowatt of power is flowing to this particular phase. Over here you can see that one of the phases is 8.26 kilowatt, 1.7 kilowatts are the power in the other two phases. And again, here this is a single phase panel over here, single phase 2-wire panel, and the power of 1 kilowatt is being drawn by this lump load over here, and the 5.56 kilowatts of power is flowing into the UPS. And now let me conduct the DC load flow over here, and this is the DC load flow. So in the DC load flow, you can see in the case of the UPS is now taken as a DC load. So about 5.278 kilowatts of power is flowing from the battery over here and going to the load over here. And over here you can see that our inverter is drawing about 1 kilowatts of power, and that's it. And now let us conduct the DC short circuit analysis. For that, you will have to go to this tab over here which says DC short circuit analysis, and after that on the right side you have these options over here. So first thing which I have to do is to select and fault the bus, which is the same for the AC fault analysis. So when I click on the run DC short circuit analysis, I have these values over here. So the fault level at this bus is 0.71 kiloamps. Now let me go ahead and fault the DC bus number 1, and the fault level is 0.8 kiloamps. Okay, now you can also generate different types of reports from this DC short circuit analysis. And let me go over to the edit study case, and from the edit study case you can change the charger contribution, battery contribution, short circuit contribution, etc. Now let us conduct an arc flash studies over here. So to perform the arc flash studies, this is already available in the DC short circuit analysis right below the run DC short circuit over here. So I have to fault one of the buses over here. So let me go ahead and flash this bus, and conducting the arc flash study we have. Okay, here you can see that this circuit breaker will be operating in the case of a fault at this bus. So this shows that, let me clear up this for you. Okay, this is a level A, and the arc flash boundary is 1.15 feet, and the incident energy is 0.71 calorie per centimeter square at 18 inches. And let me go over to this bus, and in this bus, in the DC arc flash parameters, I can change the parameters of the type of panel board or what the bus is enclosed in. So I can change that accordingly. We have different width heights and the reflectivity coefficients. You can also change the gap between different electrodes, the orientation. So the DC arc flash is over here, so you can disable the update or enable the update. This gets updated after the arc flash study is conducted. So this is how you perform DC arc flash analysis in ETAP. So in this lesson we have looked at conducting DC short circuit studies and arc flash studies, and in the next lesson we will look at how to perform DC battery sizing calculations. So that's all for this lesson. I will see you in the next lesson. In this lesson we will be performing battery sizing calculations in ETAP. So in power stations and substations we have an entire protection system which is dependent on DC power. So in power stations we have power electronic converters or rectifiers which is used to convert the AC power to DC power for the DC protection system. So in case of failure of the AC system or the failure of the power electronic converter, we provide a mode of backup for our protection system. So this is provided by means of batteries. So performing battery sizing calculations is important so that to ensure that the battery can provide the necessary voltage and also provide the power to the protection system or the critical load for a definite period of time. So in batteries we have two important parameters that have to be considered. So the first one is the voltage. The voltage depends upon the system voltage, and the ampere hour determines the duration for which the battery can provide power to the critical load. So in order to perform battery sizing calculations, we have to go to the battery discharge sizing option on the top over here, and I have already created a study case over here. Let me go to the edit study case option over here. So we have the info tab. So in the info tab we have the study case ID. So my study case ID is PS, and the battery, I can select the battery for which the calculations have to be performed and the load model, and this can be based on the type of elements or based on the duty cycle type. So I'm sticking on to the duty cycle type, and the calculation method will be based on the load flow calculation, and we will use the ampere hour curve interpolation with the fixed amps, and the duty cycle will be normal and the duration will depend upon the duty cycle span. And let me go over to the sizing option over here. So in the sizing option I can provide in the voltage requirements such as the maximum system voltage deviation, minimum system voltage deviation, and we can also provide in the battery charge voltage. So the charged cell will have about 2.3 volt per cell, and the minimum battery voltage will be 1.75 volts per cell. And we can use the sizes in the library as maximum or minimum range. We can also use this option, which is the desirable number of cells, and we have all the correction factors for the temperature, the aging compensation, the design margin, and so on. And in this tab over here we have the voltage drop calculation parameters. So we have the time in step which is per 1 minute, so this calculates the voltage drop per minute. So we have the duty cycle span options over here. So we have chosen the 1 minute span for the battery and the load. So this is the IEEE recommended standard for battery sizing calculations. What this means is that we can vary the load and the battery within a minute, and we also have the load duty cycle with no 1 minute span and the 1 minute span for the battery alone, but as this is the IEEE standard I will use this one. And we can also use different correction factors for the voltage drop calculation, and we can use the battery sizing capacity or the load duty cycle, the battery duty cycle only, and here you can also consider the temperature, the aging compensation, initial capacity, and so on. So let me click this on OK, and now let us go to our loads in order to provide the duty cycle over here. So going into the DC motor and to the duty cycle tab, you have this option over here. So in order to insert the duty cycle, we can use this add option over here and provide in the type of load, the name of and the percentage load or the amps. We can use the based on amps option and provide in the amps which calculates the percentage load, or we can provide the percentage load which in turn calculates the amps over here, and we can provide in the starting time and the duration. So these both are in seconds. So the duration over here is about 30 minutes and the start time is 0. And over here we have the random load. The non-random load is what we have planned for our design, and the random load is something we expect our system to cover as well. And similarly, we will provide in these values for all the DC static load, the DC lump loads, and our DC motor. So after providing all the duty cycle values over here, then we will go to the run battery sizing option on the top right corner over here. So after running this, you get the battery time slider over here, and also we have this values populated close to the battery. So the number of strings is 1 string, and we have to use the 5 plates per cell and the 100 amp hour battery. And we also have to use the 53 cells in series. So 53 cells in series will give us the required system voltage of 110 volts. Now, by varying the battery discharge time slider, we observe that the power being withdrawn from the battery. So you can see that after about 20 minutes the battery has 3.45 kilowatts of power, and after 30 minutes you can see that now the battery is providing about 2.3 kilowatts of power. So we can also go to the plot options over here, and I will plot the voltage and ampere of the battery over here. So you can see the amperes, and after 30 minutes the amperes get reduced to 0. So the battery can provide a backup period of 30 minutes. And over here you can see that the battery voltage is rising after 30 minutes. And you can also generate reports over here. You can select the summary report over here, and over here you have the nominal voltage, maximum system voltage deviation, and so on, the correction factors. So here the number of cells is 53, the number of string is 1, the rated voltage is 109.18, and the rated capacity is 100 amp hours. So this is how you can perform battery sizing calculations in ETAP. And in the next section we will discuss about renewables and HVDC links. So I will see you in the next lesson. In this section we will discuss about renewables, and in this particular lesson we will be talking about PV power or the solar photovoltaics. So let us go to the concepts. In this lesson we will discuss about various terminologies of the PV panels that are used, and we will also look at how to design a grid-tied PV system. And finally we will look at how to implement the grid-tied PV inverter in the ETAP environment. So here we will go through the basics. I am not going to explain about the basics of solar photovoltaics and how power is generated using photovoltaic effect and so on. Here we will discuss only about the terminologies that are used in the design aspect. So the standard test conditions are the test conditions that is used to rate a PV panel. So PV panels voltages, currents, the power and its efficiency are rated on the standard test conditions. So here we have the panel ratings over here. We have the VOC, which is called the open circuit voltage, the ISC short circuit current. So the voltage and the current are rated based on this test condition over here. And we also have the kilowatt peak or the watt peak, which is the power and peak, which is corresponding to the power that is generated during this test condition over here, and this is the efficiency. And then in the design we will discuss about how to design a grid-tied PV system. So the energy put into the grid is given by watt-hour PV, and the energy drawn from the utility or the grid is given by watt-hour load. So we will have different tariffs for the energy from the PV as well as the grid. So this is given by CPV and the C load. So in order for the net cost to be 0, then the energy which is to be provided by means of the PV system should be equivalent to this particular equation over here. So for the net cost is 0, that is we do not pay anything to the utility in this case. So the amount of energy that is required to be generated is given by WHPV. So next we will look at this example over here. At present I do not know the required amount of energy from the PV system, but I do know the load, which is 400 over here. So the energy is 400 kilowatt hour, and I do know the tariffs over here. So for simplicity I have kept this at the same values of $1 per kilowatt hour. So the net cost is 0 when the energy from the PV system is 400 kilowatt hour. So here we have the per day energy requirement from the PV system over here. So this is 400 by 30, that is equal to 13.4 kilowatt hour per day, and the peak rating of the PV system is given by this equation over here, that is kilowatt PV rating divided by HAT minimum. So the HAT minimum is called the minimum insolation level, which is given in kilowatt per meter square per day. This is also given in hours. So when we divide these two quantities, we get 13.4 divided by 4.2. This value depends upon the location of the installation and is available in the geographical tables as well. So the peak value of the PV system is about 3.19 kilowatt. So we have the peak power, and next we will have to compute the number of panels in series and the number of panels in parallel. So here we have a string. So in the string we get a number of panels in series, and the number of panels in parallel is the number of strings in parallel. So the number of parallel cells on the number of series cells is computed over here. So the number of panels in series is given by the voltage of the array divided by the open circuit voltage. So the voltage of the array is dependent on the voltage input of the inverter that is being used. So in this particular example I have used 1000 volts, and thus we get 35 panels in series. So in order to compute the number of panels in parallel, we will have to obtain the current from the array. So the current from the array is given by the power divided by 0.85 times the open circuit voltage of the entire array, which is given by this term over here, VOCT. So that is equal to 4.11, and the number of panels in parallel is given by the current of the entire array divided by the short circuit current. So that is about 0.47, and I have rounded all these values to the next closest integer. And so the total number of panels that will be required is about 35 panels. So 35 into 1, that's 35 panels. So the total area of installation. So the total area of installation is about 1.3 times the entire area of the panel. So the number of panels into the area of one panel gives the total area of the panel. The 30% additional is used to take care of the shadow effects and other effects, etc. And let us assume that the area of one panel is 1 meter square. So the total area is 1.3 times 35, that is 45 meter square. So sometimes in the design problem you will be given only the total area of installation, so you will have to determine the amount of energy you could produce by the particular given area. Now we will enter into ETAP and we will look at how to implement this in ETAP. So here we are in ETAP, and in ETAP I have already configured the single line diagram over here. We have two grid tied inverters over here, two grid tied PV inverters over here, and we also have a utility that is connected via a transformer over here. So the example values that is used over here is based on this Excel sheet over here. So from this Excel sheet you can see that the HAT minimum is obtained for 5.2 kilowatt per meter square per day, the area of the panel, the kilowatt hour load. So here the kilowatt hour load is 1000 kilowatts hours, and the tariff is the same, and you can see the energy per day requirement is 34 kilowatt hour, and the kilowatt peak rating of the PV system is 6.54 kilowatts. And here we have the same calculations. The voltage of the array, the number of panels in series is 31, the number of panels in parallel is 1. So the total number of panel is 35. I will provide this Excel sheet in the renewables. So let us go to ETAP over here, and in ETAP you can implement grid-tied inverters in two different ways. Here the inverter is inherent to this module over here, whereas here we will have to provide the inverter separately. So this is available from the AC toolbar over here. You can see here we have the PV array, and this PV array is similar to that of this PV array but as a separate inverter block over here. So this does not have an inherent inverter, so this is available in the DC toolbar as the PV array option over here. So this is the PV array over here. So we will have to connect this to a DC bus and then to an inverter over here. So let us go to the configurations over here. For the PV array editor, we will have the info tab, and we will also have the PV panel over here. So I have chosen the Qcells 230 watt panel. I have used these values for my calculations, so I have chosen this panel, and we will go to the PV array, and from the PV array we get the watt per panel is fixed, we cannot change this, and we get the number of panels in series. I have provided this 35 as from the Excel sheet values, and the number of panels in parallel is 1. So here you can see the PV array total values. So the number of panels is 35, the DC volts is about 1000 volts, the DC power is 8.025, and the DC amps is 7.82. And then we will have to go to the irradiance calculator over here. So this calculates the irradiance watts per meter square, and we will have to provide in our local time the date, etc. And by providing in the latitude and the longitude values over here, you get the irradiance over here. So we get the equation, the solar altitude, the solar azimuth, and so on, and you also get the irradiance. So at this particular time of the local time, so the irradiance is 297. So let me provide the noon time over here. So we'll have to put this in the AM. So we get this irradiance of 889. So I will update all these values over here, and you will get these values over here, and we have the MPPT of kilowatt hours. So you will have to check this box over here. This is the maximum power point tracker. This is an algorithm that is used to extract the maximum power from the PV system. So then we will have to go to the inverter tab over here, go to the inverter editor, and provide in the ratings for the DC, and correspondingly the AC ratings will be updated over here. And in the DC generation page, you will have this will get updated as per the irradiance calculations. So let me close this over here and click this on OK. So let me conduct a load flow without our grid-tied inverter systems over here. So you get the 6 kilowatt hours of power is flowing from the utility to our system. So 6 hours into the duration of 6 kilowatts into the duration gives us the energy requirement. So now let me close this system over here and let us run the load flow analysis. So you get the 6 kilowatts of power is flowing from our PV array over here, and this will be available for a period of 5.2 hours per day. So when you perform the calculations, you will get about 936 kilowatt hours of power for an entire month. And next we will do this using this PV array over here, and for this particular PV array you can provide number of panels in parallel as well. So the same number of panels are provided in series and in parallel, and let me provide in the latitude and the longitude values over here. I'm going to provide in the noon time 12 AM, and let me put this on calculate. So you have the air mass value and the irradiance values over here. I'm going to click on update all, and then I'm going to click on OK and go to the inverter, providing the ratings over here and here. And in this DC generation page, you will have to provide in these values of AC from the inverter itself. So I have already provided in 6 kilowatts of power in this case, and when I close this over here, you will get about the same kilowatts of power from this grid-tied PV as well. So this is how we can implement grid-tied PV systems over here. And let me show you something else. So in the PV panel, the ratings are already provided over here. So you get the VOC, the ISC, and the VMP and the IMP are the power at the maximum power point. So this is the maximum power point. So these values are this is the IMP value, this is the VMP values, and the fill factor is just a benchmark that is used to indicate the quality of the PV panel. So in this lesson we have gone through the basics of PV systems and the design of PV array, and we have also seen how to implement grid-tied PV systems in ETAP. So in the next lesson we will discuss about wind turbines, and I will see you in the next lesson. In this lesson we will discuss about implementing wind turbines in ETAP, and we will also look at a small design problem over here. And let us begin with, here are some of the basics of wind turbines. The power from a wind turbine is given by the following equation, which is equal to 1 by 2 rho A U cube Cp, where rho is the air density given in kilogram per meter cube, A is the swept area given in meter square, and U cube is the wind velocity given in meter per second, and Cp is the power coefficient. And let us look at what the power coefficient is. The power coefficient is given by this equation, which is P out by P in. So this is actually a term of efficiency, and this efficiency is given by the product of the blade aerodynamic efficiency, the mechanical efficiency, and the electrical efficiency. There is also complex equations involving the calculation of Cp. We will not go through that equation. So here you can see the blade aerodynamic efficiency. So the aerodynamic energy is first converted into the mechanical energy over here, which is then converted to the electrical energy. So the aerodynamic efficiency is 39%, and this is theoretically limited to 39%. And over here we have the mechanical efficiency, which is 96%, and the electrical efficiency is 0.94. So the power coefficient is given by the product of all these efficiencies, and it's about 35%. And next I want you to introduce to this term over here, which is the TSR, or the tip speed ratio. So the tip speed ratio is actually the speed at the tip of the turbine over here to the speed at the center or the hub. So the TSR determines the number of blades to be used, and this is actually a mechanical design over here. So next we will look at the various types of generators that are used for wind turbines, and these are within the ETAP environment itself. So the type 1 is an induction generator, the type 2 is also an induction generator, the type 3 is a voltage control method for induction generator, type 3 is MVAR control, type 4 is again voltage control. And we also have like PMSG generators that are used in wind turbines, but in this version of ETAP we do not have any more types available. So let us go through a simple design. So the design here I am explaining is the most simplest design and is not very sophisticated. Actually the design would involve you to design the aerodynamic blades, the number of blades, the shape, and the mechanical side would involve you to calculate the stress and strain on the blades, the mechanical gears, and also for the electrical side you will have to decide the peak wattage of the motors, the lock rotor currents, and etc. But here we are only looking at some of the few basic terms that we can use to implement wind turbine in ETAP. So here we have the energy required is about 4000 kilowatt hour per month, and the per day energy requirement is 133.33 kilowatt hour. So the average period of operation is 20 hours. This is actually an assumption. This value can only be attained by taking continuous survey in the location of the wind turbine installation. So that actually depends upon the location and the severity of the wind, etc. And so the total power required by the wind turbine will be about 6 kilowatts of power. And we know the power from the wind turbine is P is equal to 1 by 2 rho A U cube Cp, and from this we can compute the swept area, and this is about 16.60 meter square. And from that we could actually compute the radius of the turbine, and thereby we also have the diameter of the turbine. And we can also compute the TSR and determine how much number of blades this requires. So by using this design, we will go and implement a wind turbine in ETAP. So let's jump to ETAP. And here we are in ETAP, and you can see the project from the previous lesson, which involves the solar arrays over here, which are connected in two different methods. And here I have implemented the wind turbine already over here. So let us go to the wind turbine editor in order to see what are the values we will have to enter for this. So over here you can see the wind turbine type. This is generic, and I have selected the type 1, and the control is WECC type of control. You can also change the control to the user defined model, but I do not have any user defined model right now, so I will use the WECC method. And the ratings page, in the ratings page you will have to provide in the rating and the voltages over here, and I have put the design and the normal at 90% of generation. And in the model over here you can provide the locked rotor percentage, 650%, the power factor, and the grounding. You can also select the model from here, and from the library I have selected a high voltage, low slip, high torque. So let me select this high voltage, low slip, high torque, and from this I have selected this, and let me select this 100 HP, and I will update these values over here. And then we will have to go to the turbine over here, and in the turbine I have used the V rated as 12 meter per second over here, so I will have to provide that over here. And the swept area is 16.60. This is in meter square. The air density is in kilogram per meter cube, and the cutting speed is the minimum speed required for your wind turbine to operate. This is actually a aerodynamic design value over here, and the cutout speed is the maximum speed, wind speed that you want your turbine to operate. Again, this is also an aerodynamic design term over here, and this is the diameter of the blade, and this is the RPM of the blade and the pitch angle. And here you can see the power coefficient Cp, and I have used the sample data over here. As you can see, this involves a equation having about 9 different constants over here, and these are obtained based on empirical formulas and on the data collected from the location of installation. So I will use the sample data over here and going to the wind. So here I can select the average base wind speed, and I have, let me provide in 15 meter per second, and you can observe the wind profile over here. You can see the ramp wind. So these values, the gust wind, the noise wind, the turbulence scale, mean speed, frequency, etc., are actually obtained by conducting survey in the installation location. You can have devices such as anemometers to measure the wind speed and so on. And the pitch control area, I am just putting in the sample data over here. The pitch control actually regulates the angle of attack of the blades with the wind, and thereby this controls the RPM of the turbine. And similarly, the inertia page over here, you providing the values of the inertia over here, so that to conduct transient stability this can be useful. And now let me click this on OK, and I'm going to quickly run the load flow over here. And over here you can see that our wind turbine is already powering our system over here. You can see that this wind turbine is underexcited because we have used an induction generator over here. When an induction machine is used as a generator, it only generates active power, and the reactive power has to be provided by the grid. So this will always be in red color unless we change the type over here. So this is how you implement wind turbines in ETAP, and I will see you in the next lesson. In this lesson we will discuss about optimal load flow, and we will also conduct an optimal load flow in ETAP, and I hope by the end of this lesson you will understand the difference between an optimal load flow analysis and a simple load flow analysis. So let's get started. And over here we have the optimal load flow. We will discuss the difference between the optimal load flow and the load flow over here. So this is used by utilities for guidance and decision making. So in order to explain optimal load flow, I will use two different examples over here. So the example number 1. So in this example we have 3 generators connected to a single load. Each generator is capable of managing the load individually, and these 3 generators have identical capacities, identical fuel cost, and identical turbine systems, etc. And these are connected at different distances from the load over here. So the generator G1 is connected about 1 km away from the load, and the generator G2 is connected 3 km away from the load, and the generator G3 is connected 0.5 km from the load. So according to the load flow analysis, you can actually determine, or you can actually have different number of solutions. So say this is a 100 megawatt of load, and we can make the generator G1 generate about 50 megawatts, generator G2 generate about 25 megawatts, and the generator G3 generate about the other 25 megawatts. So in all we could provide 100 megawatts of load to this load over here. So what if we also take into the consideration of economy? So saying that all these 3 generators have identical fuel cost and identical capacities, say we will only take into consideration of the transmission cost. So here we have 3 different transmission costs. The transmission cost increases as the distance between the source and the load increases. So when we take into the economic factors as well, then most of us will select this generator over here, that is G3, because here when the fuel costs are all same and the cost involved in the transmission is much less for G3 compared to G2 and G1. So utilities will opt to start this generator in order to provide this load over here, because this is the most economic selection between these 3 generators over here. So here we have the difference between the optimal load flow and the ordinary load flow. So in the ordinary load flow we just assign and we can have different combinations of generations, but whereas in case of economic considerations and other considerations such as voltage constraint, security constraint, reactive power constraint, real power constraint, etc., we will opt for the optimal load flow, and the optimal load flow will give the most optimal solution in this case. So let us look at another example over here. So in this example we have a generation company which has 3 generators and having the following cost functions. So the cost function for the unit A is 15 plus 1.5 PA. PA, PB and PC are the value of power that is generated using this machine over here. So 1.4 PA plus 0.04 PA square, which is given in dollars per hour. And similarly for unit B, we have 25.1.6 PB plus 0.05 PB square. And similarly for unit C, we have this equation over here. So the question is, how should these units be dispatched for a load of 350 megawatt at minimum cost? When taking into consideration of ordinary load flow, we only need to meet this 350 megawatt without any consideration. We do not have any constraints. We can actually put in different ways as we want to, but here we have this constraint over here. So we will have to select these 3 units and appropriately size the generation values so that we have the minimum cost in this case. So I have solved this problem over here. So lambda A is the first derivative of the above cost equation over here, and we will have to equate for lambda A, lambda B and lambda C, and after equating you will get the power to be generated from the generator A is 95.3 megawatts and PB is 74.2 megawatts and PC is 180.5 megawatts. So in total we have 350 megawatts, and here we also have the cost of generation, and you can see that the cost involved in generating 350 megawatts is of $1,927.2 per hour. So this is the minimum cost that you could achieve in this case. We can also implement optimal load flow in ETAP with various constraints. Let us see some other types of optimal power flow. In this case we have different constraints. So in the economic load dispatch, here we will only consider the economic factors such as the fuel cost, the energy price from the grid, etc. And in the optimal reactive power dispatch, we will try to minimize the reactive power. So here the reactive power is the constraint, and the economic emission dispatch, here we will consider the emission as a constraint. We will have to reduce the emission. Over here we have the security constraint, so we will have to take into consideration of various contingencies as well. So in ETAP we can also perform this optimal load flow, and let us go ahead and do it. So here we are in ETAP, and I have already created a similar layout as explained in the example. We have 3 generators over here, and each generator is of 200 megawatts each, and we have these following loads over here. So let me conduct a load flow in this case, and you can see that this is the swing generator over here, and these generators are generating about 9 megawatts of power over here, and this is 4 megawatts of power. And you can see the total load over here, that is 5 megawatt plus 1.8 megawatt plus 4.5 megawatt plus 6.6 megawatt. So here I have assigned the values of generation, and I have not used any constraints in this case. So in order to perform optimal load flow, you will have to go to this portion over here, and you can see the optimal power flow analysis. Now select the optimal power flow analysis and go to the edit study case over here. And in the edit study case, you will get the study case editor. You can provide in the study case ID. This is the solution parameters, and here you can select different loading categories, generation categories, charger loading, initial conditions, load diversity, etc. And over here, so this is the objective or the constraint that we are selecting. So the objective constraint, so I have used the minimum real power losses, so the weightage is 100%, and I will also check this over here, so the minimum reactive power losses, and over here I have the minimum fuel cost as well. So I have selected these 3 constraints over here, and the weightage provided for these 3 constraints is 100 over here. And the bus voltage constraint, I am not providing any constraint for the bus voltage over here for now. And we can also provide in the branch flow constraint, so we can decide how much of power we need to limit for these 3 cables over here. And similarly generator AVR, and over here this is the generator MW. So here you can see that we are minimizing the cost that is involved with these two generators, generator 2, generator 3. So let me add in this also over here, and let me deselect all of these. Here the maximum megawatt is 10 megawatt. That is limiting our optimization. So let me go ahead and change that, and let me go to this generator over here, and in the fuel cost you can see we have the model type. I have selected the equation over here and provided the equation that I have used in the example over here. So providing the values for C0, C1, C2, and we can also provide in the fuel cost in dollar per mega bitumen. You have to provide in the generator limits. So the generator limits I will provide in the operating values, or if it is user defined I will provide in 150 megawatts. So the minimum is 0 megawatt and the maximum is 150 megawatts. And let me go ahead and show you this fuel cost for this generator, and let me change this to 150 megawatts. So even though the capacity of the generator is 200 megawatts, I will be limiting the generator to 150 megawatts of power, and the optimal load flow will be conducted based on that. So let me again go back to the edit study case and to the generator megawatt. I'm going to select generator 2, generator 3 and generator 4, and all the weightages are 100% or 100. If I want to change the weightage, I can change this weightage over here, ET, and let me provide in this value over here, and let me go back to the objective and verify this. Okay, we have minimized the real power losses, minimized reactive power losses, and the fuel cost as well. So let me click this on OK, and I will run the optimal load flow over here, and you can see that the power that is delivered from these three generators over here. So our generator number 4 is delivering most of the power, 7.2 megawatts, and over here we have 3.7 megawatts, and over here we have 4.4 megawatts of power. And here we have optimized our generation based on economic constraints, but when we look at the voltage at this particular bus, you can see that the voltage is 50%. So we will have to go ahead and provide in some constraints for the voltage as well. So let me go to the objective over here. I'm going to select the flat voltage profile, and I'm going to provide in a enforced constraint for the voltage as well. So this is the voltage constraint over here, and after that I'm going to run the optimal load flow again. So in this case you can see that the voltage has improved, and you can see that the MVAR generations has also changed in this case, and this is 7.8 megawatts of power, 4.3 megawatt and 5.7 megawatts. So this is the optimized power flow, taking into the consideration of the voltage, the fuel cost, and we can also provide in other constraints that are available over here. So let me close that, and when we compare this with that of the ordinary load flow, this is what you get. Our generator 4 is generating 5 megawatts, generator 2 is generating 9 megawatts, and over here we have our generator 3 generating 4 megawatts. And for the optimal load flow, we have the generators generating the power at the minimum fuel cost, and we have also constraints on the voltage as well. So now let us generate some of the reports over here. You can select the optimal setting report over here, and let me generate the optimal settings over here. And you can see these are the optimal operating conditions. So the generator 2 is operating at 4.263, and delta is the change from the rated value we have provided in, or the value from the normal load flow analysis. And we have the generator 3 over here and the generator 4 over here. So these are the optimal values for operation, and we can also provide in constraints for tap changers, SVCs, StatComs, etc. So I hope you understand the difference between the optimal load flow analysis and the ordinary load flow analysis. So that's all for this lesson, and I will see you in the next lesson. In this lesson, we will learn to perform unbalanced load flow in ETAP, and before getting into ETAP, we will have to look at some of the terminologies that is associated with unbalanced load flow. So unbalanced load flow is most popularly used by distribution engineers, where they have to balance between the loads on the various phases of a transformer and so on. So let us look into some of the terminologies that are associated with unbalanced load flow. So the main terminology is the voltage unbalance ratio. The voltage unbalance ratio is the ratio of the maximum voltage deviation from the average voltage deviation, and there are two terms that are used within the voltage unbalance ratio, that is LVUR, which is the line voltage unbalance ratio, and PVUR is the phase voltage unbalance ratio. So we will look at what these are. And the line voltage unbalance ratio is the maximum voltage deviation from the average line voltage deviation to the average line voltage, and it's expressed in percentage over here. And the phase voltage unbalance ratio, PVUR, sorry, here there should be PVUR, and this will be the maximum voltage deviation from the average phase voltage to the average phase voltage, and this is again expressed in percentage. And VUF, this is the voltage unbalance factor, and the 2 here represents negative sequence. So this is an index used in European standards to indicate the degree of unbalance, because when there is an unbalance in the supply, there will be greater amount of negative sequence. For a perfectly balanced supply, there will be only positive sequence alone. There will be no zero sequence or negative sequence. Whereas when there is an unbalance in the supply, there will be a negative sequence that will be introduced into the system. So determining the amount of negative sequence can actually give you an idea of the unbalance in the system. So VUF2 is given by the negative sequence voltage divided by the positive sequence voltage. And similarly, we have the VUF0, where 0 is used for the zero sequence unbalance factor. Zero sequence only occurs on the system when there is a connection to the ground. So here we can also use this term. Generally there will be 0% of VUF0. However, we will talk about this term. So VUF0 is given by the zero sequence voltage to the positive sequence voltage, and again this is represented in percentage. So the next factor is the current unbalance ratio. Similar to the voltage unbalance ratio, it is the deviation in the current from the average value or the specified value. So similar to the voltage unbalance ratio, we have the line current unbalance ratio, the current unbalance factor to IUF2, and similarly IUF0. And the line current unbalance ratio, or the just current unbalance ratio over here, so this is given by the maximum line current deviation from the average current to the average current over here. So this is the ratio of this deviation to the average current. And IUF2, similar to that of VUF2, here this will be given in the ratio of the negative sequence current to the positive sequence current. And similarly, IUF0 will be the ratio of the zero sequence current to the positive sequence current. So now we have gone through all the terminologies that are associated with unbalanced load flow. So we will go to ETAP to perform an unbalanced load flow. And here we are in ETAP, and as you can see, I have already made a single line diagram for the demonstration, and this consists of a power grid, 2 generators, and 3 different nodes over here. And let me go to the power grid editor. In the power grid editor, you will have to go to the ratings page, and here you have 2 options. You can provide in a balanced supply or an unbalanced supply. So in the unbalanced supply, I have provided these values, that is, I can provide different magnitudes for the different phases over here. These are in percentages. I can also change the angle over here, so I can also introduce unbalanced based on the phase shift between these phases over here. And let me click this on OK. As for the generator, we cannot provide in the unbalanced except by providing different loads on different phases. All generators are inherently balanced, and what happens when there is an unbalance in the case of a generator is that a negative sequence is generated. So the negative sequence which is generated will cause a negative torque on the turbine. So when a negative torque on the turbine occurs, there will be damage to the turbine, and in the protection viewpoint we will have to provide in a negative sequence overload protection for these generators over here. And then for the load, go into the load over here and go to the nameplate. On the nameplate you get this option over here. So this is the model type, and from the drop down list you get various model types. So the conventional is the balanced load over here, and you have the exponential, the polynomial, the comprehensive, etc. And we also have the unbalanced. So in the unbalanced, it is possible to provide different loads for the different phases, including different power factors, different MW loads, etc. And this is how you can provide a single phase load to a 3-phase bus. So click this on OK, and similarly I have modeled all 3 loads in the unbalanced type over here. Here you can see that all the loads are 2 MVA, but the resulting power factors are different. So let me close this, and in order to perform the unbalanced load flow, you will have to go to this mode over here which says the unbalanced load flow analysis. Now using this mode over here, on the right side you get the options over here, and on the topmost you get the run unbalanced load flow. So when I click this, you get these values populated on your single line diagram. So I have already generated an output report over here. So when you run it, you will be asked to enter a output file name. So here you can see this is the voltage drops over here, 0.024 kV line. This is the voltage drop of this cable over here, and similarly the voltage drops of all the cables are populated across the single line diagram over here. And let me go to the display options. On the display options, let me check in the amps over here. So, and over here you get the average of the phases. So the values of the loads here is the average of the 3 phases. So I want to have the values of all the different phases, so I'm going to check on all phases and I'm going to click on OK. So here, let me push this aside. So here you get the amps for all the different phases. So this is the first phase or the A phase, then we have the B phase and the C phase. So the C phase has 316.3 amps. So let me go over here. Okay, the C phase has 314.9, so that's correct. And let me go over and select the all sequences, and from the sequence you get all the sequence, that is the positive sequence, the negative sequence and the zero sequence. So when there is an unbalance, there will be negative sequence involved. So when I click on all sequences, you can see that the amount of negative sequence that is here. So you can see the negative sequence is increased. So this is 162.3 amps and 43.62 amps and 12.13 amps. So here you can also see the various voltage drops on each phases for the sequences and for the different phases. If you go to the display options and change that, and here also you get the negative sequence voltage on the entire bus over here. And the other option you can have is to provide in a fault insertion. So you will provide a single phasing, that is to disable one of the phase. So what this option does is that it opens the A phase of the power grid. So here in this case this will be the power grid, and over here this will be the generator. So when I cut off the phase of A phase, then this will be the amount of the negative sequence or the unbalance that will be introduced in the system. So let me put into all phases, and I'm going to provide the kW values. So here this will be the different load values, and the next thing you can do is go to the alert view over here, and in the alert view you can observe the options over here. At the bus 3, the line voltage unbalance ratio, the positive sequence is 1.62 for the phase A, 4.2 for the phase B, and 2.6 for the phase C. And similarly you get these values. You can see that at bus 5 you have the 0 sequence VUF0, at bus 5 you also have the VUF2, and at bus 5 you also have this line voltage unbalance ratio. So there is a voltage unbalance, and when you go down you also get this current unbalance over here. On the cable 2 you have the current unbalance IUF2, IUF0. So for this demonstration I have created an unbalance significantly so that I could demonstrate this for you, but in actual projects you will not have this amount of unbalance. So if you want to toggle the alert view, you go over to the option over here, and over here you can provide in the different critical values over here. So this is 3%, this is also 3%. These are the default values. I usually keep at the defaults. So on this page you can also increase or decrease the precision, the maximum iterations, etc. And these are all basically the same options that are seen in the load flow analysis, and similar to all the other options you get to generate different reports from the report generator. And so this is how you run unbalanced load flow analysis in ETAP, and I will see you in the next lesson. In this lesson we will learn to perform optimal capacitor placement in ETAP, and on the screen you can see this is one of my previous examples that I have used in protective device coordination, and I have changed these two loads over here, and these are put at very low power factors so that there will be a drop in voltage at this bus. So let me conduct a load flow over here, and you can see this is the voltage at this bus. This is only 95.81%. So what I am trying to do is to improve the voltage profile at this bus by introducing capacitor bank. So what the capacitor bank does is that it supplies the reactive power that is required for these two loads, so that the reactive power is no longer required from the grid over here. So this causes the voltage at this bus to improve. So ETAP has this option of providing you with the optimal number of capacitor banks, also taking into account of the economic factors as well. And by using this tool in ETAP you can perform the capacitor bank sizing. So in order to perform the optimal capacitor placement, you will have to go to this option over here which says the optimal capacitor placement. So go to the optimal capacitor placement, and on the right side you have these options over here, and for now I will go to the edit study case option over here, and on the edit study case you get the info of the case study, and you have the objective. You can provide the voltage support, the power factor correction, or both. So let me go to the loadings page, and here you have the diversity factor, the loading categories, generator categories, etc. And here you have the voltage constraint. So you can provide in a global voltage constraint. So this global constraint is 110% and 95%. And here you can provide in individual constraints as well. So I'm going to turn off the global constraint, and my constraint will be for the bus number 3. So the voltage will be 105. So the maximum voltage constraint is 105%, and the minimum voltage constraint will be 98%. So these are my constraints that I'm going to provide in. So let me select this. So here I have the individual constraint and the voltage in percentage. So the minimum voltage can only be up to 98%, and the maximum voltage can happen up to 105%. And if we have the power factor constraint, you can provide in the power factor constraint as well, but here I'm only considering the voltage profile. Here we have the capacitor information, and from the capacitor information you can see that there are various capacitors that are available over here, and you can select any of these capacitors, and you can also provide values over here for the maximum value, the bank size, etc. So here I'm going to select this capacitor, that is the maximum kV rating is 0.48, the bank size is 100 kVR, maximum number of banks is 10, and the cost per kVR is 10, the installation cost is 600, and the operating cost for a bank per year is 100. And so I have selected this capacitor, and then I am going to select this bus. So the bus candidate is bus number 3. So usually this will be over here, and you will have to click this on add, so that the candidate is bus number 3, and then I'm going to click on OK. So now we can go to this option over here and run the optimal capacitor placement. So you will have to provide in an output file name. So I'm going to provide a output file name, and after this ETAP will populate these values alongside the bus. So the bus 3 is the candidate over here, and the optimal number of banks is 10, and the kVR is also provided over here, the amps, the rated kV, and the rated kVR. So in order to verify this, what I'm going to do is to add a capacitor bank with the following specifications. So the number of banks is 10, and the rated kVR is 100, and the voltage is 0.41. So let us do that. So here we have the capacitor. I'm going to connect this capacitor to my bus over here, and I'm also going to provide it in a switch. So this is a single pole switch. Go to the capacitor, go to the ratings page. The kV will be 0.41. The number of kVR per bank is 100. The number of banks will be 10, and the maximum voltage will be 0.5. And I'm going to click this on OK, and then I'm going to run the load flow. So after running the load flow, you can see the voltage improvement over here. So because I have provided the constraint value for 98%, the voltage has improved to 99.39%. So this is a great improvement, and the voltage cannot go down below 98% according to this constraint. So the software, the ETAP module has performed the optimization over here. So this is how you can perform optimal capacitor placement in ETAP, and I will see you in the next lesson. This lesson is about switching sequence management, and we will see how we can perform the switching sequence management in ETAP. So on the screen we have the single line diagram, and this is the single line diagram of an industrial network having several distribution transformers and one generator transformer over here. So what the switching sequence management does is to understand the response of the system during the switching operation. So there are two ways in which we can do that. One is a kind of manual way, and we also have a sort of automatical way of doing it. So let us see how we can do the switching sequence operation in these two modes. So what we are going to do is that I'm going to put this bus this is a 110 kV bus, and I'm going to put this bus into permit. So in order to put this bus into permit, I will have to isolate the bus from the downstream as well as the upstream ends. So to do that, I will have to operate these 3 circuit breakers and these 2 isolators, and afterwards I will have to close in these ground switches over here. So in the ideal case, the ground switches are the switches that are to be closed at the last instant. So we cannot have the ground switches closing when the system is in live condition. So we will have to provide a sort of interlock in there, and to do that we will have to go to the ground switch, and in the ground switch we have the interlock tab over here, and in the interlock tab we have 2 logics over here. We have the pre-switching logic and the post-switching logic. So in the pre-switching logic is the logic which is to be satisfied before the action can take place, and similarly for the post-switching logic we have the action taking place, and afterwards the condition is to be satisfied. So I have selected the pre-switching logic, and in the pre-switching logic I have put the close as active, and I have provided the following switching condition. So let us see what the switching condition is. The switching condition is CB1, CB36, CB3, SW2, SW3 all have to be opened. You can see the AND operator is used. So all these conditions has to be satisfied. So CB1, CB36, CB3, S2, S3 has to be in the open status or the open condition over here. So here we can provide in these conditions by using the drop down menu available over here, and if you want to add in any other line, you just go to the last line and click on add, and after that you get new lines, and you can also delete the previous lines over here. So I have provided in the same switching or the interlocking over here as well, the same pre-switching logic for this ground switch as well. So when you're going to isolate the incomer to your system, you will have to turn in the backup power. So the backup power is provided by means of this generator over here. This is a 10 megawatt generator which is connected to a generator transformer over here, and as you can see, let me go over to the load flow. So in the load flow you can see that these 2 loads over here have about 15 megawatts of power. So this generator will not be able to supply power to both of these loads over here. So we will have to provide some type of load shedding in this case. So let us see how we can perform this switching sequence. So I'm going to perform 2 types of switching sequences over here. So let us see what the response of the system will be for these 2 types of switching sequences. So let me go ahead and perform it. So first thing you will have to do is to go to the load flow analysis over here and check in the auto run. I am going to turn on the auto run, and afterwards you will have to go to the switching interlock enforcer, and I'm going to click on this. So we have the switching interlock enforcer active. So in later versions of ETAP you have a padlock over here. That's the same switching interlock enforcer. So the first thing I'm going to do is I'm going to double click over here. So in the auto mode on, when I click on any of the switching elements, so it opens or closes. So when double clicking over here, I have the generator turned on into the system over here. So and that's it, and afterwards I'm going to open this circuit breaker over here, and I'm going to operate this circuit breaker over here, this circuit breaker over here, and this one over here. So you can see during the switching process, you can see that the voltage has dropped at this bus to 92.56, and when I open this bus is de-energized, and you can see during the entire switching process our generator is in the overload condition, and then I will have to provide the load shedding. So I'm going to shed this load over here, and for that I'm going to operate this bus coupler over here. So still we have the generator in the overload condition over here, and I'm again going to open this and this. So now the generator is not in the overload condition. So as you can see that during the entire switching sequence or the switching operation taking place, the generator was in the overload condition. So when I followed this switching pattern or switching sequence, the generator is mostly in the overload condition. So I'm going to implement another switching logic, so let me do that. And for the interlock option, when I try to close this ground switch, you can see that the switching interlock enforcer comes over here and says that the action is conflicting because these two switches are in the closed condition. So now the switching interlock enforcer is not active. So I'm going to click on this to activate it again. So I have clicked that over there, double clicking this, and now when I switch on the ground switch, it gets grounded because of the interlock enforcer. So let me go ahead and make another switching pattern, and here my priority is to not overload the generator. So let us go ahead and put our system in the previous state over here. So now our system is in the previous state, and let us follow a different switching pattern. And in this switching pattern, I am going to make sure that the generator is never overloaded. So let us see how we can do that. I am going to switch on this one over here, and I'm going to open this bus coupler and this over here. So load shedding has been already done over here, and then I'm going to open this breaker, this one, and this one. So during the entire switching process, you could observe the variations in voltages, the generator overloading or the bus voltage variations, etc. So when opening or closing the entire thing, you can see this. So when I close this, so here prior to opening this portion over here, you can see that the generator is providing load over here. So when I open this breaker over here, you can see there's a dip in voltage, and again when this is open, there's a variation in voltage. So during the entire switching operation, you can see the variations in voltages, the overloading conditions, etc. So this is a sort of manual approach towards this. So by using this tool or this method, the operator can make sure whether there is any critical or marginal conditions that occurs on the system. So now we observe the two different switching patterns and their responses by the system. So in the first case, you have the generator mostly in the overload condition, whereas in the second switching sequence, our generator is not in the overload condition at any instant during the entire switching process. So this is a manual method of doing it, and there's another method of doing it, that is by using the switching sequence management. So the switching sequence management is available in the mode toolbar over here. Just go ahead and select the switching sequence mode. So I have already made a switching sequence over here, so let me go ahead and change that. And before that, I'm going to perform these operations, so the system will be in the previous state. Okay, now our system is in the previous state, and going to the switching sequence management, and then we will have to go to the edit switch sequences. So let me delete in all of these switching sequences because I want to explain all of these. And you can see we have the switching sequence editor, and I can provide in the switching sequence ID. So let me provide in a new switching sequence ID over here, and here we have the switching sequence ID, and let us see how we are going to operate it. So I am going to follow the first switching sequence where the generator is mostly in the overload condition. So let us see how that goes. So when I click this on over here, we have the switch closing over here, and this is automatically updated in the switch sequence editor. And let us just follow the pattern over here. So this opens over here, this opens over here, this opens over here, these two opens over here, these two, and finally this. So here we have the switching sequence over here. So I'm going to I'm going to click this on OK, and then I will run the switching sequence. So when I click on the run switching sequence, we get the sequence view over here, and we have the actions populated on our single line diagram. So let us go ahead and see this over here, and over here we have the alert view. So here we have the various alerts during the entire process. So we can also override the pre-switching conditions or logics as well directly from over here. So this is the condition where our time is 0, because I have not provided any time duration or any time. So let me show you that. You can see I can provide in the time delay if I want to. So say the last operation takes place, like takes about 10 minutes to operate, can be provided over here, because all the switching cannot be taking place instantaneously. There will be some amount of delay between each of the switching operations taking place. So I'm going to click this on OK. Again, go to the run switch sequence, and see over here we have the alert as explained before, and in this condition you see the action status is not available here, so that none of the switching sequence is available, and all these alerts are prior to the switching sequence taking place. So here we have the execution control, and in the execution control I'm going to click on the step start option over here. So now we can see our first action is completed, and these are the number of alerts over here. Similarly, the next action is taking place, and these are the alerts over here. And I can go on clicking the step execute, or just click on the auto execute over here. So this executes the operation, and after the time period it automatically goes to the next operation. So here all the operations are taken place over here, and these are the final alerts over here. So during each of the switching operation you can see the various alerts occurring over here. You can see still the generator is in the overload condition over here, and it is after the 10th action you can see that the generator is not overloaded. So I'm going to create a new switching sequence. This is A2, and I'm going to delete all of these. So I'm going to delete this, and let us begin with the second switching sequence. So that is, this will turn on. So we have the other switching sequence over here, and I'm going to click on OK. I'm going to run the switching sequence and go ahead and step start this over here. And in this switching sequence you can see the generator is not at all overloaded during the entire switching sequence. So here this is the automatic way of doing it, and this can also be used with real-time systems where you can obtain the real-time load flow values, and you can observe the system responses to your various switching activities. So this tool can be used by operators in order to foresee what all changes you could create on the system due to various switching operations. So whether you have to turn in the generator on first, or you have to provide load shedding first, or etc. So the priority and the switching order actually determines the various responses on the system. So here in this lesson we have performed the switching sequence management both manually as well as automatically. And that's all for this lesson, and I will see you in the next lesson. So here we are in ETAP, and here you can see that I'm starting to build a single line diagram, and this is a simple single line diagram which converts the 415 volt AC to 110 volt DC using a charger over here. And in order to go to the control systems diagram, you will have to provide a source for the control systems diagram that is provided from the single line diagram over here. So in order to provide the source, you will have to go to the DC toolbar and select the composite CSV. So go ahead and fetch that from over there and go ahead and put it over here. and then go ahead and double click on this, go to the ratings page and provide in the voltage ratings. So now you have the voltage ratings, and in order to go to the control systems diagram, go to your systems toolbar, and in the systems toolbar you will get the control systems diagram. So go ahead and select the control systems diagram, and you will enter to the control systems diagram. So usually it will ask for a new presentation, so go ahead and click that on OK, and afterwards you will head into the control systems diagram mode. And over here you have two options in the mode toolbar, and you have the following elements you can draw in the single line diagram or the control systems diagram over here. So first thing you will have to do is to bring in the source from the single line diagram over here. So let me go ahead and bring this source over here. So in order to bring the composite CSD from the one line diagram, you will have to select the composite CSD from over there and hold the shift key on your keyboard and drag it to your control systems diagram option over here. So you will get the DC source in the control systems diagram, and the next thing you will require is a DC bus. So the DC bus is over here, and you can see there are two buses over here. One is the positive rail and the other is the negative rail. So let me go ahead and connect my DC source to the positive rail and the negative rail as well. So this is connected to the positive rail and the negative rail, and you can see the initial voltage is 100, and because I have not operated this operating voltage is 0. So let me go ahead and put a switch on the positive rail. So this switch is over here, and I'm going to also provide a circuit breaker as well. So circuit breaker, double click on the circuit breaker, go to the library. So this is a thermal magnetic type, and just select some circuit breaker over here, and after that let us go to build the project. So in this lecture I will be drawing a simple relay latching logic. So let me go ahead and do that. So the first thing you will need is a push button. A push button is available over here, and go ahead and connect that to the positive rail, and then you will need a control relay. So the control relay is over here, and you will need a contact as well. So there are several types of contact available here. You get the form C contact, the macro control contact. So I will show you that in a bit over here. So let me go ahead and connect the contact over here, and I will need a node in between this so that I could connect this all together. So I have connected everything here accordingly, and okay, then go ahead and connect the relay to the negative rail over here, and I'm going to provide another contact over here. So another contact comes over here and is connected to a general load over here, and connecting the load as such. And then let us go ahead and write the components over here. So the relay, go to the relay, and in the relay you get the control relay. This is the device number 1, and go to the ratings page, and in the ratings page you can provide in the voltage ratings, the burden rating, and also the inrush rating and the duration of the inrush. So let us go ahead and select the library over here. I'm going to select the Allen Bradley, and I'm going to select this relay, which is a 110 volt relay. So go ahead and select this, and let me provide an inrush rating over here as well, and the time of duration is 1 millisecond, and the contact. So this relay has two types of contact, that is a form C contact, and here my contact is not the form C contact, this is a conventional contact over here. So I'm going to assign this contact to this relay, and to do that I will have to go ahead and click this on add. So we have two convertible contacts over here. So I have put the status as normally open, and the voltage rating is 110 volt DC. So after that I can go ahead and provide the contact ID over here. So you have to fill in the other details as well. So I have assigned the contact device 1 3. So after clicking on OK, now this contact is assigned to this relay. So when this relay acts, this contact will be closed over here. And similarly, you can assign the contact in another way. Here, go ahead and select the contact controlling device assignment, and you can select the type of device over here, and these are the contact available for this device. So the contact number 4 is available over here, and I'm going to select this. So again, this is linked to this relay over here. So when this relay is energized, you get the contact. These two normally open contacts will be turned to close, and the rating for the load will be say 10. So I'm going to click this on OK, and now let us see how the operation works. So okay, I'm going to provide in a switch over here, and I'm going to put this on the closed position. So this is a normally closed push button, and this is a normally open push button. So go ahead to your voltage drop mode, and as you can see, we have the sequence of operation over here, and this is in the auto run mode. So everything is okay. Let us go ahead and push this button over here. So this will push to close. So when I push this to close, the condition of these normally open contacts are now in the closed condition. So this is called the relay latching. So relays usually operate when they are energized. So this push button only energizes the relay for once. So you can double click on this, and you can see the operating time is 100 milliseconds, but still the relay is now in operation, because when I push this, the relay gets energized and this contact plus closed over here. So this contact is now providing the energizing for this relay over here. And in order to de-energize the relay, I will have to go ahead and push this push button. As you can see, now the relay is de-energized. So this is what is called the latching, and this is the fundamental logic behind every automation project. Okay, now let us go ahead and make use of the other contacts that are available in the relay itself. So let me select the form C contact over here. So the form C contact is over here, and I'm going to connect the form C contact over there, and I'm going to connect a light bulb. So this is the light bulb over here, and I'm going to connect this light bulb over here, and the remaining portion will be connected to the DC negative bus. So this is the device 3 here, and I'm going to connect. Okay, I'm going to leave the other portion right there, and let us see how the operation will work. So the rating will be 1 watt, and this will be 110 volts. And go ahead and click that on OK. Now go ahead and assign the contact. So the device has a contact over here. So I'm going to select the contact. This contact is now assigned to the relay over here. So let me go ahead and do that. So let us see how that works out. So I'm going to push this on close, and you can see now this is in the position B. So in the position A, the normally open contact and the normally closed contact were there, and when the position changed over here, you can see the normally open contact is now in the closed condition, and the normally closed contact is in the open condition over here. And let us go ahead and also make use of the macro controlled contact as well. So here we have the macro controlled contact, and I'm going to provide in a light source as well over here. So go ahead and provide the light source to the macro controlled contact, and I'm going to provide in the rating 110 volt, burden rating is 1 watt. And go ahead and select the macro controlled contact and go to the duty cycle. The macro controlled contact is a contact that is dependent on time. It's sort of a timer that will get energized after a period of time. So let me go ahead and provide in states over here. So this will be in the off state initially, and this will come into the on state after say 1000 milliseconds, and I'm going to click this on OK. So let us see how this works out. Now let me go ahead and I'm going to push this over here, and you can see after the 6000 millisecond this has closed over here. So that is already closed over here. If you want to check that out, you can see I'm going to increase the time delay. So let us increase the time delay. Let us see how this works out. Okay, this is, you can see this is closing after the time delay over here. So I'm going to also push this to close, and you can see the other contacts getting energized as well. So now what we have done is, in the sequence of operation, you can also perform the load flow in order to calculate the voltage drops at various nodes. So let us go ahead and do that. So here I have another control system diagram. As you can see over here, the diagram is a little different from what we did previously, but this is the same relay latching logic. You can see I'm going to push this on. Now this device is energized, so you can see the current state is operated over here, and when I push on this, you can see now this is the operated state and this is in the idle state. So it's basically the same relay latching logic over here, and let us go ahead and perform the load flow calculation with voltage drop. So let me go ahead and put in a wire. So go ahead and select something from the cable library, and the length will be 100 feet, and click this on OK, and I'm going to provide in a solenoid. So here I will have a node over here. So the solenoid rating will be 100 watt solenoid. You can select this from the library as well. So I'm going to provide in the user defined ratings over here. I want to see significant voltage drop over here, and I'm going to provide in a light bulb over here as well. So here we have another node as well, and here the wattage rating will be 10 and the voltage rating will be 110 volt DC. So let us go ahead and go to the voltage drop mode, go to the edit steady case option over here, and in the edit steady case you get the simulation method, and in the simulation method just go ahead and select the load flow calculations. So go ahead and click this on OK, and go ahead and run the simulation with voltage drop. So now you can see the voltage drops over here. These are the voltage drops. So let me go ahead and provide the voltage at the nodes as well. So here you can see the voltage at this node is 109.99 volts, and the voltage at this node is 99 volts, and the voltage over here is 99.9 volts. So here you will get the voltage drop at different nodes over here, and you can decide what the burden of the device, and you can select the device and the burden of the device so that the voltage across the positive and the negative rail should not decrease beyond a particular limit. So this is how you can perform the voltage drop calculations with the load flow in the control systems diagram. And you can also generate reports over here. The voltage drop report can be generated over here. You can see the voltage drops over here. This is 10 volt, that is 9.09%, and the maximum voltage drop occurs across the light over here. This is 90.9%, and you can also get the power consumed in watts over here. So this is a pretty useful calculation over here. And that's all for this lesson, And in this lesson you just saw how we can implement DC control systems in ETAP, and the possibilities that the control system diagram give is enormous. You can implement any type of control system that you want to, and you can also verify the voltage drops, the sequence of operations, etc. using the DC control systems diagram. So I will see you later. In this section, which is the advanced practical project section, we will learn to simulate power system networks, complicated power system networks such as these on my screen over here. So the grid shown over here is only a part of the grid in state of Kerala. So this grid is a part of the Kerala State Electricity Board grid, and this is only merely a portion of the grid over here, and I have omitted some of the details in order to make the single line diagram more simple. You can see I have not used protective elements such as circuit breakers. I have only used these single pole switches over here which function as a isolator, and you can see all the symbols are different from which we used to do, because Kerala State Electricity Board follows the IEC standards and 50 Hz frequency. So when you change the standards, all the symbols change to IEC, and everything else is most likely the same as that of ANSI standards. So the green bus over here is actually a 220 kV substation, and all the reddish buses are 110 kV substations, and the bluish buses are 33 kV substations. So in this lesson we will be simulating transient stability analysis on this network. You can see over here we have two 5 megawatt generators connected to this substation over here, and we will analyze the performance of the grid, the substation voltages when a fault occurs on this substation. So what will be the generator or triangles, the voltages, and the effects on other substations. So let us begin by conducting a simple load flow analysis. So everything is fine except for the under voltages over here. We will perform another analysis or simulation in order to improve the voltages at all these substations. So that will be for another lesson. So in this lesson we will be looking at the transient stability. So let me go to the transient stability analysis over here, and let me go to the edit steady case option over here, and in the events you can see I have already created the event over here. So I will be faulting this bus over here, which is a 110 kV substation, and the fault will be cleared at 1.1 second, and the fault is initiated at 1 second. And I will plot the two generators over here and all the 110 kV substation voltages as well as the 220 kV substation voltage. And before we enter into the simulation, I have to say that I have made a large number of assumptions for this network. So let us run the transient stability analysis over here. And I have the time slider over here, and the fault was initiated at 1 second and it was cleared at 1.1 second. And let me observe the transient stability plots. Because the generators were open at this point, I have used simple single pole throw switches like these over here at many instances to make it relatively more simple than using circuit breakers and other protective devices. So these actually function like some isolators. And let me observe the bus voltages. Okay, I will select only the 220 kV substation for the Malaparamba. and let us just observe the plots over here. So you can see the variation in voltages with respect to the percentage of the nominal, which is 110 kV. So this is 100% of voltage, and 100% means 110 kV. So in this case, for the 220 kV, the 100% is the 220 volts. So let me zoom in a bit so you can see over here the green one, the record substation or the 110 kV substation at record actually reached 0 voltage, and the other substation retained some of the voltage during the period of fault, which is normal. So let us observe what happens when we connect these generators to the network. So right away I'm going to the plots option over here. I will plot the relative power angle alone. Okay, we will get the speed as well for these two machines over here, and for the case of buses I will select all the 110 kV substations and including the 220 kV substation. So let us observe the plots over here. So this is the bus voltages over here. So let me zoom in a bit. So you can see it was something similar to the previous results, and let me then observe the generator plots alone. So these are the generator plots. You can see the generator speed is shown over here. So this is the generator 1 and the generator 3. You can see only a single graph because both of them are superimposed over each other, because I have used identical machines at identical speeds and identical characteristics. So you can see the speed oscillates with respect to the fault which occurs at 1 second over here. So the fault occurs at 1 second. You can see the machine accelerating and decelerating, and this is the relative power angle. You can see this is the actual power angle at this point, and the power angle, relative power angle, starts to oscillate at the point of fault. So now we have conducted the transient stability analysis, and we can generate a report and submit it to the authority. So what my conclusion was that this grid is pretty stable, and the impact of these two generators during the fault on this substation is not severe. So everything is within the acceptable limits. So we don't have to worry about the transient stability when we have these two generators over here. One more thing which I want to show you is that you can actually perform the transient stability analysis with these isolators open. In any case, you can see this substation is connected to this substation, and this is connected to this substation over here, and you can also see this substation is connected to the substation over here. In fact, this substation has two feeders over here, two 110 kV feeders, which are basically feeding from the same source. So you can actually open any of these and you can run the load flow, and you can also observe the transient stability analysis in several cases. So this is one of the configuration. So in order to make multiple configurations, you can actually go to the configuration manager over here. So I have created two configurations, and one is the generator off configuration. So just go to the AC switches single throw over here, and you can see I can open or close any of these configuration switches over here, and it automatically changes everything. So now we have this open over here, and in case of complicated networks, if you are having any trouble knowing if any part of the network is de-energized, you just need to go to the check circuit continuity. So you can see over here, let me turn this off as well. You can see the circuit continuity. These two substations are isolated in this case. And that's all for this lesson, and I will see you in the next lesson.